Even if you know nothing about chemistry, you are at ground zero. But still, by the end of this one shot, I promise you can at least make 3 or maybe 4 question, and if lucky 5 correct attempt in your January JEE mains. I welcome all of my dear students to this amazing one shot of chemical bonding, where I have coupled and summarized all the block theory, including all the relevant basics of chemical bonding. In fact, a bit larger to some extent, because this chemical bonding will be very useful for organic chemistry also, and obviously it's a backbone of inorganic chemistry. Do not worry about writing all these lecture notes, because all the lecture notes, and especially for inorganic chemistry, the hand-picked problems that I have selected for you, you can obviously download all of them for free. From where? Just go to the description section and you will find the PW app link, the amazing app which is helping millions of students every year to excel in their competitive journey. So let's start the process. So to begin with, we already discussed in our chemical bonding one shot video previously that octet rule failed. Initially, it was thought that atoms in nature combine to form inert configuration, but after discovery of inert gases compounds, the octet rule and the Cossel and Lewis concept was completely blown. And post development of quantum mechanical model of an atom, valence bond theory came into picture, which simply said that atoms in nature combine with each other to pair their unpaired electrons. For example, if I have 2 hydrogen atoms, they will be having some potential energy as per thermodynamics. And if they are very much in love with each other, so they will approach each other because of some attractive forces. And because their attractive forces will be dominant, so at a distance of about 74 picometer between the two nucleus, that becomes the bond length of hydrogen atom, they attain and acquire a minimum potential energy. So if energy is minimum, then this signifies that yes, they are in love with each other and they want to approach each other, which results into the formation of a chemical bond. So valence bond theory told us that these atomic orbitals overlap with each other. More be the extent of overlapping, stronger is the chemical bond formed between them. But this chemical bond formation is revolving around the concept of orbital overlap. So let us again revise those orbitals which we have already studied in atomic structure. Now, orbital is actually a region around space where probability density of finding electron is maximum. And what quantum theory has taken electron to be? Quantum theory has mathematically formulated electron as an electron wave which has a positive notion and a negative notion. Solving the Schrodinger wave equation, we get some solutions, and those solutions are mathematically plotted. The probability is mathematically plotted, and the plots which we get is the shapes of orbitals. So these orbitals, the positive and negative sign which these orbital has, they are not charge, they are the phases of an electron wave. Now, why I am telling you this is because we have a term called Gerade and Ungerade set of orbitals. Although when we'll be discussing coordination chemistry, over there even NCERT, although does not describe these ungerade and gerade orbital terms, but when you go into splitting of d orbitals, you always see this term T2G and EG. That G represents the gerade term. So NCERT is a very mysterious book, and although that G is not written anywhere, but they have included that logic, and it is our responsibility to tell you what this gerade and ungerade mean. We will be discussing more about this Gerade and Ungerade in the molecular orbital, but molecular orbitals are formed from atomic orbitals. So let us understand what is this Gerade and Ungerade term is. So the symmetry in the orbitals is a point from which lines drawn on one side and produced to an equal distance on the other side will meet the point, and if this new point the sign is same, then the orbital is termed as Gerade orbital. Sir, I didn't get anything. Let me give you a picture. That's why I've given again these orbitals. Now, what I'm asking you to always remember is when you see an S orbital has same wave notion. It is either all positive or it is either all negative. It do not have both the notions. Point number one. Now, if we know this, and let's say this is the molecular axis. Now, what's a molecular axis? For example, if a nucleus is approaching another nucleus, then they will approach each other. The distance of approach, the axis along which they approach each other, is termed as the molecular axis. So let's say if this is the molecular axis and this is my center point. So from this center point, if I'm moving, let's say, to a distance x upside, and let's say if I'm moving to the same distance x exact opposite downside, what sign, what wave notion I'm getting? Positive. Over here also what notion I'm getting? Positive. So because I am getting the same wave notion, this is not charge, this is notion, this is positive and negative notion of a wave. So because it is all symmetric, so s orbital becomes a symmetrical orbital, and therefore it is termed as a Gerade. S is termed as a Gerade atomic orbital. Now coming to d orbital, we know d orbital are of the shape of d orbitals. How many type of d orbitals we have? 5 type of d orbitals. Out of those 5 d orbitals, we definitely know 3. For those 3 d orbitals, their lobes lie in between the coordinate axes. What are those? Sir, dxy, dxz and dyz. Now you again have to always keep this thing in your mind that if this is positive, then this is positive. Opposite lobes are of same wave notion. If this is negative, this is negative. Similarly over there, if let's say this is negative, this will be negative. If this is positive, this is positive. So now what about their Gerade and Ungerade nature? Okay sir, draw a point. Okay beta, drawn a point. Now move, let's say move towards this at an angle of, let's say, 45 degree. So if I've moved here, I see a negative sign. Exact to the equal distance, move to the other side. Does the wave notion, the sign is same? Yes sir, that is also negative, this is also negative. So d orbital is also a Gerade orbital. Let us check the 2 orbitals where the 2 type of d orbitals where electron lobe, the orbitals are found along the coordinate axes. This becomes d x2 y2. This becomes d z square with one lobe oriented along z axis and a one Saturnian lobe along the xy plane. Okay, so again, if this is positive, this is also positive. You have to keep this thing in your mind. So this becomes the negative notion. What about this? Sir, if this is positive, this will be positive. If this is negative, this will be negative. Now tell me about their Gerade and Ungerade nature. Okay sir, go to a center, gone to a center. Move some distance to one side. Okay, what is the sign you see? Negative. Move the equal distance opposite side. Okay sir, this is the point. What sign you have reached? Sir, negative. So this is also symmetric about the center. So this also becomes a Gerade orbital. Now again coming to this slide. Okay, so all s and all d orbitals are Gerade, but this p orbital is ungerade. How can you see that? Come to a p orbital. Let's say this is an internuclear axis. Okay sir, if this wave notion is positive, then this is negative. So if I'm moving, let's say, to a distance of x upside, and if I'm moving an equal distance x downside, do I get the same Sign? No, I'm not saying charge. Do I'm getting the same sign of wave notion? No. So because I'm not getting a symmetrical sign, so it becomes an ungerade atomic orbital. These are again d orbitals, which we can clearly say if this is plus, because here I've taken color also to tell you that these both are of same notion and these both are of same notion. These both are of same notion, and the Saturnian lobe along the xy plane, if I'm drawing dz square, then this definitely becomes the z-axis, because in atomic structure, through atomic structure, what we already know is for dz square, there is a one lobe along z-axis and a Saturnian lobe. The probability of finding electron lies in the xy plane as well, and that Saturnian lobe, the one tied to you when you go to a swim, or when you were a child, you should to go to a swim. That Saturnian lobe becomes the xy plane area where probability of finding electron also exists. Now, sir, so these orbitals overlap? Yes, these orbitals definitely overlap. Sir, when they overlap, only then atom can combine to other atom and form a strong covalent bond. Yes. So that means more will be the atomic orbital overlap, stronger will be the bond. Definitely yes. So what type of orbitals you can have? See, as already told you, electron is atomic structure says that electron, in order to know the exact property of electron, you have to consider electron as a wave. And when wave interfere with each other, they can do so in a constructive interference also. They can even interfere in a destructive interference also. For example, electron wave is like the mobile phone signal, because that electron is a moving electron is an electromagnetic radiation. Sometimes when you go to a lift or to a very ground floor, maybe the tower signal is not reaching you. At that point of time, the interference of the wave become destructive, and therefore you cannot listen to what other person is saying, and you say, sir, signal, my friend, signal is not coming. So similarly, when two atoms, their orbital overlap with each other, they may do so in a constructive interference when positive lobes of both the combining atomic orbitals overlap. This will only result to the formation of a chemical bond. If they are having a negative interference, sometimes JEE also asks this. For example, this plus is interfering with this minus, this will not lead to the formation of a covalent bond. So these are the types of negative interferences, negative overlap, when no bond formation take place, and obviously when two lobes are directed away from each other. For example, if this S lobe is trying to form a sigma bond with this PX lobe, sir, there is no overlap area. No. So they also result in formation of no chemical bond. Hence, theoretically, we say they form a zero overlap. Similarly, can two p orbitals also result in a zero overlap? Yes. What molecular axis NCRT recommends us to take? Z-axis to be the molecular axis. So somebody has formed a sigma bond along Z-axis. Okay. If there are unpaired electrons still present, then the electrons will try to overlap laterally. That is called a pi bond. So let's say if this py and this px, sir, let's say this is Z-axis, this is x-axis, this is z, this is x. So this becomes your y-axis. So you tell me, if this hand and this hand, does these lobes are overlapping with each other? No, sir. So px and py also will have no lateral or sideways overlap. So they will also result to a zero overlapping. So whenever you find an atom to be existing in nature as a molecule, it will definitely have a positive overlap. One more important point: when two atomic orbitals are approaching each other in a head-on fashion, I'll just mention them. When they are having a head-on overlap, then such a bond is called a sigma bond. So sigma bond is formed by a head-on overlap, and obviously because the overlapped area is maximum, therefore sigma bond is always strong. Then whom? After formation of sigma bond, first two atoms, if at all they are forming bond, the first bond that they will form, the first overlap which they will result in the formation as a molecule, it will always be a sigma bond. After the formation of sigma bond, if an atom is having unpaired electron, it will try to form a lateral overlapping called the pi bond. So because pi bond is a sidewise, or somebody call it a lateral overlap. So these overlap because the extent of overlapping is weak. Therefore, sigma bond formed between two orbitals is always stronger than the pi bond. Now, what types, talking about the pi bonds, what type of pi overlapping or sideways overlapping you observe? S, because its shape is spherical. So S does not form any pi bond. So who form pi bonds? P. So P overlapping, you can have PP pi bond formation. You can have a P sidewise overlapping with a D. You can have a PD overlap as well. Moreover, you can also have a DD overlap. Now, discussing about the extent by which this pi bond, which pi bond formation is strong, we'll be doing in the later slides. But first, let me tell you about this sigma bond. Sir, sigma bond is strong because extent of overlapped area is small. Pi bond is weak because extent of overlapped area is weak. Yes. So, do we have strength comparison in sigma bond as well? Yes. Just check over here. When a P and P are overlapping, because the extent of overlapping is large because they both are directed towards each other. So extent of PP overlap is largest, followed by SP overlap, and the minimum will be SS overlap. So let me list that also for you, but okay, I'm listing that over here. So extent of, if I'm talking of sigma bond, extent of PP overlap is maximum, followed by SP, and the minimum will be SS because they are hugely directed towards each other, and S, being a sphere, is not directed towards the other sphere. So extent of overlapping will be minimum. Now, such questions are loved by JEE. For example, if I have to compare the strength overlapping, then one thing I've already told you, sigma is always stronger than pi. Second, if you're comparing sigma bond, then PP overlap is the most effective and strongest, followed by SP, and the minimum becomes SS overlapping. So let us do some questions. For example, if you have same value of N1 plus N2, what is N1 plus N2? The combining orbitals that are overlapping with each other. N1 represents the principal quantum number of one orbital. N2 represents the principal quantum number of the other orbital. For example, if I'm having a 2s overlap, again, if I'm having a 2p overlap, or if I'm having a 2p overlap, okay, I'm separating this because first I'm discussing this side, that when N1 plus N2 value is same. Now, because of one atom, what orbital is participating? 2s. Of another, what is participating? 2s. So energy level is 2 and 2. So here N1 plus N2 value is 4. Here also it is 4. Here also it is 4. So sir, this is simple, because in nature, generally what type of atoms combine with each other which are of almost equal energies? In life also, what types of friend you make which have almost the equal or almost equivalent. If your thoughts are equal, you will be friends with each other. Similarly, if your level, the level of thinking represents your energy. So if energy is same, then they will form a perfect covalent bond. Now, so when N1 plus N2 value is same, can you tell me which overlapping will be strongest? Sir, you already told us. So here PP will be strongest, followed by SP, and the minimum overlapped area will be of 2s. Now, discussing this other question, here n plus 2 plus 3 is 5. So principal quantum number, the energy level addition is 5. The energy level addition is 5. So this is again when N1 plus N2 value of 2 overlapped orbitals, which you are supposed to say that who is strong or who is weak. First check the value of N1 plus N2. Now, Sir, this is PP, this is PD. Now you tell me who will have a higher extent. I will give you a picture to just, although you have to learn this in order to be quick in your examination, but I'm just giving you a picture. For example, what will be the, because here, okay, because PP, PP can also have a sigma overlap. So here I have discussed the sigma overlap, which is finished. Now here I'm discussing the pi overlap. Now, in order to understand the pi overlap, let's say this is 2p. Okay, sir. Sir, 3p will be of higher energy. Yes. So this will be 3p. Now you tell me, if you are saying hello to this friend, hello, you must have observed what is the level of overlapping you are making. Just make an observation and I'll give you another picture. Now, if I compare 2p, this is, let's say, 2p, with a 3D is of higher energy, definitely. So what type of D I have to think of, sir? Because they are forming pi bond. So you have to align at least perpendicular to me, I mean parallel to me. So let's say I'm having this, some dxy, dyz or dzx. Although it is more, you tell me, does this orbital is more closer to the p orbital? Yes. You can see, if you have to punch or say hello to your friend, and if your friend is taller to you, the way you will say hello will be, I mean, it will be much lesser because your hands will not go. But if that person, although he's taller, but he is approaching to you, he is approaching at you, closer to you, so obviously I feel you can also have this, just you can also have this feeling that the extent of overlapping will be large. But obviously I want you to always remember this, that when PD and PP overlapping are present, PD overlap is stronger. Similarly, DD overlap will be much stronger if we are talking of the pi bond strength between them. Now, if N1 plus N2 is different, this is a very clear case. How? I'm telling you. You just tell me first, what is the value of N1 plus N2 over here? So 2. Over here, 4. Over here, 3 plus 3 is 6. This is comparison of sigma bond. Now, in the later version, I am comparing pi bonds. Now, what is value of N1 plus N2 over here? 4. Over here, 5. Over here, 6. Now, if N1 plus N2 value is different, you tell me, through quantum theory also you know, N represents the energy level. So, if my energy level is low, I will be listening more to the nucleus. I will be highly localized, and if I'm highly localized, I will be having much effective overlap, either sigma or pi, because I'm not very diffused. So this is a clear point you should have to remember also, that if N1 plus N2 value is different, then the orbital, then the set of orbitals having low value of N1 plus N2 are more stable, because this is basic thermodynamic rule that if energy is low, stability is high. So overlapping stability will also be high. So even if I'm talking for sigma bond, less energized orbital will have more effective overlapping because energy is less, so stability is more. A simple thermodynamic principle. And over here, if I'm talking of pi, extent of pi overlap also, then also I'll say, because N1 plus N2 is low, so stability will be high. Now, but if N1 plus N2 value is same, then you can obviously say that for sigma bond, you will follow that trend. And for pi bond, you will always say that, over here I have written, this is for pi bond. So for pi bond, you will always say that DD overlap extent is highest, followed by DP, and the lowest will be of PP overlap, but I'm talking of sidewise overlapping. Now, sir, do orbitals only have, now Now, okay, d orbital shape I'm discussing over here because I want to give you that picture which I've already discussed to a more larger extent. Now, let's say if this is dz square, then one dz square when approached by another dz square, can you tell me what type of bond they inform? Sir, they are approaching dz square orbitals are approaching each other. When they'll approach each other, they will definitely form a sigma bond. So what type of overlap you will have? 1:1 overlap. Now, sir, if this is dyz or those type of orbitals which lie along the same plane, dxz. So I'm considering, because NCRT considers z axis to be the molecular axis. So this is z axis. Okay, sir. This is z axis. So this is x axis. So what is dxy? When lobes, if that is z axis, this is x axis, then this board is your xz plane. So if you see that xz plane, can you tell me how this dd orbitals are overlapping? Yes, sir. This green is overlapping with that one and this blue is overlapping with this one. So what type of sidewise overlapping you are seeing? Sir, it is a pi overlap. Yes, but what type of pi overlap? Sir, 2:2 overlap, as in two orbitals of this is overlapping with two orbitals of this, obviously. Now, again, coming to dyz, sir, if it is z axis, because molecular axis is always z axis as per NCRT. If this is y axis, so this becomes your yz plane. Now, if 1 dyz, 2 dyz are having a pi overlap, can you tell me what type of overlap it is? Clearly seen. Sir, it is also a 2:2 overlap. Moving ahead. Now, this is the actual reason I'm trying to tell you this. Those pi overlap were 2:2 overlap. But if d orbitals are overlapping with one another along an internuclear axis, let's say that axis is z axis only. But if dx2y2, one dx2y2 is overlapping with another dx2y2, you just check when they are overlapping sidewise also, what type of, how many number of orbitals are taking part in that pi bond formation. Sir, obviously we can see this one, this is one, this blue will be laterally overlapping with that blue, that lobe. This one will be laterally overlapping with this one, and this will be laterally overlapping with this one. Similarly for dxy, because this is z-axis. Now, if this is z-axis and I am talking of dxy, so sir, this is let's say z-axis, this is x-axis, so this will be y-axis. So what plane you will be having for these dxy lobe? This plane. So there will be somewhat like this. Now, if this is overlapping with another dxy, can't you see this overlap? This 2, this 3, and this 4. So that's what I'm telling you. This green will have a 1 overlap. This blue will also have an overlap. This blue will also have an overlap, and this green will also. So what type of overlap in this type of d and d pi sidewise overlapping you are saying? It is 4:4 overlap. Now, sir, but you said sigma is more stable. Yes, definitely. Pi is less stable. But sir, when we were talking of that pi bond, that lateral overlap, it used to be a 2:2 overlap. Two orbitals were overlapping. Sir, but this is 4:4. 4 is much, although pi is weaker than sigma. But when pi bond involves d orbital, and not all d orbitals, those d orbitals which have the capacity to form a 4:4 overlap, then such type of lateral overlap we term as delta bond. So if someone is going to ask you that who is the strongest bond? Sigma bond. Post that, who is the strongest bond? Sir, delta bond. And the least stable will be pi bond, because this involves 4:4 overlap, and pi bond generally involves 2:2 overlap. although sigma involves 1:1 overlap, but here extent of overlapping is much higher. That's why sigma bond becomes always stable, although the overlap is 1:1, but the orbitals are completely emerging into one another. Sidewise overlap are always lateral, less in extent, but if less in extent only, two orbitals are overlapping to a less extent, A4 orbitals are overlapping to a less extent. So 4 is always greater than 2. So delta bond, although delta is not very famous as per JEE mains, but obviously in NEET they have asked a few times. So mains also they can. Moving ahead. So okay, now one question. Let us see if we have done something or not. The number of given orbitals which have electron density. Okay, this is just a question, but see, JEE means just a question. You just have to tell that how many orbitals have their electron lobes along the coordinate axes. So, sir, we already know. Let's say this is x-axis. So, how will you draw px? That along the x-axis. Sir, if it is y-axis, it will be py. If it is z-axis, it will be pz. So 1, 2, 3, their lobes definitely lie along the axis. Now, can you tell me what is dyz? Sir, we have already seen yz electron lobe lie in between the coordinate axis, not along the coordinate axis. So this is not your answer. Dz square, yes sir, because that Saturnian lobe will not lie, but that dz square lobe will lie along the z axis, so it is lying along the axis. So this is also an answer. And dx2 y2 we have already seen, this lies along the coordinate axis. So this simple questions are asked. So what is your answer? 5. Moving ahead. Now, okay. Now, whatever we have learned, let us draw that phool patti again. What we have seen, let us try and predict whether we can say that bond will form or will not be formed. For example, the question is saying, although this is not a question from the because JEE does not ask you to draw, but you can very well understand for example, if question is changing the molecular axis, the question generally does that. For example, what molecular internuclear axis we take? Z axis. Question can also change it. So just giving a brief so that you may also change whenever question is telling you. So let us draw this. Draw the type of orbitals between given when. Okay, the question is saying you have to again consider z axis to be the internuclear axis. Now, sir, if it is z axis, now tell me. Okay, let's say this is z axis. What is shape of S? Sir, it is spherical, all around the chord 3D. Now, if this is dz square, then sir, dz square, this is one lobe like this and another Saturnian lobe. Although I know Saturnian lobe will not do anything, but this can have a effective overlapping with S. So this will definitely give rise to a sigma bond. Bond will be formed. Now, S and dx2i2, let us draw it. S is a sphere. If this is my internuclear axis and question is asking me to have Z as internuclear axis. So if this is internuclear axis, let's say this is X, this is Y. So this will be dxy. So let's say this is X. So this will be Y. Now, what is shape of dx2i2? So dx2i2 is orbitals lying along the coordinate axis, but coordinate axis what? X and Y. So let's say this is X axis and this is Y axis. So this is something like this and something like this. Now, just for the sake of simplicity, because I can definitely see it is like this, another one is like this. So sir, S can never have a pi overlap. S can never have a pi overlap. I have told you and given you that picture over here. S can never result to a pi overlap. Although some people will say, sir, this much at least it is having an overlapped area. No. This is a theoretical thing that you should have to keep in mind, that S always, if you are oriented along my axis only, if you are oriented, I will not just remove this because I wish to give this PPT to you. If this is S and if I am directly encountering an orbital in my axis, then only I'll form a bond, and that bond will always be a sigma bond. S never forms a pi bond. If somebody tricks you by saying it will have some overlap, but that overlap is close to zero, because these atomic orbitals are mathematical justification of quantum theory. So the value, that is the extent of overlapping, that is approximated by this visual figure, is approximately negligible, is nothing. So S can have no pi overlap, so this will result in a zero overlap. So coming to the question, what will be our answer? Sir, our answer will be, because S is overlapping with that dx2y2, or simply you can say this is X, this is dx2y2, so their overlap will be ineffective and they will not result in the formation of any bond. So I'm just writing no bond formation. A very beautiful question for you to understand. Now, similarly, S and D, YZ. So this is, let's say, S. And what can you say about DYZ, sir? This is molecular axis, Z axis. Okay. So if this is Z axis, let's say this is Y axis. So what is the shape of DYZ? Sir, lobes lying in between the coordinate axis. So this is perfect. This is Y, this is Z. You can easily draw it also. There is no artist. For example, here we have to be an artist. So we have done that through that 3D imagination, that this is DXY and this is S. So it will again have a lateral overlap. Here we can easily see this has to be drawn in this YZ plane, and this is S. They'll also have a bit of overlapping, but that bit of overlapping is negligible. So S can never form a pi bond. So here also no bond formation will be taking place. So here also no bond, here also no bond. Now, what about this PZ? Okay, sir, Z is molecular axis. Okay, I'm sorry, taking molecular axis like this. Now, this is PZ. Okay, sir, this is PZ. Now, what about dz square? Sir, one lobe will be lying along z axis. There will be one Saturnian lobe, but we can neglect it because it will not result in any overlap. So this and this will overlap and will result to a formation of very beautiful sigma bond. Why I'm saying beautiful? Because PP, this like P and this is D. It is just like that PP overlap. So although it is a PD overlap, but its extent will be much larger than SD overlap, because extent of overlapped area will be more. So these questions you will only able to decode when you try and make these phool patti, these flower petal pictures in your mind. So moving ahead, now moving forward, let us explore the concept of hybridization. We already know how to calculate the state of hybridization for a central atom. How to do it? We calculate bond pair electrons, the sigma bonds, plus lone pair of electrons, the electrons of the central atom that are remained after bond formation. Summation of bond pair plus lone pair gives you what? Gives you steric number. So if steric number is 2, so hybridization will be sp. If steric number is 3, hybridization is sp2, and so on. This we have already discussed in our previous bonding 1 lecture, and hybridization state we know how to calculate. But my point is, now when discussing the concept of hybridization, why it is needed? Because VBT has already told us that atoms approach each other in order to pair their unpaired electrons. When they are approached to each other, what shape they will acquire? Already told by VSEPR theory, saying lone pair repulsion is highest, so keep them most separated, followed by lone pair bond pair repulsion, and the minimum repulsion will be experienced by bond pair electrons. So sir, shape also we know. Atoms combine with each other and do, we have just recently finished the overlapping. So more effective will be the overlapping, more strong is the bond formed. So why actually we need this hybridization concept? Giving you an example of a very simple molecule, methane. You tell me, what is electronic configuration of carbon? Sir, valence electronic configuration, because valence electrons participate in bonding. Sir, it is 2s2, 2p2. So these 2s electrons and these 2p electrons of carbon needs to get paired. But sir, this 2s electron is already paired. This carbon is approached by how many combining hydrogens? Sir, 4. So carbon need to have how many unpaired electrons? Sir, 4. So this becomes the ground state of carbon. And because carbon is approached by 4 incoming guests, so this carbon will undergo excitation and will reach an excited state, because ultimately this isolated carbon was not stable because it had 2 unpaired electrons. When it is approached by combining atoms, when some other guests are coming to your place, and you will be getting so much happiness out of them when they are approaching you, you will get excited. So sir, how this energy cannot be created nor can be destroyed? So where this energy is coming? Energy of 2s is less, energy of 2p is high. So when atom is exciting itself, it will utilize its internal energy. Whatever money you have in your kitty, you will use that money in order to excite yourself. You will bring some cold drinks, some snacks. You will be spending that extra amount what you have. You won't take a loan, and you will bring stuff to welcome guests at your place. Although you will feel very happy in welcoming them, but you will just reorganize what energy you have, what money you have. You will invest that money to bring some refreshments from the market. Similarly, this, how many incoming atoms are coming? 4. So how many unpaired electrons this carbon needs? 4. So it will undergo an excitation. What electron is getting excited? I guess you can clearly see this 2s electron is getting excited and acquiring a higher 2p subshell, because energy of 2s is less, 2p is higher. Now, sir, so we do not need any concept of hybridization. We have 2 unpaired electrons. Hydrogen, okay sir, let us draw that hydrogen. Hydrogen also has, each hydrogen has an electronic configuration of 1s1. So this 1s electron will try to form a sigma bond with carbon. Sir, one more hydrogen will come. Sir, one more hydrogen will come. One more hydrogen will come. So we do not require any concept of hybridization. We do. When this S is combining with S of hydrogen, this overlapping is an SS overlapping, while the other 3 hydrogens are overlapping with p orbital of carbon. Sir, PS-SP overlapping is more strong, is more effective. So 3 bonds will be stronger and 1 bond will be weaker. We thought this, and we have gone to Mother Nature. We saw the tetrahedral geometry of carbon. We were very happy that, oh, we have done some huge thing. And we assumed through the VBT, what we have studied till date, we started calculating this bond length. For example, let's say this is 1s 2s overlap. So this overlapping is weak. So what we thought is this bond length will be something different and these bond lengths will be same, because these the remaining all three are simple. 1s of hydrogen and 2p of carbon. So we supposed that these 3 will be same and that one will be different. No. Mother Nature has given us a slap and told us that no, all these 4 bond lengths are same. People got crazy. So the theoretical concept of hybridization was given to the scientific community, and we said no, central atom is entertaining combining atoms, so it will undergo modification. It will modify its house so that all the incoming electron will feel the equivalent ground reality. If you have got AC in one room and 3 rooms are having nothing, you are welcoming 4 guests and you need to give respect to all those four guests equally, so you'll not invest extra money. Air condition AC, let's say it is a 50,000 stuff, so you sell that 50,000 AC, and by selling that 50,000 AC you get 40,000 rupees. That's a second hand AC, na? So with that 40,000 rupees you bought 4 coolers. So now you had 4 rooms, one, because 2s is stable, like a stable room, a room with an AC, and 3 rooms don't even any fan and cooler. So you go and sell that AC. Out of those 40,000 rupees, you buy 4 cooler and you fix those 4 coolers in all the 4 rooms, so that when the guests are coming, they will feel that you are giving them an equal platform, equal respect. So the bond lengths will be, I'm just relating with that common sense and giving you a picture also. How many combining atomic orbitals are participating? 4. But they will be modified, they will undergo intermixing, or you can say they will undergo modification, and this modification in chemistry is termed as hybridization. And hybridization will, their hybridized shape will be all of similar energy, similar shape size, everything. Sir, but here one lobe you have made, these are the hybridized orbital. But here one lobe, sir, you have made larger another lobe, because theoretically it was proposed that hybridized orbital has the capacity to form a much stronger overlapped area. So hybridized orbitals forms a much stronger bond, and in order to show that they have much more effective overlapping, electron, what is orbital? The probability of finding electron. So probability of finding electron we have increased in one lobe and significantly neglected and decreased in the other lobe, because in this hybridized orbital, the unpaired electron of the central atom and the unpaired electron of the combining atom will find their maximum occurrence. So probability of finding these pair of electrons will be much larger here, hence reduced. So one lobe we have made higher, we always, when we make hybridized orbital, we make a higher lobe in order to show that they can have an effective overlapping than the combining atomic orbitals. Now, can you tell me, let's say these 4 orbitals are formed, but they are formed by partnership of how many people? By partnership of these 4. So can you tell me what is the percentage of S character in this? Obviously, it is an sp3 hybridized orbital. So these hybridized orbitals are sp3. This is also sp3, 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 sp3. But in this sp3 hybridized orbital, what contribution of S is there? Sir, easy. How many S participating? 1. How many total people have formed this company? 4. So what will be percentage S character? Sir, easy, 25%. So this becomes the S character calculation. We will be using this also. So this is how you know how to calculate S character. Now, sir, what about the shape? Shape will be similar. Now, these hybridized orbital will be oriented in 3-dimensional space in order to have minimum repulsion. Just what VSEPR theory told us. So this will be one hydrogen, another hydrogen, third hydrogen, and fourth hydrogen with a bond angle of 109 degree, 28 minutes. So everything goes just the same. With a just theoretical inclusion that central atom, before overlapping with the combining atom, will undergo intermixing and modification, and that modified orbitals are termed as hybridized orbitals. Now, coming to first, okay, I'll give those theoretical feature to you, but coming to the steric number rule, which we have already discussed in bonding 1, but I'm repeating it again. If steric number is 2, hybridized orbital are 2, so they'll be aligned as per VSEPR theory on a linear geometry with a bond angle of 180 degree. If I need sp hybridized orbital, how many participating atomic orbitals I need? 2. So S and P. It can be any P, X, P, Y, P, Z. I've just taken X because here, if I'm going to a 3D geometry, I'm taking XY plane to be the molecular plane. Now, similarly, if 3 atomic orbitals are undergoing hybridization, steric number will 3. Mind you, again, steric number is bond pair plus lone pair, and while calculation of bond pair, we only account for the sigma bonds, because now we already have seen hybridized orbital have effective overlapping. Sir, pi bond is a weak bond, so pi bonds pi electron we will never give a preference. We will never give a, if somebody is coming to your home, your relatives, friends, relative, Okay, he is coming to your home, you are entertaining them. Will you modify anything? You will not pay any difference whether he has come or not. Or maybe your relative has called you, okay, give one night he'll come to your place from station, something. Will your whole family will undergo modification? No. So because pi bond are weak, so pi electron never occupy, they are not even given that much of preference to take a hybridized orbital. So steric number is calculated as, I'm again writing it, bond pair. But for bond pair, you only have to calculate the sigma bonds formed by the central atom plus lone pair. Lone pair, because lone pair repulsion is higher. So these two electron pair will occupy the hybridized orbital. Now, if steric number is 3, shape will be trigonal planar. Bond angle 120 degree. What all orbitals I'll use? Sir, 3 atomic orbitals you need, because you are saying that you are considering molecular axis as xy plane. So px and py. 3 already discussed. If steric number is 4, so I'll be requiring 1s and 3p. Hybridization will be sp3. Bond angle will be 109 degree 20 minutes. Now, coming to why I'm saying xy plane is the molecular plane. Now, if my steric number is 5, how many hybridized orbital I have? 5. As per VSEPR theory, what shape I'll have? Trigonal bipyramidal. So trigonal xy plane is used. So 1s 3p used. What about D? Sir, I require 5 orbitals. 1s 3p, but I need one more. So what D you will pick? Now that's why I've written this separately. Now, what is your molecular plane? XY plane. How many bonds you are making? Sir, 1 up, 1 down. Trigonal bipyramidal. What all d orbitals have high probability of finding electron along this? Let's say this is xy plane, so this is z axis. So who has that their electron plane along z axis? Are dz square. Moreover, it also has a Saturnian lobe along the xy plane. So probability of finding electron is maximum for dz square along z axis and also on the xy plane. So what dz square will be actually utilized for formation of sp3d hybridized orbital? Dz square. Again, for sp3d2, when steric number is 6, I will obviously take dz square. Sir, why you will take dz square? Because what is octahedral? Positive x, negative x, positive y, negatives are y. The xy plane at 90 degree angle, one again up, one again down. So you will need dz square. But sir, I need one more d. So what is next possible probable d you will be taking into account for hybridization? dx2y2, because their lobes also lie along the coordinate axis of xy. So dx2y2, a very beautiful concept. Now last, steric number 7. Sir, pentagon as in 5 bonds are in one plane, 1 up, 1 down. Sir, up down, again we need dz square, because they are xy plane, so again we'll need x2y2. Now which, I know 3 d orbitals are left, dxy, dyz, dzx. Who has much more probability of finding electron in this xy plane? The dxy. Although the lobes are not oriented along the coordinate axis, but at least they are there in xy plane. So what else d orbital you will use? dxy. A very beautiful concept. And now coming to the theoretical features, because we have already discussed, let us list them. So first thing that I'm saying is the features: number of hybridized orbital forms will be equal to number of participating atomic orbital. If you are modifying 4 rooms, how many rooms will be modified? 4. So obviously combining atoms or combining atomic orbitals will be equal to hybridized atomic orbitals. Hybridized atomic orbitals are equivalent in shape, size, everything. Hybridized orbital form more stable bonds. That's why we only hybridize sigma bond pair electron and pi, and sigma and lone pair, not pi. Hybridized orbital are directed in space. They will acquire space in order to have minimum repulsion as per VSEPR theory. Now, this is a point for which I have taken this theoretical point also, because rest I have discussed, but this is the point I want you to make note also. Relationship between S character and bond length. Now, what is it? Although glimpse of it we have already seen in periodicity, but again listing it out for you. Now, what I'm saying is, let's say this central atom is carbon. So this is an sp hybridized carbon. Who is the famous example of an sp hybridized carbon? Sir, a triple bonded carbon. Okay. So this is a double bonded carbon and this is a single bonded carbon. Now to this carbon, I am only considering first this C bond H bond length. So can you tell me, this is the combining hydrogen atom? I am just asking, as per periodic table, if you'll just think, the distance between nucleus of carbon and hydrogen is called bond length. So all these bond length, let's say this is L1, this C bond H bond length is L2, and this C bond H bond length is L3. Sir, both are carbon. I mean, all three are carbon. Combining with all three hydrogens, bond length must be same. No. We have recently seen how to calculate S character. For an sp hybridized carbon, can you tell me what is percentage of S character? Yes, sir. So you just tell me percentage of S character. Sir, easy. Sir, this is 1 by 2 into 100, that is 50%. This is 1 by 3 into 100, that is 33.33%. And sp3 is already done 1 by 4 into 100, that is 25%. Now you tell me, through our knowledge of atomic structure, penetration of S subshell, penetration of S orbital is more closer to the nucleus. What does nucleus want? Nucleus is a plus, a huge plus. It wants to attract all the minuses around it. Sir, attracting minus is termed as electronegativity. So this carbon, the carbon we know through our periodic table, the carbon with electronegativity of 2.5 is this sp3 hybridized carbon of an alkane. While the alkyne carbon has more percentage S character, so it will be more electronegative. A more electronegative species will snatch the bond pair of electron more towards itself, thereby resulting in the shortening of this bond length. So as depicted here, sp hybridized orbital becomes smaller in length. This L1 is less, followed by sp2, because S character is here, S character is more, electronegativity more, so I will be attracting those hydrogen bond electron towards myself, thereby resulting in shortening of bond length. And the largest bond length will be of sp3 hybridized carbon with hydrogen. So although nucleuses are same, but because of S character, the formed hybridized orbital will have a different bond length. So summing it up for you, a very important conclusion: more be the electronegativity, more be the S character. So as S character increases, electronegativity increases, and as S character increases, bond length, as S character increases, bond length decreases. Actually, this is the point I wish you to always keep in your mind. We will be doing some more discussions of such application. Moving ahead. Now, sir, hybridization we have done. Okay, let us do some basic examples of hybridization also. So coming to, although we know how to calculate state of hybridization, but just I'm trying to give you some few examples and picture. Can you tell me, explain this sp hybridization BeCl2? Definitely, sir. Sir, beryllium, how many electrons in its valence shell? 2. How many bonds? 2. This is Cl, this is Cl. What will be its hybridization? Sir, bond pair is 2. Lone pair on beryllium is 0. So steric number is 2. So hybridization is sp hybridized because steric number is 2. Sir, why telling this? Just telling you this in order to tell you the orbital picture. That's it. Orbital picture photo I have beautifully already taken, because I'll not be making that full patti, that flower petal, because you just need to understand, you do not have to be an artist, you have to be an engineer. Now, engineer is by the way an artist, but you should not be an hand artist. You should be a brain and analytic artist. Now, so sir, okay, sir, tell us first, beryllium, it has electronic configuration of 2s2. This is ground state. So will beryllium can form bonds in its ground state? No. So excitation required because I need to have unpaired electrons. So this 2s electron will get excited to 2p. 1 1. So this becomes your excited state. Now, who is approaching you? It's a chlorine. Okay. Writing that chlorine. So this chlorine has 3s2 3p5. Okay. How many unpaired electron this combining chlorine has? Sir, only one. Which one? Sir, this one. So chlorine wants to pair this unpaired electron present in 3p subshell of chlorine. It will approach beryllium, and when approached, beryllium will modify itself. How many orbitals beryllium will take part in hybridization? 2. So how many orbitals will be formed? 2, but those will be sp hybridized orbital. Shape will be linear. So can you tell me, if this is beryllium, this orange portion, the central atom is beryllium, this is beryllium. So can you just give me a picture that if this is beryllium, what this orange lobe represents, or this represents sp hybridized orbital of beryllium. What does this orange lobe represent, sir? This also represents sp hybridized atomic orbital of beryllium. Now, what does this green, sir? Combining atom, the atom that is coming will not, it is a simple 3p orbital. What is shape of p? Sir, dumbbell. So what is this? This is nothing but 3p unhybridized orbital of combining atom. Do not the guest that is coming to your place, why he will modify his home. So this is 3p orbital of chlorine. This unpaired electron and this unpaired electron gets paired. Work done. This is also 3p orbital of combining chlorine. Sir, what is this blue and yellow orbital? Let's say this is x-axis. Let's say this molecular axis is x-axis. Let's say this molecular axis is x-axis. So this becomes your py, 2py, and this becomes your 2pz. Why they are not involved? Because they are empty. This is xp. Let's say px is used. This is 2py, empty, 2pz, empty, but still showing you those empty orbitals in order to tell you when they are used. So giving you another example. First, let us check how we calculate hybridization state quickly. C double bond O, C double bond O. This we already know. What is its shape through VSEPR theory? Linear. Why? Because bond pair is 2, because we only calculate sigma bond. Lone pair on carbon is 0. So steric number is 2. So hybridization is sp. We first calculate hybridization state like this only and predict shape as per VSEPR theory. Now, if I'm asking you that you tell me what type of pi bonds carbon is making. Okay, let us do it. Now, the combining atom, the central atom is carbon. Electronic configuration, valence shell, 2s2, 2p2, done sir, too many times. 2s, 2p. Now this is ground state. Now, how many bonds carbon has to form? 4. So how many unpaired electrons carbon need? 4. So excite it. So this 2s electron of carbon, in order to entertain those combining oxygen atom, what I'll do is I'll try to excite this. Reach over here. So how many unpaired electrons I have now? 4. Now, who is coming to my home? Sir, oxygen. Let us draw that oxygen. 2s2, 2p4. So this is 2s and this is 2p. How many electrons of oxygen needs pairing? So 2 electrons of 2p. Fine. So one will form a sigma bond. Obviously, first bond formed between two atoms is a sigma bond. So because now, what is the hybridization of this carbon? Sir, sp. So how many atomic orbitals you will utilize for getting hybridized to? So 2 sp hybridized orbitals are formed. Bingo. But there are another 2p unhybridized orbital. Let's say if this is px, this will be py, so this is 2p, this is 2py, this is 2pz. They both have now one unpaired electrons. But first, what formation will take place? The sigma bond. So this one sp hybridized orbital of carbon will form a sigma bond with one 2p of oxygen. So what is this green lobe? This green lobe is 2p orbital of 2p atomic orbital of oxygen. Because this is CO2, so one oxygen will be this. Let's say this is oxygen 1. So this is of oxygen 1. And this is oxygen number 2. So what is this, sir? This is 2p orbital of oxygen 2. So these two sigma bonds are formed. These two sigma bonds are formed. These two sigma bonds are formed. Now, let's say these are sigma bonds, then I have to predict two pi bonds also. How? Sir, both oxygen have one, so one unpaired electrons more. So this 2p electron, sir, where it is present? In this orange lobe. Sir, this will combine with whom? This will combine with carbon. Also has two, py and pz. So let us focus on this carbon. With what is this orange? This orange is sp hybridized orbital, because hybridized orbital forms the sigma bond. So let me write that hybridized orbital again for you. So what are these? These two are sp hybridized orbital of the carbon. But because carbon still has got unpaired electrons, let's say this is x-axis. Let's say this is x-axis. So this becomes your y-axis. So this will be 2py of carbon having this unpaired electron. Now, because this is py, so it will overlap with the 2py of oxygen. So this will be 2py of oxygen. But they will have a less effective overlapping. What will be that less effective overlapping? It will be a pi bond, lateral overlap. So this is x-axis, y-axis 2py, and then z-axis, these 2pz, this 2pz and this 2pz. Because carbon 2px is used for hybridization, 2py having one lone pair, 2pz, the yellow one, having the another, not lone pair, the unpaired electron in the forming the pi bond. So this is 2py and the yellow one will be 2pz. So this 2pz will be doing a lateral overlapping with this 2pz of oxygen. So just telling you this picture so that for ABCD type of questions, sometimes, for JEE mains, sometimes you are asked such questions, but I'm giving you just this picture so that the whole inorganic chemistry of yours becomes very quite stable. Moving ahead now. Again, some discussion of sp2. Now we'll be quick in discussion because we have already seen a few examples. So, but for organic chemistry also we'll be requiring this. So, sir, carbon as in C double bond C. Now through VSEPR theory, we definitely know this is C2H4. How many sigma bonds this carbon is forming? 3. So bond pair is 3, lone pair is 0. So steric number is 3. So hybridization is sp2. This carbon also is sp2 hybridized. So this sigma, and this sigma. First I'm showing you these 3 sigma bonds. This 1 sigma, 2 sigma, and this sigma. This sigma is between sp2 hybridized of one carbon. So what is this? So this green one is also the another carbon. So this is also sigma, sigma, sigma. So these are the similar sigma formed by the sp2 hybridized orbital of carbon 1, and this is sp2 hybridized orbital of carbon 2. Now, why I'm drawing this is because the geometry will be trigonal planar. So let's say this is a carbon, 1 hydrogen, 2 hydrogen, and 1 carbon. So it is forming a triangle, 1, 2, 3. The other one is also forming a triangle, one with this carbon, 1 hydrogen like this, 1 hydrogen like this. Now this whole molecule will be a planar molecule. But apart from this planar molecule, this carbon also is left with one unpaired electron. I'll just color it with this different green color. So what can you say, sir? If it is pxy plane, then pz will be remaining. So this pz of one carbon, this pz of one carbon, and this 2pz of another carbon will have a lateral overlapping. So what I'm trying to tell you over here is, let me give you another picture for this, that if this is a carbon forming a sigma bond, and sigma bond. So these three sigma bonds are sigma bonds formed by the hybridized orbital. What can you say about the other carbons? A similar picture. So all these constituents will lie on a plane. So the whole molecule is planar. Let's say this planar molecule I have over here. Let's say this planar molecule I have over here. Now, this carbon has one 2pz containing the unpaired electron. Let me make that 2pz for you. This is the 2pz containing that odd electron, the unpaired electron. 2pz of another carbon containing that odd electron. So this pi cloud will have a sidewise overlapping and will be giving this pi bond to you. But can you tell me, for the nodal plane, what is a nodal plane where probability of finding electron is 0? What electron? Pi electron. So nodal plane for pi bonds will be the molecular plane. The molecule which has been formed in this plane will act as a nodal plane because pi cloud is not lying on this plane. So this is also an actual JEE question. So these theoretical questions also you have to keep in mind, and that's why I'm discussing these few examples of hybridization as well. Although through VSEPR theory we already know them. So again, for SP, says this is also same. So C triple bond C, this H, this H. So this is linear. So this is a sigma, this is a sigma, this is a sigma. This is a sigma, this is a sigma, and this is a sigma formed between sp hybridized orbital of carbon. Why sp hybridized? Because each carbon is forming two sigma bonds, no lone pair, so it is also sp, it is also sp. But now here, how many pi bonds we have? 2. So let's say sigma bond is forming along x-axis, so one will be 2py forming this pi bond, or yellow one. Then this blue one will be pz, this blue one will be pz forming this sidewise overlap. So how many pi bonds? 2 pi bonds. More be the bond order, lesser will be the bond length. So C triple bond C will have shorter bond length, C double bond C will have larger, and C bond C will have much larger bond length. Moving ahead. Now these examples I have given you the picture. Boron, the central atom, sp2 hybridized. This is the 3p orbital of combining chlorine, or 2p orbital of combining fluorine, giving you a 120-degree angle, that is trigonal planar arrangement of an sp2 hybridized bf3. Now last thing for hybridization's concept as such. I mean, hybridization is finished, but sometimes some questions are also framed around it. How? I'll tell you. For example, if a question is asking you, you tell me, okay, pi bond are there in a compound. You tell me what type of pi bond it is and how many pi bonds of that type are there. For example, the CO2 which we have recently done, this CO2 molecule, as we know, this is sp hybridized carbon. So 2s and 2p, carbon will excite itself having, this is of carbon, an excited state. These two will participate and forms 2 sp hybridized orbital, and these two are remaining to form pi bonds. They will combine with whom? They will combine with oxygen. Oxygen with electronic configuration of 2s2, 2p4. So 2s is all paired, oxygen happy. But these 2p are not paired. One will form a sigma bond. Obviously, one oxygen will form a sigma bond. So let's say this forms a sigma bond. What about this? This is 2p, maybe x, y, z, whatever. 2p of oxygen will form a pi bond with 2p of carbon. Similarly, 2p of another oxygen will form a pi bond with 2p of carbon. So what are these pi bond? This is a 2p this is a 2p. So 2p of carbon is used, and for oxygen, sir, again 2p used. So if somebody is asking you what type of pi bonds are present in CO2 molecule, so you say it's a p pi bond. And how many p pi bonds are present? 2. So can you just do the same thing for SO3 for me? Can you tell me what type of pi bonds SO3 has and how many? Again, obviously, sir. Doing the basic again. What is SO3? S double bond O, double bond O, double bond O. What is valence electronic configuration of sulfur? So 3s2, 3p4 because it is oxygen family. How many unpaired electrons I need? Sulfur is forming 6 bonds, sir. 3 sigma and 3 pi. So you require 6 unpaired electrons. So I have to excite myself. So I'm directly giving you the excited state. 3s and 3p. Sir, why you have not drawn? Because I'm exciting. So using different color. This 3s electron will get excited to 3d. This 3p fourth electron will again get excited to 3d. So you have 6 unpaired electrons. Who is the combining atom that is coming to sulfur's house? Sir, oxygen. Electronic configuration 2s2, 2p4. One bond, one unpaired electron has formed a sigma bond. Let's say this has formed a sigma bond because 2 are unpaired for oxygen. This has formed a sigma bond. Your job is done. Now, what electron of oxygen is participating in pi bond formation? Sir, 2p electron. So for oxygen, let's say I have 3 sigma bonds. The white one is sigma bond. The pink one is the pi bond. In order to form pi bond, oxygen always uses 2p electron. That I can see, this one. But what electron sulfur is using? That will give you the type of pi bond. Okay, so going to sulfur again. Sir, hybridization, because there are 3 bond pairs, so hybridization will be sp2. So the 3 orbitals will be utilized to form 3 sp2 hybridized orbital. Sir, sulfur has 1 odd electron in 3p. And sulfur has 2 more odd electrons, unpaired electrons, but in 3d. So for sulfur, this 1 3p will be used. Okay, I'm sorry. In the red pink one, I have to do it. So 1 3p is used while the other 3d is used. So if question is asking you what type of pi bond, so here p pi bond is there, but one. Which one? P pi, 3p and 2p. And p pi d pi bonds are 2 in number because this 3d and 2p are sidewise overlapping to give rise to this pi bond, a very important and beautiful concept. Now, similarly, you can do for SO2 and ClO4 minus also. You can clearly find the number of bonds. I've given you this example, but that will be your homework so that I can move ahead. If you find any doubt, you can always give a comment on the comment section. Now, coming to this slightly stronger topic. So I am giving a caution for those who are starting it just from zero and watching this chemical bonding lecture. You should skip this 3-4 slides, but for all, because I promised that I will be including every S block, P block details also, and that is the reason I have segregated bonding 1 and bonding 2, because I do not wish to miss these very important but more or less a step higher than mains. So talking about the hybridization in species having odd electrons. Now, if a species is in possession of an odd electron, then technically what that species should do. Hugely loved by NCERT, that you should know also, that if I am a molecule and I have unpaired electron and odd electron in my electronic configuration, then generally I prefer to be exist in nature as a dimer. For example, species have odd electrons like NO2. If you draw the Lewis structure of NO2, what you'll find? Sir, there is an odd electron. So this odd electron of 1 NO2 will try to get bonded with another odd electron of another NO2, and this NO2 will prefer to exist in nature in form of a dimer N2O4. Ultimately, goal is end result is done. I want to get stabilized. Therefore, two nitrogens have bonded their unpaired electrons and existing as a dimer. Similarly, this methane in organic chemistry, you will see in reaction mechanism also, when there is a odd electron, this is called a free radical. So free radical created in Wood's reaction also, this also exists as R bond R higher alkanes, so it will form ethane. Similarly, this CF3 will also form a dimer C2F6. This ClO3 in nature, it also, because of the presence of this odd electron, it will also exist as Cl2O6. So generally, this is not, I mean, this is a very basic thing which you should know, that when odd electron is present in a species, it generally exists as a dimer. But and for these species hybridization, what we have done is, we know all those hybridizations, but there are certain species in nature which have got odd electron, but these odd electron species form odd electron bond. For example, this NO, you can very well see it has an odd electron, but in nature, this NO, although somebody grabs your neck, then sometimes it also forms a dimer, but a very weak dimer. These dimers are very strong, but this dimer is very weak. ClO2 also has odd electron. O2 minus also has odd electron, but these species, in fact, these two, they never exist as dimer. They remain in nature as odd electron species. But sir, if they are odd electron species, then they are violating what we have studied, VBT. That is, sir, you said all atoms exist in form of molecule to pair their unpaired electrons. Now, in order to stabilize themselves, they do not. Why they do not dimerize? They do not dimerize because they have an ability to form odd electron bond. Normally, what a bond is? Normally, if we see a bond, it is a, let me draw a normal bond for you. So a normal bond is basically, let's say A is bonding with B, so it is a two-centered two-electron bond. For example, two atoms, two nucleus, two centers forming a two-centered two-electron bond. This is the normal bond that we know. But in nature, sometimes it is observed that some species like these three, the famous species, they are odd electron species, but how they stabilize themselves, they do not wish to form dimer. They stabilize themselves by making an odd electron bond. I'll show you what it is. See, this chlorine is having one odd electron. This oxygen is having lone pair of electrons. Now, can you think of a possibility? For example, this double bond O is always existing. This single bond O is always also, although the single bond is coordinated, so this is always existing. But now, if I'm drawing these three electrons are participated, and between these two nucleus, these three bonded electrons, they start coming under influence of both the nucleuses, hence attaining stability. So if their energy is reduced, although it is an odd electron bond, but such odd electron bonds, instead of having an odd electron pair, such species find application in nature that they exist as a odd electron bonded molecule. Now, coming to another example, this O2 minus, this is a single electron, this is a double bonded, this is a lone pair in this O minus. So again, this single bond is always existing, but they also forms a 3 electron shared between two atoms. Like, I'm giving you another example, this odd electron bond. For example, if I have to identify the formation of, in nature, H2 plus is also known to be existing. How? This hydrogen, if it was H2 one hydrogen was having one electron, another hydrogen was having one electron, and they were supposed to form a simple two-centered two-electron bond. If I remove one electron, it will be a H2 plus, and the single electron will find its occurrence in influence of these two nucleuses. So two nucleus but sharing one L. So this is also a odd electron bond because number of electrons participated is 1. This is also an green one is odd electron bond because number of electrons participated are 3. So these are some famous examples where the species do not dimerize and in fact exist as a odd electron bonded molecule. Now if you grab someone's neck and asks what can you say about NO, actually NO also forms this odd electron bond. These two bonds are already there. The unpaired electron of this nitrogen, the odd electron of this nitrogen, and one of the lone pair. I'm using another color. This green odd electron and this lone pair, they also forms a odd electron bond also. But yes, sometimes in nature their dimer is also known to be existing because this order, this is through electronegativity you can check this is minus, this is plus, this is minus, this is plus. So a resonance, this odd electron can stay in resonance between these two nucleuses. So a dimer, but a weak dimer of NO is found in nature. Although for other species they always exist in form of dimer. So that's why I'm saying it forms it can exist as a weak dimer, but it can also exist as a odd electron bonded molecule. Now why I'm discussing this, first let me help you with the bond order calculation, and then what your competition loves is they ask their hybridization. So first let us understand their bond order first. Now just one point that you should have to keep in your mind, because it's a statistical fact, that whenever odd electron is present between two nucleus, it can be one electron, still an odd electron, it can be 3 electrons, still an odd electron between two nucleuses. So the bond order for such bonds are always considered as 0.5. That statistical thing you have to remember. That's why I said those who are starting from 0, you can skip these slides, but those who are listening to me, odd electron bonds, for them statistically you always give them a contribution, a bond order of 0.5. Now if you know that now, and we are supposed to tell the bond order of NO. Now I have told you NO, somebody snatches your neck, then you'll say it form a dimer, but a weak dimer. Otherwise those 3 examples, NO, O2 minus and ClO2, always exist as a odd electron bonded species, not dimers. So if we know that it is also not forming a dimer, and we are asked that I have to calculate bond order of N bond O, then definitely sir I can see bond order 2. But now I know it will also form a odd electron bond. This already I made it. One using odd electron of nitrogen and using one lone pair on oxygen. So this is a odd electron bond. So can you tell me what is the bond order? Yes, very easily. So bond order will be equal to this 2 plus 0.5 contribution of the odd electron bond. So the bond order of NO will be 2.5. Now this will either be validated when we'll study our molecular orbital theory. We'll again check that through MOT also they say bond order of NO is 2.5. Now coming to O2 minus, sir, bond order 1 we can see, and this odd electron bond will have a contribution of 0.5. So bond order of CO will be equal to 1.5. Now if you know if you can calculate for these two, can you help me with bond order of ClO2? Definitely sir, it's a double bond O, it's a coordinate bond O, but there is a odd electron bond also. Now it can do, so this can be double, so this can also be double, because whenever pi electrons are there, resonance can come into effect. So I have drawn those resonating structures also for you. Now if you calculate bond order of Cl and oxygen, both are CN and oxygen, what is the rule for calculating bond order of a resonating structure of a resonating species? You concentrate on one of the side. Let's say this. So what is bond order over here? So 1, because this coordinate bond, and this contribution is 0.5. So here its bond order is 1.5. So number of bond orders of that particular bond in on all the resonating structures. So here it is 1.5, and in the second resonating structure this bond order is 2, divided by number of resonating structures are 2. So this is 3.5 by 2, as in 1. This is 3.5 na. So 3. Okay, 1.75, right? Just check. 3 by 2 is 1.5, so 0.25 will be more, 1.75. So the bond order of Cl bond O is 1.75. Now the most important thing, hybridization. I'm giving you a trick also. For hybridization, if you have to calculate hybridization of a species containing odd electron, then generally what we know through our concept of hybridization, the basic concept of hybridization, what we know, we give hybridized orbitals to sigma bonded electrons and lone pair of electrons. Now, a single electron, generally, if 2 electrons are termed as lone pair, then those 2 electrons are of such huge importance that we provide them a hybridized orbital. But obviously to a single electron, the level of repulsion will be not much higher. So generally the odd electron is not preferred to be taking or to be accommodating into a hybridized orbital. But you can also think of a common sense that in hybridization only we have learned that what orbitals undergo intermixing to form hybridized orbital, those who are of lesser energy. So if energy of the central atom containing the odd electron is less, then you may offer, because its energy is less, so you may also use that orbital to undergo intermixing, because that orbital is still very stable. Now, sir, how can we check the energy of that orbital having that odd electron? By the electronegativity difference. Now, that's what I've made the two cases for. When central atom is more electronegative than the combining atom. For example, if I have to predict that what is the hybridization of this carbon having this odd electron, this CH3 radical, what will be its hybridization? Now, carbon is combining with hydrogen. Who is more electronegative? Sir, carbon. So this minus and this minus will make, if this minus is also concentrating on this odd electron, then these two minuses will repel each other and will increase the energy of the unhybridized orbital. Because energies increase, so will you offer that high energized orbital to participate in bonding? Sir, we only invite those orbitals for intermixing which are of equal energy. If your energy is increased, you go to hell. We will not offer you to participate in hybridization, and that's why I already told you, generally when odd electron is there, we do not include that orbital for hybridization. So the shape of the CH3, the hybridization will be again sp2, because there are 3 sigma bonds, no lone pair, because odd electron we do not count generally, and shape of the carbon, of this carbon radical, carbon with the odd electron is also termed as carbon radical, will be trigonal planar. But case 2, when this carbon is bonded with fluorine, now who is more electronegative? Fluorine. Fluorine has withdrawn all the electron density, yes sir. So carbon has become relatively partially positive. So this plus and this minus, now they will attract each other. Now this orbital energy is not very high because carbon is deficient of electron. So because its energy is reduced, therefore now it will be offered that, my friend, you also come with us, let us undergo hybridization, let us undergo modification, because you are of equal energized orbital. Equally energized orbital undergo hybridization, undergo modifications. So When we talk of CF3 radical, at that point of time we say this odd electron is present in an sp3 hybridized orbital, because when we have done spectroscopy, we found that this CH3 radical is not trigonal planar. It is trigonal pyramidal. That means the hybridization of this carbon is sp3. That means this orbital is also involved in hybridization, and therefore here I have drawn both the lobes and located the orbital of odd electron, which is unhybridized pure 2p orbital of carbon. But here odd electron stays with the sp3 hybridized orbital of carbon, because that unhybridized orbital is offered to be participating in formation of a hybridized orbital. Now, for these two questions, you tell me the hybridization of nitrogen and chlorine in these two species, and obviously if at all they contain an odd electron, then you tell me in which orbital, in which type of orbital that odd electron is present. So sir, it is very simple. NO2, sir, is very simple. You already told us that NO2 exists as a dimer, because in order to stabilize, generally what species do is this odd electron that is present in NO2 is definitely utilized for bond formation. So this nitrogen will treat this odd electron as a bonding electron with another dimer that it is going to form. So it is obviously having 3 sigma bonds. This lone pair is utilized for sigma bond formation, so there is no lone pair, so steric number becomes 3 and hybridization becomes sp2. So where this odd electron is supposed to be present in, it is supposed to be present in an sp2 hybridized orbital, because I said for odd electron containing species which forms a dimer, that their hybridization is very simple. You just consider them to be forming a covalent bond with another species of their type containing that odd electron, hence their hybridization status, definitely with the steric number rule which we know. Now, ClO2, the one that is left. Now, if somebody asks you what is the hybridization of this chlorine and the place where that odd electron is present, now this is, I mean, you can definitely predict, but it is a good common sense. Now, since we already know the structure and we know that this also, that the lone pair on oxygen and the odd electron on chlorine will form the odd electron bond. Done that, drawn the bond order also. But first, if I'm asking you that what is the hybridization state of this chlorine, sir, it is also very evident. This is one sigma bond, this is another sigma bond, and this is lone pair. So steric number becomes, bond pair is 1, 1 plus 1 is 2, plus lone pair is 1, so steric number is 3, so hybridization will be simply sp2. Now, the position of this odd electron will be, let us check. Chlorine has an electronic configuration of, valence electronic configuration of 3s2, 3p5. So these 3s electrons are paired, these 3p electrons, 2 of them are paired. How many hybridized orbitals we need? Sir, 3. How many bonds chlorine is forming, sir? This sigma, this pi, this is coordinated, so definitely because forming a sigma bond, so this will also be requiring a hybridized orbital, and this is also a lone pair requiring hybridized orbital. So how many electrons you need, sir? Unpaired electrons I will be requiring this 1, this 2, and this odd electron 3. So 3 unpaired electrons I require. So what is that ground state? It is containing only 1 sigma electrons, 1 unpaired electrons. So I have to get to the, from ground state, I have to excite this species. This is 3s, this is 3p. We very well know excitation to 3d is possible because chlorine has vacant d. How many unpaired electrons you need? Sir, we need only 3 unpaired electrons. So who will only undergo excitation? Sir, this electron. Okay. Then this will be coming over here, and the remaining I'm using the same color. This is a pair, this is a pair, this is a single electron, this is a single electron, and this pink electron has gone to 3D. Now, how many orbitals are involved in hybridization? Sir, 3. So these 3 have formed sp2 hybridized orbital. Perfect. This is presence. One will be acquired by lone pair, one will be doing the coordinate bond, and this will also be making a sigma bond. See, sigma, 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 a coordinate bond and a lone pair. Okay, sigma, let's say this is sigma, this is lone pair, and this is coordinate bond. Done. The 3 hybridized orbitals are utilized. Now, the 2 pi electrons, one is 3p and one is 3d. Now you tell me, because I have one I have represented white and one I'm representing as pink. So I'm saying this is the white electron that is making pi bond, and this is the pink electron that is contributed in and taken as an odd electron. Why? Because for bond order calculation, if you remember this bond order formation, if someone asks you what is bond order, you will also calculate this pi, and to this bond order you will also regard as 1. But for bond order of a odd electron species, we have statistically recently seen it is 0.5. So that odd electron would be this pink colored 3D electron. Moreover, why we are saying it is not getting hybridized? Because we have drawn the resonating structures. You can very well draw the 2 resonating structures like we have drawn over here. The 2 resonating structures of this ClO2. So what electrons undergo delocalization? Non-sigma electron, that is pi electrons. So this will definitely be a pi electron, because some people even say, sir, you said when central atom is electropositive, include the odd electron in hybridization. Because then people will say this is an exception. No, this is not an exception. Although the rule that I have told you, when central atom is relatively electropositive than the combining atom, the odd electron occupies the hybridized orbital. But if at all it is occupying an hybridized orbital, then it cannot undergo delocalization. So how come it is giving rise to resonating structures? So because it is giving rise to resonating structures, point number 1, therefore it has to be a delocalized pi electron, and therefore it will not be given a hybridized orbital. And because it is occupied, and moreover I'm coupling up with the fact that it is a 3D electron, energy of 3D is high. So to which orbital do you offer hybridization? Is like forming a company or forming a group in which people can play together. So who all people you offer in your group to play and intermix, which are of similar energy, which are of similar thoughts, which are of similar principles, which are of similar nature. If one is of higher energy orbitals do not undergo intermixing, as I've already told you. So this has to be a 3D orbital where this odd electron finds its place, because it is not even offered to undergo hybridization, because it is undergoing delocalization also, because it is undergoing resonance also. So a very beautiful fact you should keep in mind. Moving ahead. So moving to another topic of Bend's rule, not mentioned in chemical bonding, but a very important part of the block chemistry, the P and D block element chemistry. So taking and considering that these Bend rule, students get confused a lot in this also. I will try to make it very simple for you. Now what does Bend rule say? Sir, we studied hybridization. So after studying hybridization, what myth generally come to students' mind is that in every hybridized orbital, the percentage of S and P character is always equal. No. Actually, hybridization is a rule which says that intermixing takes place. After intermixing, whatever partners, whatever new orbitals have been developed, generally when combining atoms, every atmosphere is same, then they all have equal SNP, the percentage SNP character that we have calculated. Generally it is all equal, but not always. Sir, then there is an exception. No, that's why I'm saying I'll keep it simple. For example, Let us assume the molecule of inert gas XeO2F2. How can you predict its shape, sir? It is very simple. Through chemical bonding, we know. What do you know, my friends? Sir, we know here bond pair is 4 because 4 species are coming in. Now, oxygen requires how many electrons? 2. So 2 oxygen will require 4. Fluorine requires 1, so 2 will require 2. 4 plus 2 is 6. So how many lone pair of xenon is left? 1. So what is steric number? Sir, steric number is 5. So what will be hybridization? Sir, it will be simple sp3d. So this much we know, already done. Sir, if it is sp3d hybridized, what geometry you will think of by making its structure? Sir, trigonal bipyramidal. But in trigonal bipyramidal, what is the position which lone pair occupies? Sir, equatorial, because it offers minimum repulsion. So lone pair always occupy equatorial position. Done, sir. Now I have two axial positions, two equatorial position and two axial positions. Now which position who will acquire? Now I'm giving you very basic. Sir, oxygen forms double bond. Bond order is more, so bond length will be less. So which is the smallest length in trigonal bipyramidal? Sir, equatorial. So this common sense will only tell you that oxygen will be coming over here. That means they will be forming a triangular plane, and trigonal bipyramidal is the structure geometry of AB5. So these two fluorines will be coming over here. So even if you do not know this bend rule, with common sense of VSEPR theory and whatever we have studied, we can easily predict this structure. What is the shape? The seesaw shape. But for calculation of bond length of some good questions, some block chemistry questions, you need to know this bend rule. So what I'm extracting with this, we have made through common sense. Now through this common sense, I'm extracting some conclusion for you. What is the conclusion? And this conclusion you have to remember and keep in your mind for other block chemistry questions which you'll be doing abhi. Now, first conclusion. Lone pair is coming to what position? First of all, you tell me what is the hybridization, sir? sp3d. Now, Bent rule says the hybridization, the percentage of S and P character in all hybridized orbital is not same. First point number one. Sir, so who has what character? So let us remember one thing which we have studied when we were discussing electronegativity also, and in previous slide also, in case of alkane, alkene and alkyne. Through that we always remember, sir, percentage S character of alkyne was highest. So if percentage S character is highest, the hybridized orbital has small length. So this conclusion that percentage S character as increases of any orbital, bond length decreases. This conclusion which we have drawn also, we are writing also. So this conclusion you will keep in your mind in order to signify and compare bond lengths for few questions. Now, percentage S character is more, bond length is less because they are inversely proportional. Or else, if this decreases, bond length increases. Now, electronegativity, electronegative atom. Now, who is electronegative among oxygen and fluorine? So, fluorine. Fluorine, you tell me, has acquired what position? So, fluorine has acquired axial position. Now, you tell me for the trigonal bipyramidal species, the axial position are the axial electron cloud is more significantly oriented by what lobes, what orbitals? Sir, pz and dz square, because if this hybridization is sp3d, then you tell me which orbitals are more oriented along z-axis, because this is xy plane. Let us say this is xy plane, so they are oriented along z-axis. So sir, this will be contributed by pz and it will be contributed by dz square. So these orbitals definitely will have less of S character, is what I am trying to tell you. And the conclusion which I want you to make is, because electronegative atom is occupying axial position, so definitely electronegative atom is itself electronegative. If someone has more of s character, if some orbital has more of s character, that orbital will also be electronegative. So if I am electronegative, I want electron. So how will I give that electron to you? So electronegative atom hates s character. So wherever electronegative atom has come, actually the s character in that particular set of hybridized orbital will be less. So that is what I have written also, which is again a conclusion of Bend's rule, which says a more electronegative atom prefers to occupy that hybrid orbital which has smaller percentage of s character. So what I want you to remember is, because axial bond length is more generally, bond length more, so percentage s character will be less, and percentage s character will be less, that means electronegativity is less. If electronegativity is less, then electronegative atom will occupy that position, because electronegative atom will hate s character, will hate you to be electronegative. So this conclusion, electronegative atom hates s character. Now if I am asking you where lone pair is going, sir, so lone pair always go to equatorial position. Equatorial position has a bond angle of 120 degree. Equatorial position has smaller bond length. So lone pair is going to that position where electronegativity, because bond length is less, so percentage s character, or in other words, electronegativity is high. Because electronegativity is high, as in it will have more influence of the nucleus, so lone pair will try to be closer to the nucleus. So what I'm trying to tell you is, you have to learn this conclusion that lone pair loves s character, electronegative atom hates s character, and as s character increases, bond length decreases, and vice versa. Now sir, why you are telling us this? How can we use this? Now the structures, the two structures I'm asking you, what is the structure of PCl3F2? Now with this knowledge which we have shared just now, it is very easy for you now. Sir, we very well know it has 3 equatorial positions and got 2 axial positions. Now obviously this molecule PCl2F3 will also have these 5 positions. So can you tell me who will go? Sir, electronegative atom, as in who is electronegative? Fluorine. Fluorine will occupy that position which is having less s character. Who is having less s character? Who is having larger bond length? Who is having larger bond length? Sir, axial positions. So how many axial positions you have? 2. So 2 fluorine will definitely fit over here. How many fluorine are there? 3. So all 3 will want to come to the axial position, but only 2 axial positions are present, so 2 fluorine will be coming here. So fluorine will definitely occupy that position which is having less s character, because axial position is higher in bond length, higher be the bond length, lesser will be the s character. Now what about the other fluorine? Now it has to go to equatorial position because it does not have any option. And what about the chlorines? Whatever space that is left. What about chlorine? Whatever space that is left. Now if you know this, then only you will be very easily commenting on this also, that because equatorial position has similar mu and this also have similar mu, upside and downside, so here mu net will be 0. So this molecule is non-polar. So whatever theory if we have concluded with, statistically, experimentally we can check also, and this came out to be a non-polar molecule. While that one, if this F would have been there, it would also be non-polar, but actually this molecule has got a mu net. So whatever Bend's rule conclusion we have drawn, so again revising that conclusion, lone pair loves s character, lone pair attracts s character to itself, electronegative atom hates s character, and therefore they tries to give that s character, and percentage s character is inversely proportional to bond length. Now applying all these logics to some questions that will be relating to bond length. Now first, the very basic question which we already seen in the previous slide. Sir, alkyne has s character of 50%. This has s character of 33%. This carbon alkane has S character of 25%. So sir, if S character is more, then bond length will be less. So it will have least bond length, and alkane C bond H will have maximum bond length. This we already know. So we have compared the C bond H bond length as per percentage S character, that we already know also. We have felt it also. Now I'm saying you don't try to feel this for the other questions, but try to apply the logic. Now what are the set of questions? Now you have to compare bond length of O bond O. This is O bond O. This is O bond O. But this O bond O belongs to hydrogen peroxide H2O2. This O bond O corresponds to O2F2. Sir, why you have drawn structure like this? Because this is also a block chemistry logic, that these molecules are not planar. For example, if this is H, this is O, this is O, and this is H, then the plane in which this H is lying and the plane in which this H is lying, they are not same plane. It is an open book structure. If one is lying in this plane, the other is lying in the other plane. So this structure is also known as open book structure. So I'll name this structure separately for you. So this structure is termed as open book structure. So this is a factual logic which you should know through the nature this molecule. Now coming to common sense, we are asked the O bond length. So this is also O bond O, this is also O bond O. Now this is very simple. What can you say about this O bond O? This you can easily do through logic also. What logic? Oxygen and hydrogen, which is electronegative? This is minus, this is plus. Here this is minus, this is plus. So electron density, because of presence of lone pair also and because of presence of shared electron pair cloud also, the minus is so much high, minus and minus will repel each other and will bring this bond length to maximum distance. Over here, the electron cloud on oxygen is reduced. Why? Because it is connected to a more electronegative fluorine. So this is minus and this is plus. This is minus and this is plus. Electron cloud is reduced, so this repulsion will be reduced. If repulsion reduced, they can at least, I'm not saying they'll attract each other, but they'll be at least closer to each other. This Y will be slightly less, but here because of this high repulsive forces, they try to be far apart from each other. So obviously I can say this X is larger, that Y is smaller. This X is larger, this Y is smaller. But you can also apply the logic which we have just now concluded with. What logic? Electronegative atom hates S character, do not love S character. So electronegative atom gives all whatever S character it has in its hybridized orbital to lone pair, because lone pair loves S character, and it also transfers its S character. Who? Electronegative atom also transfers S character to, if another less electronegative, or from me, if it is electropositive, then I'll transfer that my S character to that one. For example, applying that same logic over here, if I'm saying fluorine is an electronegative atom, okay sir, electronegative atom hates S character, so it will transfer the S character to lone pair also. It will transfer the S character to less electronegative oxygen. This bonded pair is O bond O. Oxygen is less electronegative than oxygen. So here fluorine is transferring S character to lone pair also, and this bond also. This hydrogen do not has this capacity because it is not electronegative with respect to oxygen. So for this O bond O, percentage S character is transferred to it. So here S character is increased. So if S character is increased, bond length is decreased. Transferring of electron takes from S character takes from that side also, from this side also. So because S character is increased here, S character is increased. So if S character increased, bond length decreased. So this O bond O will be less. O bond O to F2 will be less. Applying the same logic. Although over there we can even say by simple logic of electronegativity difference. But here you cannot do that. You have to use that logic only. Again, let us try this. We have to compare O bond F. O bond F. This. We have to let us focus on one. This O bond F and this O bond F. Now, if you have to compare O bond F, so let us do that. Now, this O bond F is connected directly with an electronegative atom. This electronegative atom will transfer S character to lone pair also. This will transfer, no. This F is connected with an O which is connected to an equal. This is not an electropositive atom. So I can transfer my lone pair. If I'm an electronegative atom, fluorine is an electronegative atom. It can transfer it lone pair to lone pair. It will transfer to lone pair, to this also, to this also. But it cannot transfer to this bond because this is that fluorine itself. Even this fluorine can also do that, transfer to this also, and it cannot even transfer to this bond. But come over here. This fluorine can transfer its S character to this lone pair. To this lone pair. Sir, this can also do to this and this. But it can also transfer its S character to this O bond O. Because this O is electropositive with respect to F. So here S character is more of the S character has been transferred. So for F, S character is decreased. This one. Because this can transfer to lone pair also and to bond pair also. This can only transfer to lone pair. Moreover, here this fluorine is also transferring to that lone pair only. This oxygen's lone pair is receiving S character only from this. So they can easily and highly, to a large extent, these lone pair can extract, because lone pair loves S character. So they can, to a large extent, extract S character from this fluorine, and this fluorine will also furnish S character to this less electropositive, less electronegative O bond O. So because S character is decreased, so its bond length will be increased. So this O bond F will be large. So O bond F of O2 F2 will be large and of OF2 will be small. This type of question you can only apply by extracting the conclusion of Bend's rule, which we are doing. For example, this is a good logic. I mean, let us do one more example. Now, compare this S bond F, but what F? Equatorial F. So this, not the axial one. The question is even telling you this equatorial S bond F. So I have to compare this bond and I have to compare this bond. Equatorial we just have to compare. Now, sir, what about the shape? SF4 and SOF4. Sir, this is SF4. This is FOF4. You can very well draw through VSEPR theory and VBT what we know. Now, what we do not know is how to compare this S bond F bond length. Both are S bond F, but they are same, no. Because Bend rule say hybridization do not have same percentage of S and P character, all hybrid orbitals. Now, sir, this F can transfer its S character to this lone pair. Although it only has this lone pair, it does not have any less electronegative atom. So only to this. Okay. What about this? Sir, this fluorine can transfer. Sir, this is not lone pair. This is okay. It is less electronegative, so it can transfer. But lone pair loves electronegative, loves S character. Lone pair of electron loves S character. Remember, lone pair of electron loves S character. It also has to receive that S character, but lone pair loves S character, so it will extract more of S character. So here S character is reduced to a larger extent. Here also S character is reducing, but to a smaller extent. So less be the S character, more is the bond length. So this S bond F of SF4 will be larger than S bond F present in SOF4. Beautiful example. Moving ahead. Okay, one more, sir. Yes, these type of questions are, I mean, students fear from. Now you tell me, do you fear? Let us try this again. Same logic we'll apply. We have to compare C bond F in these four molecules. Do we have some symmetrical molecules? Yes, CF4. So can first let me draw this CF4 separately for you. So drawing this CF4 separately for you. So this CF, F, F, F. So let us focus on one CF. Let's say this one. So here, because it is a symmetrical molecule, so obviously we know it is tetrahedral. We know what is percentage S character. It will be strictly 25%. This we know how to calculate because it is sp3 hybridized, so S character is 25%. So whatever be the length of this S bond, C bond F will have an S character of 25%. Okay, sir. Now going to the okay, CHF3, going to the extreme side because F is increasing one by one. So I'm going to CH. Okay, so I have to compare C bond F. So this is CF. And let's say I have only one CF and rest are H. So what bond I have to compare? I'm changing its color. I am to compare this bond. That's why this I have written separately. Now you tell me here what all things are present. Sir, this fluorine will transfer its S character to this hydrogen also because this is electropositive with respect to fluorine. It will transfer S character to this hydrogen also. It will transfer S character to this hydrogen also. Because I'm transferring more of my S character, so my S character is much reduced. So if my S character is reduced, this bond length is increased. This fluorine is not able to furnish to give its S character anywhere. So obviously its S character will be as compared to that one. Here S character is more. So if S character is more, this bond length will be less. So among this and this will have less bond length. CF4 is having less C bond F bond length, while CH3F has the highest bond length. Why I'm saying highest? Because here the C bond F will transfer. The C bond F will definitely transfer, but here it is transferring to three sides. So S character is getting reduced. Let's say I'm talking of using another color, H, H and F. Now I can definitely still transfer my S character, but I can transfer my S character to two places. So here S character is much reduced, so size is much more. Here S character is distributed to two places, so S character is reduced as compared to this, but not reduced to that extent. So size, because it has low S character, it has larger S character with respect to that one. So if S character is more, bond length will be less. Similarly, we can do for CHF3 also, because then there will be transfer for one C bond H only. So I hope I'm making sense, and I hope now this question I want you to do by yourself. This will be a homework for you because I'm using the same logic. So this will beautifully make this question of yours. Now, moving to the other side. This is also an extension, although again, this is also not there in chemical bonding side of NCERT, but related to block chemistry. Now, when we see block chemistry, when we see bond angles of hydrides, especially of p block, nitrogen family and oxygen family, these hydrides of group 15 and group 16 elements, when we saw them, and in bonding one also we have compared the bond angle, so it is very easy for us to compare. For example, I'll again do it. Let's say central atom is E, maybe N as in group 15 element, maybe O or TE as in group 16 element. I have to compare the bond angle. So first you tell me, what is the hybridization? Sir, easy. Let us make it for NH3. Sir, nitrogen, a lone pair and 3 hydrogen. So hybridization is sp3. What about water? Sir, again simple. Oxygen, one lone pair, another lone pair, one hydrogen, another hydrogen. So what can you say about this angle theta? This is theta. This is theta. I can definitely say because of presence of lone pair, this theta is lesser than Tetrahedral angle 109 degree 28 minute. Its shape is trigonal, pyramidal. Its shape is V shape or bend shape. Theta is less than 109 degree 28 minute for both of them because there are presence of two lone pairs. So let's say this is theta 1 and this is theta 2. So I can definitely say theta 1 because there are two lone pairs, so they'll repel more. So theta 1 is less, theta 2. We obviously know the value also. This is somewhere around 107 degree and this is somewhere around 104.5 degree. We already know this, done that, been there, done and dusted. But what I'm trying to explain you right now, what can you comment about their bond angle when we move down the group? So focus on nitrogen, HH. Nitrogen, HH. If I am electronegative, I will share the electron cloud. I will extract the electron cloud. I will become delta negative. So if I am minus, the electron cloud on my shoulders are high. The same question we have done in bonding 1. So if these shoulders, I'm attracting electron, so my shoulders will become heavy. So angle with respect to, because repulsion will be more, so angle will be large. So as my electronegativity decreases, because we know down the group electronegativity decreases, so definitely bond angle should decrease. So point is, bond angle of hydrides of group 15 also and group 16 also should decrease down the group. Sir, it is definitely decreasing. Yes. Bond angle is definitely decreasing down the group. No worries. But when a scientist called Drago started looking at the value of this angle, it was decreasing drastically after second period to third period. And after third period element, although if you snatch the neck via spectroscopy, you will see bond angle is decreasing. But look at the value, my friends. Look at these values also and these values also. So by looking at these values, the famous scientist Drago, he concluded that these elements, the central element of hydride of group 15 and group 16 post group second period element, that is post nitrogen, after pH3 till antimony hydride, after sulfur till tellurium hydride. So he said that these central atoms are not at all getting hybridized. Why? Because if they will not get hybridized, then what orbitals they will use for bonding? Like for example, let us do it for phosphorus hydride. The picture I've already given, but let me give you a basic regarding it first. Phosphorus is a group 15 element. Electronic configuration will be 3s2 3p3 because it has 5 electrons in its valence shell. 3s has 2 electrons, 3p has 3 electrons. So is the case with nitrogen also, because nitrogen is also 2s2 2p3. So what we say to hydride of nitrogen? We say to hydride of nitrogen that it is forming 3 bonds with hydrogen. So 3 hydrogens are coming with their 1s1 electron. 1 will form a sigma bond, 2 will form a sigma bond, and 3 will form a sigma bond. Lone pair always is given a hybridized orbital. So how many orbitals take part in hybridization? 4. So how many are formed? 4. So there will be formation of 4 sp3 hybridized orbitals. One sp3 hybridized orbital containing the lone pair, 3 sp3 hybridized orbital forming the sigma bond. So for nitrogen, hybridization takes place, sp3 hybridized. For oxygen, hybridization takes place, sp3 hybridized. But Drago said, because this bond angle should be, because lone pair repulsion, so this bond angle will be slightly less than 109 degree 28 minute, and it was less also, and falling in that range also, 109, approximately lesser than 109. Because for other hydrides the bond angle was falling to an angle close to 90 degree. So Drago said these central atoms are not even participating in hybridization. Why he's saying so? Because lone pair is present in ns orbital. Why is saying ns? Because for phosphorus, for phosphorus, arsenic, antimony, for all of them he said. Similarly for sulfur, selenium, tellurium, for all he said that the lone pair is present in ns orbital, pure atomic orbital, and the sigma bonds that they are making, they are definitely making with px, py and pz, because px, py and pz are mutually perpendicular to each other. Therefore, the bond pair that is observed in the hydrides of phosphorus and heavier, I mean the element that is coming below it, all these bond angles were closer to that of value 90 degree. So this can only take place when that theoretical intermixing, that theoretical hybridization, as in mixing, khichdi banna, that hybridization was not at all taking place in case of hydrides of these elements and these elements. So if somebody is asking you what is the hybridization of phosphorus in pH3, you will say it is not getting hybridized. What is hybridization of Te in TeH2? It is not getting hybridized. How can you say that? As per Drago's rule, because that bond angle is almost equal to, approximately close to 90 degree. That means pure atomic orbitals are participating in bonding, not hybridized orbital. Moreover, so no hybridization, that I have already written over here, that no hybridization. Okay, no, I have not written. So let me write that no. So no hybridization is taking place for these elements and for these elements, as in their hydrides. Now, one more important thing is, if, for example, let's say for nitrogen hybridization is sp3. So what is percentage s character? So 25%. What about hydride pH3? pH3 lone pair is present in a pure 3s orbital. So pure 3s orbital, the lone pair is present in pure 3s orbital. So pure 3s orbital will have a s character of 100%. More be the s character, more is the electronegativity. So because I am largely electronegative, my lone pair is present in pure s character, very very close to nucleus, because as s character increases, electronegativity increases. So if my electronegativity is more, I will not give those electrons. So down the group, basic nature, what is a base which gives electrons? So by looking at these lone pair of electrons, you can easily say, because if you just go by periodicity logic, so down the group electronegativity decreases, so they should give the lone pair also easily. But actually NH3 is the best base, and down the group basic nature decreases. This also you cannot explain. But if you know Drago's rule, you will say no, the lone pair of nitrogen is present in an hybridized orbital which has s character of 25%, while lone pair of all these elements are present in pure atomic orbitals of ns which has a s character of 100%. So if s character increases, electronegativity increases. So they are present at highly electronegative pure atomic ns orbitals, and hence they will not furnish those lone pair of electrons. Therefore basic nature of hydrides of group 16 also and group 15 also decreases down the group. Very sweet and beautiful logic. Moving ahead, so moving forward, can you relate bond angle with bond length that we have just discovered? Because see, I am mixing up all the logics, because questions JEE ask whatever slides I have made for you, specially designed for you. I have tried and include all the periodicity, chemical bonding and block questions, but I'm not spending like giving you the question and the year, and because that will be taking time and I want to save your time. So I'm just coupling all the logic for you. So can you tell me bond length and bond angle relationship? Just go by the basic which we have just read. For example, I am the central atom, these are my combining atoms. If the bond length goes on increasing, then the distance between those combining atoms with the central atom will increase. Now you tell me if this hand and this hand is repelling each other, because of which bond pair repel each other, and the distance which after repulsion they reach becomes the bond angle. So as the bond length increases, the combining atoms, their distance increase, so naturally the bond angle will decrease. So you should always keep this logic in your mind, because the combining atom are getting far away from each other. So the steric repulsion, I mean, they are also nucleus surrounded by electrons. So if these combining atoms are getting far apart, then this angle will surely get reduced. I've written that concept also for you, so make sure you remember this, that as bond length increases, bond angle decreases. That's an inverse relationship, and bond length we have already known through Bend's rule. So let us apply what we have learned. Now the theta 1 is again a bond angle of FCF. Here also theta 2 is a bond angle of FCF. If you just go by your VSEPR logic, so this is also tetrahedral, this is also tetrahedral, you will say both are 109 degree 28 minute, but through Bend's rule we know that S and P character for all hybridized orbitals are not same. So apply that logic again. Sir, over here if you go and just check this fluorine, I am checking the bond length only first. This bond length I am checking. Which bond length? This bond length I am comparing with this bond length. Now you just tell me, if I'm doing this fluorine, because it is an electronegative atom, so it will throw percentage S character to this hydrogen. It will throw percentage S character to this hydrogen. But this fluorine can only throw its S character to one hydrogen, because this is again a fluorine atom. So electronegative atom can give its S character to lone pair and to less electronegative bonded atom. So because this fluorine is throwing S character to two places, this is throwing character to only one place, so here S character is reduced. If S character is reduced, then definitely bond length is increased. So if bond length is increased, that is theta 1 is less. So this theta 1 is less than this theta 2. Simple. Again the same logic. Now again I have to compare this theta 1 and theta 2. If you just apply VSEPR theory, both are 109 degree 28 minute, but no. Bend's rule, sir, this chlorine will throw S character to this hydrogen, so this is same thing. This chlorine will give electron over to that hydrogen only. So here S character is reduced much. So if S character is reduced, bond length is increased. If bond length is increased, then bond angle will decrease. So this theta is less. So theta 1 is here also. This theta is less than that theta. I guess I'm making sense and it is becoming clearer to you. Now, I'm giving you some more questions for practice, but again, in order to give some inorganic logics first. Okay, let me discuss this first question. N2H2 and N2F2, you have to compare N bond end. Now there is a reason I'm comparing this question, because sometimes JEE tricks you with this. So this is N2H2 and this is N2F2. We have already learned, what we have learned is, if we have to compare this bond length X and this bond length Y. Now we very well know this fluorine will give its S character to here also, and it will give S character to the lone pair also. This hydrogen cannot do such stuff. So over here we can definitely see, because it's an electronegative atom, so it will give its S character. So in N bond N, in Y, percentage S character is increased. Because S character is increased, so definitely the bond length is decreased. So this Y is less. This N bond N is smaller as compared to this bond N bond N. Now, how JEE tricks us is, why this you have already told, so why you are telling again? Because, can you tell me which bond length N bond N is higher, the X or the Y one? Do not apply Bend's rule. Bend's rule is only applied for similar structured species. Here bond order was 2, here bond order was 2. Whenever I was comparing as per VSEPR theory, the molecules, the bond length, everything was getting tied. So we compare applying Bend's rule to those species which are almost equivalent. Otherwise, here bond order is 2. Here this n bond n has a bond order of 1. Sir, more be the bond order, less is the bond length. This is the basic which we have already discussed. This is a class 9th 10th basic. If two atoms are connected to each other with more number of bonds, obviously the distance between them decreases. So never forget your basic. Bend's rule, the higher, this is Bend's rule is a higher education for us. So the higher logic is only applied when all the characteristic of a particular bond is similar. Then you apply Bend's rule like we have applied in so many cases before. If the structure is even not same, this is bond order 2, this is bond order 1, then go by a logic which says as bond order increases, bond length decreases. So because bond order is 2, so this bond length will definitely be lesser than that one. If you'll apply Bend's rule, you will go mad, your answer will be coming wrong. So Bend's rule applied when everything is same. Moving ahead, I think you got the point. Now, a very small topic again, as per questions, these things are also asked in ABC. I've included all those things. You will find so many questions which says that which of the following the molecule exists or molecule does not exist. How can you predict? Through VBT and VACPR theory, we can always predict whether the molecule exists or not. But some chemical bonding logic also applies to a molecule existence in nature. Now, I have divided this into few cases. Case number 1. Whenever the central atom does not have any d subshell, sir, who does not have any d subshell? After third period, because 3s, 3p, 3d subshell exist. It may be unfilled, but covalency can expand because excitation can take place, as we have seen so many examples. But sir, there is no 2d orbital. Second shell has only 2s and 2p. Therefore, for strictly this is only applicable for second period elements, because second period elements do not have d subshell. So even if they are approached by some high polarizing atom, still they cannot excite their electrons, cannot increase their covalency beyond 4, because second period element only has one orbital of 2s and 3 orbitals of 2p. So their maximum covalency can go till 4. For example, this BeF2, because it has formed 2 bonds, so 2 orbitals are occupied. So, but it will be having 2 empty orbitals, so it can maximum accommodate 2F minus, and therefore existence of BeF4 2 minus is possible. If question is telling you BeF4 5 minus, then that molecule cannot exist. Similarly, BCl5 and NCl, phosphorus is a third period element, can expand its octet, but nitrogen is a second period element, maximum covalency of nitrogen. Although for nitrogen, if you'll see, for nitrogen family, if you'll see, it is 2s2, 2p3. So 2s is definitely completely filled. So what maximum covalency it can have is, it can form 3 sigma bonds, obviously. 1 sigma, 2 sigma, 3 sigma, and this lone pair can be coordinated. So maximum it can have a covalency of, although this covalency, the fourth valency, it can only form when the other atom is having completely empty orbital, because this lone pair has to be coordinated. So keeping things short, maximum covalency of second period element is 4. So can NCl5 exist in nature? No. So this can exist? Yes. This type of question comes. Now, sulfur, third period element, so sulfur can form SF2 also, it can form SF4 also. Oxygen is a second period element, sir. Its maximum covalency is 2. Sir, can go till 4? No. For oxygen, even 4 is not possible. That's why I've given this picture for you, so that you can see nitrogen can attain a maximum covalency of 4. But for oxygen, let us check. Oxygen has electronic configuration of 2s2, 2p4. This is the configuration which you can see. Now, oxygen can definitely form 1 sigma bond and 2 sigma bonds. So 2 sigma bonds it can form. The extent to which you can donate your electron, coordinate bond, whatever we have seen, generally, if at all oxygen will try, it can maximum donate 1 lone pair. It can donate 2 lone pair. So actually maximum covalency, if in nature, although certain molecules are not even found, but if at all oxygen wants, then in nature maximum covalency found of oxygen is 3. So this OF4 also does not exist in nature. So OF2 exists, but obviously when D orbitals can expand, so you can find SF4. Now just like this, what are these X minus? Halogen, any halogen already having 7 electrons. Let's say this 8th electron is coming extra, so this central halogen will attain a minus. 1 electron may get excited and form these 2 bonds. So this is the structure of actually X3 minus, although I know it is a linear structure, but here I am just drawing the Lewis dot structure. Now you tell me who can have this maximum extent of bonding. So those who have d orbitals, obviously F3 minus will not be formed. All these 3 are found in nature. So this completes the non-occurrence of molecule because of absence of d orbitals. Moving forward, now because of steric repulsion, if the central atom is combining, why we have already done this a few examples, so I'm listing all of them together now. If the central atom is approached by combining atoms, and if combining atoms are large enough, then the molecule, then those combining atoms may not get combined because they are large. The steric hindrance, the crowding that they will create, will destroy the molecule and hence it cannot exist. For example, phosphorus can have maximum 6 chlorine around it, so PCl6 minus is possible. We have already seen this also, structure also. But PBr6 minus, this octahedral arrangement is not possible because Br minus is too large. So accommodating 6 incoming, that too 6 big Br around phosphorus is not possible. Hence this does not exist. Now for other, this is just for case of chlorine, that PCl5 exists in nature. For other species, their chlorides are also not existing in nature, like SiCl6 minus. This is actually a JEE question in which option was given and it was said that which of the following does not exist in nature. So for other, although they are third period elements, but with chlorine also, chlorine is also that, because second period element are small, even third period elements are large enough. So only phosphorus find coordination number of 6, coordination number as in number of bonded atoms that is approaching phosphorus. For phosphorus, PCl6 minus existing nature, but for other third period element like silicon, sulfur, moreover iodine, even large number of chlorine makes them sterically so much crowded, so they do not exist. But obviously the fluorides of such species can only exist in nature. So make note of these molecules. Now if I have to reach a maximum covalency, as in if I have to reach a maximum of combining atom towards the central atom, then I have to attain a high positive oxidation state. Who can make me highly positive? Only high polarizing anions like F minus, oxide. Only F minus and O2 minus. Oxide has the capacity to bring a central atom to its maximum positive oxidation state, and therefore SiF6 minus will exist in nature because silicon is a carbon family element, so it can always have 4 fluorine. But if 2F minus are also coming, it can accommodate them in its empty d orbital. What maximum bond pair a central atom easily accommodates, we have already discussed. Still octahedral structure molecules exist. 7 combining atoms is only seen for IF7, and that too over here also you can see here iodine is reaching to an oxidation state of +7. So who has this capacity to bring you to your maximum oxidation state? Only those anions who are high polarizing, because they are containing charge and their size is also very small, so the polarizing power of F minus is too high. Similarly, this SiF6 minus is possible. Hydrogen cannot bring an element to its maximum covalency. PF5 is possible, PH5 is not possible. SF4 is possible, obviously SH4 is not possible because H minus hydrogen is not at all having that tendency to bring the central atom to its maximum oxidation state. Very good examples indeed. Now moving ahead. Now again, Coming to halogens, we know that for halogens down the group, I'm not talking of F minus because generally it is not fluorides, those fluorides are not asked, but down the group, if you talk of halide ion, then their reducing nature, what is, if I am a reducing agent, I will reduce you. If I'll reduce you, I'll oxidize myself. What does oxidation mean? Loss of electron. Sir, chlorine is most electronegative, iodine is least electronegative, so it will have no tendency to carry this, it will have least tendency to carry this extra minus, so this minus can easily be given. So it itself can easily undergo oxidation. So if it can oxidize itself, it will reduce others. So whenever this I minus compound is formed with a metal, it will always try to oxidize the I minus will oxidize itself and will reduce, will reduce that metal. For example, here iron is in +3 state. Here also iron is in +3 state. Who has the capacity to reduce Fe from +3 to maybe +2 state, or maybe to iron? That halide which is having the highest reducing agent tendency. And who has the highest reducing tendency? I minus. Therefore, this Fi3 will not exist because I minus will oxidize itself and will reduce the metal, while the chlorides can easily exist. Iodides will not exist. Chlorides can relatively easily exist. Iodides cannot exist, chlorides can relatively exist. Now, for bismuth, because bismuth is New Zealand, Pakistan, Australia, sab bikau nitrogen family. For nitrogen family, the heavier member via inert pair effect, their group oxidation state -2. So bismuth anyway from its +5 state, it wants to reach to +3 state because of inert pair effect. Therefore, in case of bismuth, only BiF5 is known to exist in nature. Leave I minus, even BCl5 will reduce Bi +5 till Bi +3. So any halide of bismuth is not stable in nature, they do not exist, and only BiF5 exist in nature. So these are some beautiful facts which one should remember. Moving ahead, yeah. So coming back to this inorganic information, NCRT information, which I wanted to give you, although I asked that this question I'm giving you for practice, but just this third one, the P4O6 and P4O10 molecule, because NCRT gives this beautiful picture, which I've already mentioned, that this is the actual cyclic structure of P4O6. Sir, but we have to compare P4O6 with P4O10, so no big deal. The same structure gets modified. How? Just count. I have 4 phosphorus, these are 4 oxygens, and these 2 oxygens are bridged oxygens. Now, if this is P4O6, so if I need to draw P4O10, what I have to do is share these lone pair of electrons with whom? With oxygen, sir. So let's say this is phosphorus, so this will be a double bond O. This will also be a double bond O. This will also be a double bond O, and this will also be a double bond O. So this after, if this is P4O6, then this 4 oxygen addition makes it P4O10. Now, the question is again the same. Let's say this bond length is Y and this bond length is X. I mean, now you can very well attempt the question, but because I've made the structure, so let us do this also. Now, again apply Bend's rule. Sir, everything is same. So this oxygen will transfer the S character to lone pair. This oxygen will transfer the lone pair, okay. To the bonded, it cannot transfer because it is not of lesser, it is just oxygen only. But this oxygen will transfer the S character. This will transfer the S character to lone pair. This will transfer the S character to obviously a double bond. But sir, who loves S character? Lone, the lone pair. So lone pair will obviously withdraw much of the S character. So over here, S character is decreased. So if S character is decreased, then bond length will increase. So obviously this X will be larger in length than this Y. Similarly, this question obviously I have given you for practice, so you can do, and if you find any doubt then you can always comment. Okay, this Br6 minus, I said it will not exist, although I made a tick. Why it will not exist? Because of the crowding, because of the size of large bromine. So 6 bromine cannot be accommodated, so it will break down and it will form PBr5 and Br minus. So these molecules won't exist. Now moving forward to the one of the very important topic loved by JEE mains, not in NCERT but a part of block chemistry, the S block, P block, hugely asked. Now very simple. Now what is back bonding? In questions, what you generally see is you generally get two types of back bonding. So discussing about the first case 1, when the back bonding, that is the electrons are donated to the central atom. Sir, when, for example, we all know a BF3 molecule. So what will be the hybridization of boron in BF3? Sir, sp2. So let's say this boron is sp2 hybridized, and obviously we can see that because it's a second period element, octet is not complete, so it will be in Lewis acid. But in nature it is found that its acidic nature is not at all valid. So when chemist has drawn their minds into it, they found that because of the presence of this empty 2p orbital of boron, because it will have a geometry of trigonal planar, these fluorine have excess of electrons, that is their lone pair of electrons. Post the formation of pi sigma bond, obviously this back bonding can also take place, because excess of electron is like minus, deficiency of electron is like plus. This vacant orbital of boron is making it electron deficient, a Lewis acid. So why it should wait for receive of electron from outside when in-house supply is more than sufficient? So this fluorine can easily form a 2 pi 2 pi, but now this bond to which I'm referring as back bonding, because after formation of sigma bond, the combining atoms are back bonding, as in forming a pi bond via overlap of 2p 2p of their atomic orbitals. So sir, then this all the three can give. So that's why I have drawn these resonating structures. So this can also give, this can also give, and this can also give. This is your basic concept of back bonding. So what can you predict about the resonance hybrid? Sir, sometime this is double, sometime this is double, sometime this is double. So what can you say about the bond order? A bond order is definitely 1, but that one extra bond is shared by 3. So bond order becomes 1.3. So if we just look at the structure of BF3, we'll say bond order is 1, but actually bond order is increased. So because bond order is increased, bond length of B bond F will be definitely experimentally lesser. Hybridization, over here it is also sp2. Sir, hybridization is still same, so it is still sp2. Bond angle 120 degree, 120 degree, but acidic nature of boron is decreased. So if you do an experiment and a question, this is a very beautiful question asked by JEE, that what is the acidic nature of these boron halides? Sir, we know who has the ability to do effective back bonding. We already know this through our orbital overlap concept. We definitely, all of us know, there will be a back bonding by halogen to boron. There will be a back bonding by halogen to boron. Definitely yes. But who will have an effective pi bond formation? Sir, boron is a 2p orbital, but fluorine will have this pi bond formation via 2p 2p overlap. Chlorine will have via 2p 3p overlap. and iodine will have via 3p, 2p, 5p overlap. We already know when value of N1 plus N2 is different because N1 is 2, N2 is 2. So value of N1 plus N2 over here is 4. And value of N1 plus N2 over there is 7. Sir, when N1 plus energy level is only different, then lower energy is more stable. So this will have effective overlapping and this will have least overlapping. So if boron was not having a complete octet, then this fluorine has sufficiently filled the empty 2p unhybridized orbital of boron has satisfied its acidic strength. So it will be a weakest acid while Bi3 will be the strongest acid. Or else if you would not be knowing the concept of Beck bonding, you will be doing like, sir, fluorine is electronegative, boron has a oxidation state of +3, so it will be most acidic. So this is how concept of back bonding is going to help you with your examination. Moving ahead. Now, sir, sometimes the other way around also can take place. Yes. So sometimes back bonding can even be, the pi bond can even be formed when the electrons are donated to the bonded atoms. Like over there, the central atom was boron and was gaining pi electrons. So other way around can also take place, like in case of nitrogen family. For example, I have the structure of nitrogen bonded with 3 units of SiH3. Now, from VSEPR theory, we can easily tell that the hybridization of nitrogen is sp3 because 3 bond pair and 1 lone pair. Shape is, this is a triangle, this will be trigonal, pyramidal. But silicon has empty d orbital. Remember, silicon is not a second period element. It is a third period element beneath carbon. So because of presence of empty d orbital, silicon can easily accommodate this localized, this electron pair, the lone pair, which is an excess of electron in nitrogen. Remember, lone pair of nitrogen is always present in an sp3 hybridized orbital. So S character is 25%. So it will be a good base, basic nature decreases down the group. Now, because it is a good base, it wants to give this electron. If it has a facility of giving electron in-house only because silicon has empty d orbital, so there will be formation of p pi d pi back bond, but from central atom nitrogen to the empty d orbitals of silicon. So this p pi d pi bond can also be, sir, sometimes it will give to this silicon, sometime to this, sometime to this. So again, a case of resonating structure will take place and this will be your average resonance hybrid. But now the lone pair of nitrogen is not present because it has formed a pi bond, and for steric number calculation we never calculate pi bond because this lone pair is not existing. It has been transferred, it has been donated and formed a pi bond. So steric number of nitrogen will be 3. Lone pair is not present. Lone pair has formed a pi bond, and to pi bond we do not count in steric number calculation. So its hybridization becomes sp2. Its shape becomes trigonal planar and its bond angle becomes 120 degree. Over here it was although less than tetrahedral angle, but over here it has become 120 degree. So this over in this case of back bonding, everything has been changed. What can you comment about the bond order? If you just look at this structure, you might say bond order is 1, but definitely this bond order is increased 1.33, and because bond order is increased, so bond length is decreased. Moving ahead, this beautiful concept can be applied with some questions also. Like for example, if I'm asking you BOH3 and BOH whole thrice and boron OH4 minus, you have to comment on the B bond or bond length. Sir, again easy. This is boron, one OH, second OH and third one. So obviously now we definitely know sometimes this will form a pi bond, Sometimes this will form a pi bond, sometimes this will form. So this is a clear case of back bonding. Because of back bonding, bond order increases. Because bond order increases, so bond length will definitely decrease. So B bond or bond length of, sir, why you're not checking? Because this is boron, OH, 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 and the empty 2p orbital of boron is receiving OH minus from outside. So it must be receiving an extra electron, therefore minus, and the extra electron is given by whom? By the fourth OH. So this becomes your structure of BOH whole 4 with a negative sign. Now, because the bond order is simply 1, so bond order is 1, which is more, so bond order more, so bond length will be higher, larger than bond length of B bond O in case of orthoboric acid. H3BO3 is orthoboric acid. Now, sir, we find back bonding applications more? Yes, definitely. A very famous NCRT example of inorganic benzene. We all know what is a benzene. Alternate position of sigma and pi bond. What is inorganic benzene? B3N3H6. Now, alternate boron nitrogen we have drawn, then one hydrogen we have equally given to all of them. But sir, we cannot see alternate pi bond like that of benzene. Just take a look again. I guess it will be quite visible to you. This nitrogen giving coordinating its electron over here, this one over here, this one over here. Sir, why you're not drawing it? The reason I'm not drawing it is because I need this picture. Now, why do I need this picture? Because obviously you can see with this back bonding pi sigma pi sigma pi sigma pi. So this becomes a structure like that of benzene. The pi cloud is delocalized in the ring. I'm sorry. The pi cloud is delocalized in the ring, but order of reactivity of benzene is much less than inorganic benzene. Still, why, sir? There is also a case of resonance which will provide stability. It is stable, but not as stable as benzene, because here you can still find polarity. How? This lone pair is donated to a boron, but if it encounters another acid, another H+, then this H+ will preferably attack the lone pair on nitrogen. So this H of HCl will be attached here. When this is gone, then boron is again a Lewis acid, so it will require more of electrons. So Cl minus will be delivering its electron to boron, and therefore this H and this Cl, this H and the Cl, what does it give rise to? It gives rise to formation of B3N3. Because I have received 3 moles of HCl, so H6 becomes H9, and we have 3 chlorine atoms. So this is your product, which shows that although structure of B3N3H6 corresponds to a benzene structure, but still polarity exists in inorganic benzene. While benzene of your organic chemistry is quite stable, it does not show such reactions, such addition reactions easily. Now, this is a very famous point, the structure and the reactivity of inorganic benzene. Now, one point. If I'm asking you about the hybridization of boron and nitrogen in inorganic benzene, so because the back bonding will definitely take place over here. If you do not know this concept of back bonding, just by looking at the structure, you will say hybridization of nitrogen is sp3 because 3 bond pair and a lone pair. But is this lone pair available to this nitrogen atom? No. This lone pair is donated and formed a pi bond with boron. So what will be, because it has formed a pi bond, so it will be a plus, it will be a minus. So ultimately for nitrogen, how many bond pair we have? 3. How many lone pair we have? 0, because pi is not counted. So this will be, nitrogen will be an sp2 hybridized system. What can you say about boron? Sir, boron is still sp2 after getting that pi. That pi will not be calculated in steric number calculation, so it will again remain sp2. So hybridization of both boron and nitrogen will be sp2, and this whole molecule, just like benzene, will lie in a single plane. So another very famous example and application of back bonding in NCERT. Now, extent of back bonding. We have already discussed some question. Let us discuss few more. Now, I'm giving you these three structures. You tell me which have an effective back bonding. Sir, boron, Lewis acid, empty orbital. This will be coordinated. Perfect. This can also be coordinated. Perfect. This can also be coordinated. Perfect. Now, sir, this is 2p. This is also a 2p second period element. This is also 2p second period. Sir, everything is tied. Then remember periodic table. If not, I'm telling you, along the period, if everything is through chemical bonding, everything is same. So go to periodic table. Along a period, electronegativity dominates. Now, because fluorine is most electronegative from oxygen and nitrogen, so it will not have that much of tendency to donate its lone pair, and nitrogen being least, so here nitrogen being least electronegative will have the maximum tendency to donate, so maximum donation. So this will be more effective because nitrogen is very much wanting to donate as compared to oxygen, and the least will be fluorine. Moving ahead, sir, if all nitrogens are there, obviously still they'll do a back bonding. But here this boron is receiving electrons only from this nitrogen. Here the boron is receiving, maybe sometime this will give, sometime this will give. Over here, boron can receive it from three different sides. So in which case boron will be only looking at one member. Now here the boron has been over pampered by different nitrogens. So it will be looking at each nitrogen to a much lesser extent because it has got excess of supply. But this boron is very much depending on this nitrogen atom. So over here, the extent of overlapping will be highest because this boron is depending entirely on this nitrogen. And when the supply gets increased, obviously demand gets decreased. So extent gets decreased. A very beautiful example of common sense. Moving ahead. Now, talking of application of back bonding in carbon family. So talking about a very famous intermediate, that is carbene. What is carbene? CH2 with a lone pair. So carbon, 2 bond pair and a lone pair. Now, these carbenes are basically of two types. This is an inorganic logic, but direct application of back bonding. So telling you this also. Now, basically, these intermediate carbenes, they are not end products. They are formed in a reaction as reaction intermediates. Now, these carbenes are basically of two types. One is triplet carbene, another is singlet carbene. Sir, how this triplet and singlet is designated? Through the multiplicity. What is the formula of multiplicity? Twice of total spin plus 1. What is this total spin? For example, this carbon is forming 2 bonds with hydrogen. Obviously, carbon has 2 bonds, so 2 bonds have been formed, so it will be having its 2 orbitals, one orbital and the other orbital. Now, if these two orbitals, okay, I'm sorry. Now, if these two orbitals, okay, it is not moving. Let us do it over here only. If these two orbitals contains these electrons, the number of electrons present on the carbon of carbene is 2. But it is experimentally found in mother nature that sometimes these two electrons acquire different orbitals, and obviously what we know is sometimes it can even be present in one orbital, then this is definitely a lone pair, which we know. So over here, the spin will be plus half and minus half. The total spin will be 0. But over here, the spin will be plus half and again plus half. So the total spin will be 1. So the value of this S is 1. When this total spin is 1, so multiplicity becomes 2 plus 1, that is 3. So when multiplicity is 3, that particular reaction intermediate, because it's an intermediate, that's why I'm giving this two options. Because it is a reaction intermediate formed in just between of a reaction. So via some reactions when I'm formed, then my electrons may be present in different orbitals or they may be present as a lone pair in one single orbital. And obviously, in this case, the fourth orbital will be a unhybridized orbital. So this will be two sigma bonds and a pi bond. So hybridization of this carbon is strictly sp2 because two sigma bond and a lone pair. And because of the presence of lone pair, spin is 0. So multiplicity of such a intermediate will be 1. And this intermediate is then termed as singlet carbene. Now, talking about the stability. Obviously, you can see because of presence of lone pairs, energy will increase because these electrons are present in one orbital. Lone pair always has higher energy. So in general, triplet carbene is more stable than singlet carbene. The point of organic chemistry which I'm making over here. Sir, but there is no back bonding concept. If instead of singlet carbene or triplet carbene, we have halocarbene, as in the two sigma bonds are not from hydrogen, they are bonded with some halogens. Then in such cases, if I have a singlet carbene, for example, let's say this, I have a chlorine, or I may have any other halogen atom. The chlorine I'm mentioning because CCl2 carbene is most famous in NCERT. So talking of singlet carbene, then sir, lone pair is present. What is its hybridization? sp2. There will be an unhybridized orbital. There will be an unhybridized 2p orbital which will be empty. Now, in this case, the singlet carbene case, because there is an empty orbital. Okay, sir. This is an empty orbital. This is an empty 2p orbital of carbon, unhybridized. We have chlorine. This chlorine is having excess of electron. So shall these excess of electrons be coordinated to this empty orbital? Definitely yes. And because of this back bonding, the stability of this singlet carbene increases, which is otherwise for case of carbene, triplet was more stable, but because of presence of back bonding, this will be a 2p. Okay, sorry, chlorine will be having the lone pair on 3p orbital. So this will be a 3p 2p back bonding. And because of presence of this back bonding, singlet carbene, but singlet halocarbene becomes more stable. Hence, these reaction intermediates are given by some reactions of NCERT that we'll be discussing in organic chemistry. Now, one more question, sir. Carbon family application of back bonding. Yes. If you are supposed to tell which is a stronger acid, CHF3, again an organic chemistry basic, but giving rise, getting birth through inorganic concepts. So which is a stronger acid? Obviously we know because they are carbon containing acids, so they will be weak acid. An acid after giving H plus forms a conjugate base. So the conjugate base over here will be CF3 minus, and over here it will be CCl3 minus. Now we already know this, that organic compound is a very weak acid. Okay, but relatively who will be a stronger acid? Whose equilibrium will be lying on the forward direction? Whose equilibrium will be lying on the forward direction? The conjugate base formed, if it is stable, then it will be formed. And if it will be relatively formed to a larger extent, equilibrium will be shifting to forward direction and the acid will become a relatively stronger acid. Now, can you find any sense of stability? Yes. Where? Sir, carbon is not able to hold this minus, but it is connected with an electronegative chlorine. Sir, it is also connected with an electronegative fluorine, but fluorine is a 2p orbital, is a second period element. It does not have any empty orbital to accommodate those extra electrons. Remember the electron gain enthalpy thing? But chlorine, because of the presence of empty orbital, there will be a back bonding from of 2p electrons of carbon getting into empty 3d orbital of chlorine. So because these electrons are holded up via back bonding by chlorine, so this conjugate base will be more stable. This is not at all stable, and hence it will be a strong acid and it will be a weak acid. A very beautiful concept based on back bonding. Now, one last question for carbon family relating to back bonding. Now, sir, this we have already done. Sir, silicon bonded with 4 iodine. Sir, silicon bonded with 4 fluorine. Sir, this we have done in case of boron. You are asking about the acidic strength. Sir, there will be case of back bonding. Definitely yes. There will be case of back bonding. Definitely yes. But what the question is asking us, who is a better acid? Obviously, extent of this back bonding is much stronger because this is from a 2p orbital while this is from a higher orbital. 2p, 3p, 4p, 5p. This will be from a 5p orbital. Agreed. But unlike boron, students make this mistake n number of times. So you please make this thing note in your copy that boron, after receiving that pi cloud from halogen, has no orbital left in it because boron is a second period element. Silicon, on the other hand, silicon has 3s2, 3p2, 3s2 electrons, 3p2 electrons. What I'm doing, I'm exciting this silicon 2s electron, 3s electron, forming 4 bonds. Okay, so these 4 bonds are definitely formed by fluorine. So let me draw it with a pink color because these sigma bonds are formed by 4 fluorine. So if at all silicon is receiving this back bonding only, it is receiving where? It is receiving in the 3d orbital, which is empty. So if it is receiving this from internal F, it can also have a coordination number of 6. It can also accommodate 6 people. So it can also ask one more base to come and give its electron. So base, if doing an investment on silicon halide, base is a species which wants to give electron. So I will give electron where? Because fluorine, 4 fluorine atom will make the +4 charge on silicon a very high positive charge. Therefore, if I am a base and if I am an investor, want to give money, want to invest money, if I have an empty d orbital, then why I should invest in such species which is getting this +4, but getting this +4 with a very weak halide, because electronegativity of iodine is not that high. Whereas this fluorine will definitely withdraw so much of electron from silicon that this +4 magnitude is quite high. Moreover, silicon has an empty d orbital to accommodate the electron pair from a base as well, although it is receiving this lone pair from fluorine also. But silicon is a very accommodating species which was not valid for case of boron. So who will be the strongest Lewis acid? SiF4. So never commit this mistake of misjudging with boron family. So moving ahead. So moving forward, applying the applications of back bonding further in nitrogen and oxygen family, because this methylamine and silylamine case hybridization and shape already came in JEE Mains, I guess 2019. But I have included silyl phosphine also. We'll see how and we'll see why to move one step ahead. Now, first, let us discuss what is their hybridization. Sir, this is simply nitrogen. Carbon do not have any empty d orbital. So here I will be having no back bonding. First thing. Second thing, sir, simply I can say hybridization is sp3. Now, coming to amine silicon bond as in silylamines, sir, here we have vacant 3D. Sir, this lone pair of nitrogen will definitely try to do a back bonding. So there will be a 2p 3D back bonding. So here we will definitely see back bonding. Sir, if back bonding is seen, then this nitrogen lone pair will not be there. Yes, so its hybridization will change and it will convert. What we have learned is it will convert to a structure like this. Simple. Okay, sir, this much we know. With a partial double bond character, so bond order is definitely increased. So what can you say about the hybridization of this nitrogen? It is not as per this structure, it will be as per this structure, and therefore hybridization will be sp2 and this bond angle will be close to 120 degree. Moving ahead, sir, what about phosphorus? Now remember, here also we are having this empty 3D orbitals of silicon. But phosphorus, the charge density of phosphorus, these lone pair are present in a large sized phosphorus atom. So when we speak of donation of electron via back bonding, those electrons has to be quite localized. The charge density of that particular atom, that particular species, to give the electron needs to be high. If I have higher density of charge, then only the charge will flow, because phosphorus is a third period element, so its polarization, its charge density is not that high. So make this thing a very important point to note, that back bonding is mostly observed only for second period elements because their charge density is quite high. So here there will be no back bonding. Here we will be having no back bonding because phosphorus is a large third period element. Now I'm making a note of this so that you always remember this. Although I've added this option for you because JEE has only asked question regarding them, but a very probable concept which you should know, a block study. Now, so sir, there will be no hydrogen bonding, there will be no back bonding. Yes. Now, what we have already known is, what can you say about the hybridization? Sir, it is phosphorus. So Drago said that it will not even undergo hybridization because the bond angle which came out for such cases were approximately close to 90 degrees. So this also has an application of Drago's rule, which said that the phosphorus is having no hybridization. Now, after remembering and recollecting all those facts and logics that we have learned, let us now compare their basic nature. Sir, what about base? Sir, this is not getting, the lone pair is not associating in back bonding. The lone pair is not associating in back bonding, so definitely available for donation. But here, lone pair is not present, sir. It is donated for via back bonding. So because lone pair is not at all present, so obviously this nitrogen will be the least basic among the three. So which option is okay? This is least and this is least. So B can A is wrong, C is wrong. So I can have only B and C. Now this will be least basic. Perfect, sir. Now what can you say about methylamine and silyl phosphine? The silicon phosphorus bond. Sir, because it is not undergoing any hybridization, this phosphorus, as per Drago's rule, so percentage S character will be 100%, because this will be Drago's rule. This will be in present in pure atomic orbital. More be the S character, more is the electronegativity. So this phosphorus will try to keep this electron to itself. And this nitrogen, which is having lone pair, it is containing this lone pair in a sp3 hybridized orbital, where percentage S character will be 25%. So more is the S character, more is the electronegativity. So this will be least basic, and most basic will be methylamine, and this will be least basic. So B will be your answer. A very beautiful application of many concepts of back bonding, also Drago's rule also. Moving ahead. Now, discussing some more examples of back bonding. Now this is, let us draw the structure. Okay, sir. CH3, this is nitrogen. Obviously there will be a lone pair, then a double bond C, because carbon always forms tetravalent structure. So this will be the structure of this. Sir, can we have any back bonding? No, because this lone pair wants to go, but it will go where? There is no empty orbital. So what can you say about this bond angle? Sir, this is a bent molecule. What will be the geometry? Trigonal, planar. But because this is lone pair, so this angle will be less than 120 degree, but of the range of 120 degree, but obviously lesser than that, because this lone pair will repel. Now, sir, what can you say about? Sir, now because silicon is consisting of those empty orbitals which can be accommodated by the lone pair of nitrogen. So here you will again have your case of this 2p, this electron present in 2p orbital, or the hybridized orbital, because if you will say, what you will say to the hybridization of this nitrogen, this is sp2. So this lone pair of electron will try to do a back bonding with the empty 3d orbital of silicon. So it will be a 2p 3d back bonding, and because of this back bonding, this lone pair is not available. If it is not available, then it will have a structure that there is a single bond, but a double bond, a coordinate bond is formed between Si and nitrogen. So can you comment about the hybridization of this nitrogen? Yes, sir. Because lone pair is not present, so now steric number is just 2 because of 2 sigma bonds. So here the hybridization of nitrogen has turned to sp hybridization. This bond angle has turned to 180 degree. Now, make note of this thing, a very important fact, that this 2p3d back bonding, is forcing the structure of molecule from an angle of 120 degree to 180 degree. So there's a huge change, a change of 60 degree angle that is taking place. But in nature, when we have done spectroscopy, we found that yes, it was attaining somewhat linear geometry, and there, because it was attaining linear geometry, so this back bonding was applicable. But once the extent of overlapping, this is 2p overlapping is most effective. We already know that more effective is the overlapping, stronger is the bond. Stronger is the bond, then only I can bend any molecule as per my wish. This 2p3d has definitely given us such an effect that this molecule has somewhat acquired a linear geometry. But obviously in nature, you always find some exceptions. Now, this exception, for those who are starting from zero, can leave, but I am giving you this very beautiful case as well. Now, I have this germanium hydride GeH3 bonded with this nitrogen, and this nitrogen will also have its lone pair, double bonded C, double bonded O. When we are obviously, I'm not denying to the fact that this 2p and germanium also has D, but the D orbital for germanium will be 4D. So because energy difference has increased, so this 2p3d back bonding will be present, but it will not be that effective, which can change the bond angle from 120 degree to 180 degree. So here, because through spectroscopy I know, and therefore I'm telling you this, that because of this weak overlap, because of this weak overlap, why the overlap is weak? Because the energy difference between the combining atoms are large enough. So this overlapping will not be that effective. So will not be that effective to do what? To change the bond angle from 120 degree to 180 degree. And that's why in case of this germanium hydride bonded with this nitrogen, we say that there is no case of back bonding, but this is obviously a fact which we should have to keep in mind. Now we are saying no back bonding. So sir, in germanium, back bonding can never take place. I'm saying it will be taking place weekly. But why? I've given a statement that no back bonding is considered because the bond angle has to change from 120 degree to 180 degree. If you are demanding some slight, if you are expecting that you weak person, get me a glass of water, a glass of water can be brought to you. But if you'll ask this weak person, you weak person, get me a Mercedes car, he cannot buy a Mercedes car, he's weak. So he cannot bring about such a huge change. But small changes, I'm saying back bonding will take place, but here it is not mentioned theoretically because the impact is not created. The hybridization must not be changing because a bond angle is not changing from 120 degree to 180 degree. But if I just need a glass of water, for example, let's say we are supposed, and question is asking here, the question is asking what is hybridization of nitrogen. So we will say it is 2 bond pair and 1 lone pair, because this lone pair is not associated with back bonding because back bonding is not impactful. So here steric number is 3, so hybridization will be sp2, not sp. Here in the previous case we said that it was sp, but here we are saying it is sp2. But coming to this germanium case with nitrogen itself, nitrogen lone pair GEH3, GEH3, GEH3. Now here I'm saying this lone pair from 2p will definitely go to 4d. Why I'm saying this? Because this bond angle, if we are not considering this hybridization, then we'll say this bond angle, this theta, is obviously less than 109 degree 28 minute. Let's say if we consider that back bonding, although weak, but back bonding is taking place, so this lone pair is not existing, then this molecule will attain a shape of nitrogen single bonded with GEH3, GEH3, GEH3. And because I'm taking a case of back bonding, so what I will do here, so back bonding, this is also partial double bond because of back bonding, partial double bond because of back bonding, partial double bond because of back bonding. So I'm considering back bonding over here. Why? Because here, if back bonding, if at all it is taking place, the bond angle will be reaching somewhere around 120 degree. So from somewhere around 109 degree reaching to 109 degree reaching to 120 degree just requires an angle change of somewhere around 11 degree. 11 degree is not that big number, but getting a difference of 60 degree is a huge number. So creating an impact of 60 degree requires you to be very, very strong. And this back bonding, because of ineffective overlapping, it's not that strong, and hence over here we are considering no back bonding, so hybridization is sp2 only. But this bond angle is getting changed, and therefore theoretically we are also saying that you are getting hybridized. So here hybridization of nitrogen will be termed as sp2 and it will not be sp3, because here we are considering case of back bonding. Now this may, obviously you will think, sir, we have to now then remember this. So that's why I said this example you can skip for JEE mains, but a very good logic. Moving ahead now. Okay, sir, then now do we have to remember some exceptions? Yes, This NCl3 exception you definitely have to remember because it is block chemistry almost mentioned in NCRT of class 12th p block elements. Now NCl3 also back bonding is not considered. Why? Because actually its nature is, obviously this is also a fact, that its nature is quite unstable and explosive. Also, if you applied some common sense also, like as per VSEPR theory, what we will feel, what is the structure of NCl3, sir? 3 bond pair, a lone pair, hybridization of nitrogen will be sp3, shape will be trigonal pyramidal. Sir, you are not considering case of back bonding because this lone pair from 2p, sir, here it has to go to empty 3d of chlorine. So, sir, this 2p 3d overlapping is quite effective. You said that, then why it is not? Uh, just go to a very simple logic. What is the electronegativity of nitrogen on Pauling scale? 3.0. Of chlorine 3.0. So if I am equally electronegative as you are, then when electronegativity difference, so here I am saying no back bonding, and the reason I'm giving is because electronegativity difference is not sufficient. Because if I can give electron to you, then you should have that much of capacity to receive the electrons that I'm furnishing. Moreover, this fact also you should learn that NCl3 is a very unstable and explosive molecule. So if I would be stable, back bonding will tend to increase the bond order. If bond order increase, then bond becomes strong. If bond is strong, then this molecule should exist in nature. So because we know theoretically and statistically, practically, that in nature this does not exist, and not even this, all the remaining halides similarly is for the case of NBr3, Ni3. So these molecules also we consider no back bonding because they are broken very easily. So the bond is weak. So why will you predict a theory which is increasing their bond order? So here also we consider that back bonding is not taking place. So their hybridization will strictly be sp3. What about the bond angle? So this bond angle will be close to, because this chlorine atom is also large enough. This is a lone pair. So this will be close to whatever tetrahedral angle 109 degree 20, approximately that, because these chlorine will also repel. You'll say, sir, because of lone pair this will decrease. These chlorine will also, because they're steric crowding, they are large atoms, so they cannot come much closer. So this bond angle will be somewhere around 109 degree 28 minutes. Now this bond angle question I'm again telling you now. See, because NCl3 we just did, sir, no hybridization, no back bonding. So bond angle somewhere around 109 degree. Okay. Ammonia water we already know, we have done through VSEPR theory. In water there are two lone pairs. In ammonia there is one lone pair. So this angle we already know also that this is 107 degree and this is 104 degree. So this is larger. So option B is def. But this is not a JEE question. I have included some questions together. So this is correct angle, bond angle difference. Now, because students know this through NCRT, so such type of questions, they directly, sir, this is pyramidal, this is bent, so this will be more. This NCl3, we know it has a bond angle of 109 degree. What about OCl2? So that's why I'm comparing OCl2 and water also for you. Water we definitely know because of presence of lone pair. I've again drawn it over here. This angle is somewhere around 104.5 degree. We know that lone pair repulsion is there. So this angle will be much lesser than 109 degree 28 minutes. Okay, sir. Let us go to the application of back bonding in oxygen family, because oxygen is also small size second period element. It can also coordinate its lone pair, because second period elements can do effective back bonding if at all the other combining atom has got empty orbitals. So here the lone pair on oxygen atom, one of the lone pair can easily be back bonded this from 2p to 3d. So this will be a case of back bonding. So here back bonding will take place. So because of back bonding, the bond order of Cl bond O will increase. Sir, if bond order is increased, so bond length will decrease. If bond length decreases, then bond angle, this theta, because the pi cloud will have more repulsion, so the bond angle will rise. So among OCl2 and water, although you will see through VSEPR theory the structure is same, but this has attained a partial double bond character. So while drawing resonating structure, this will be partially double, this will be partially doubled. So partially doubled has more electron cloud, so it will repel. Partially double has more electron cloud, so as bond order increases, bond length decreases, and as bond length decreases, relationship with bond angle, sir, when bond length, they are inversely proportional. So because bond length is decreasing, bond angle will increase, so it will have an increased bond angle. I'm giving you a value also. This is somewhere around 111 degree. So we have to learn them. I've given you the logic behind it. Now moving ahead, a very beautiful examples by the way. So quickly moving to this bridge bonding, which is generally shown by Lewis acids, because Lewis acid has a character of gaining electrons. So why wait for another species? So like in case of boron hydride, BH3 in nature does not exist as a monomer because it is electron deficient. So rather it forms a 3-centered, as in 3 nucleus, and a 2 electron bond by sharing of these 2 electrons, because this will at least satisfy some of the electron requirement of the electron deficient second period boron atom. Now because the electron, I mean here boron always has its electron, but this boron electron is sometimes shared at the top side, sometimes shared with the bottom side. So because electron density of boron is sometimes at the top, sometimes at the bottom, so it is not always present, but this hydrogen always contains its electron. So how many centers you can see who are attracted to each other? 3. So this is a 3-centered yet a 2 electron bond, because specifically these 2 pink colored electrons are actually seen in the formation of this bond. And similarly in the downside you can again have this banana formation. Why this electron orbital lobe is increasing at case of hydrogen? Because this hydrogen always has its electron, but for boron sometimes the electron density is upside and sometimes it is downside. So because of the shape of such an orbital, this 3-centered 2 electron bond is also termed as a banana bond or simply banana bonding. And with this, at least this boron hydride can satisfy a bit of its Lewis acidic nature. So if someone asks you what is the hybridization of BH3, then we should know that BH3 in nature does not exist independently. It exists as a dimer of B2H6. So for BH3, the hybridization was sp2, but it is not even existing in nature. It exists as a dimer of B2H6, and therefore this hybridization becomes sp3. Now, if BH3 would be existing independently, its molecule would be planar, but because its hybridization is sp3, so this is a non-planar molecule. Now you can obviously see that these 4 hydrogens are the terminal hydrogens because they are lying on the plane, but this one hydrogen and this another hydrogen that is forming the bridge between these 2 molecules are termed as bridge hydrogens. So I just circle these 2 bridged hydrogens for you. So these 2 hydrogens becomes the bridged hydrogens, while these 4 hydrogens are the terminal hydrogens. These terminal hydrogens are lying on a plane, but like this is a plane, this will be one hydrogen and that will be another hydrogen. So these are the bridging hydrogens forming the 3-center 2-electron bond. Obviously it is electron deficient bond, but at least some of the Lewis acidic nature of boron is satisfied. So B2H6 in nature exists as a dimer. Similarly, we can also find some bridge which are electron surplus. For example, this 3-centered, there are 3 nucleuses, but they are bonded with each other using 4 electrons. Sir, like in case of aluminum chloride, AlCl3 in nature also exists as a dimer. But the bridge that is formed over here is because of the excess of electron. Now, AlCl3 independently is a Lewis acid. AlCl3 independently is a Lewis acid, but because it is a Lewis acid, why it will remain in Lewis acid in form of its Lewis acidic nature with that deficiency in nature? So it will make some jugaad, it will make some trial, some efforts from its side, and what effort does it land up with? That it also exists as a dimer in order to satisfy its electron deficiency. How it is getting satisfied? The lone pair of chlorine in the 3D, the lone pair of chlorine must be present in its 3p, okay, 3p in its third shell. So the lone pair, okay, 3p, the lone pair will be present in 3p of chlorine. So the lone pair present in the 3p orbitals of chlorine are coordinated to the 3p. So it is a very efficient 3p overlap. So this is forming a sigma bond, and it is also not a pi bond, it is a clear cut sigma bond. So because of the formation of this pi bond, how many centers here you can see? I guess now it is also clearly visible to all of us that, okay, let me change the color. This is a, okay, now there is no electron deficiency. What? So I'm not drawing such a banana bond, because over here hydrogen is always having electron density which is decreasing in case of boron. So a banana type of bond form will take place only in case of 3-center 2-electron bond. But over here we can just clearly see that there are 3 centers, and how many electrons? Just count them. These 2 electrons of aluminum chlorine, and over there aluminum has not contributing some electrons to this bond formation, but this lone pair is getting coordinated. So a 1 2 3 4, so 4 electron and a 3 centers, 3 nucleuses are attracted via use of 4 electrons. So this becomes a 3-centered 4-electron bond, and therefore AlCl3 in nature also exists as a dimer. Now, what can you say about the hybridization of this aluminum? Sir, it is also very simple. Hybridization will be, the hybridization of aluminum will be sp3. Its shape will be tetrahedral. So will this molecule be a planar molecule? No, this molecule, this existing as a dimer, will be a non-planar molecule, because geometry, shape of an sp3 hybridized system is tetrahedral. Moving forward, now some people ask, sir, B2H6 which you have given, they exist in nature in order to satisfy, but the level with which the electron deficiency is satisfied is not appreciable. I mean, there is still 3 electrons, there is still deficiency. That's why this orbital lobe is getting thinner. So whenever, although BH3 exists as a dimer, but whenever some bases are present, then it will react with those bases in order to completely fill its stomach, fill its desire of attaining electron, fill its desire of being a Lewis acid. So if I'm a Lewis acid, I will definitely gain electron. That was a jugaad, that was a routine, very minute situation that I was bringing in my home by being a dimer. But if I'm supplied with electron, I will definitely entertain those incoming electrons. So the dissociation of B2H6 is also decided by what type of base is approaching to my home, to my place, to the central atom boron. If the base is a very large base, a macroscopic base like tetrahydrofuran, dimethyl sulfide, sulfur is a third period element, hydride ion, we very well know it's a very large anion. So these are all are macroscopic, as in large bases. So what does this large base? A large base require more space. So they only one of the bases can approach this boron atom. Obviously, they will try to give electron and boron will try to gain their electron. But in such cases, in case of approach of large bases, the dissociation, the cleavage of this B2H6 takes place as symmetrically, as in one BH3 takes this Lewis base, another BH3 takes another Lewis base. So what type of bond is formed? A symmetrical cleavage takes place, and BH3 takes away electron from other large bases and satisfy themselves. So this is just simple acid base reaction forming a addition compound called adduct. But if the bases are chotu, they are very small. Small bases, sir, can easily get inside. I mean, more than one base can attack at the same point of time. But for that, boron, who is requiring those electrons, need to have vacant orbitals. Now, I've taken that time because you also think of that time. Boron is a second period element. How many orbitals it has? Only 4. 1 2s orbital and 3 2p orbitals. So in order to entertain more number of bases, because I am a Lewis base, boron is a Lewis base wanting and in deficiency of electrons, so it will want to entertain all the possible bases that can come to boron itself. So in such cases, when microscopic as in small bases like ammonia, types of 1 degree, 2 degree, 3 degree, 3 degree I mean is large enough, so 1 degree, 2 degree, and cyanide ion, because all these constituent elements are second period elements, so the base that they'll form will be of smaller size. So these smaller bases can attack more than one in number. For that, boron needs empty orbital there. So in such cases, unsymmetrical cleavage takes place. For example, this white color B becomes a boron cation BH2 plus, because now this BH2 plus will have two unpaired, two empty orbitals, and in those empty orbitals, more than one, because I'm having two empty orbitals, so I can receive electrons from two different bases at the same point of time. So in such cases, unsymmetrical cleavage will take place. This boron will give away its hydrogen and will say to this boron, you take my hydrogen, because I'm having excess of supply from the backside. So in such cases, unsymmetrical cleavage of this B2H6 takes place. A very important logic you should keep in mind. Now, a few questions by summing all the JEE questions that you might encounter in your paper. A very famous question is, BCl3 exists in nature but AlCl3 do not. Can you give me a reason? Sir, we have already done it. Now this is becoming quite easy for us. Now, if we'll just have a look at BCl3, we definitely know that because boron is a Lewis acid, so sir, what can take place? Sir, back bonding. So sometimes this will give, sometimes this will give, sometimes this will. So because of presence of back bonding, this boron chloride is satisfied. So it will exist in nature because its electron deficiencies in-house catered, satisfied. But in case of AlCl3, if you say, sir, it can also have a back bonding. No, because we have done so many cases of back bonding just now. So you can very well see the lone pair on chlorine are a 3p orbital lone pair. When they are donated to aluminium, the size of aluminium back bonding predominantly takes place with second period elements because their size is small, as we have seen before also. So here, this back bonding will not be that efficient, because in order to have effective and efficient back bonding, I need at least, among the two, I need at least one atom to be belonging to a second period element, because second period elements are that electronegative that they can entertain that incoming electron. The extent, this will be a 2p, and for boron it will also be a, okay, this will be a 3p. I'm sorry, for chlorine it will be 3p, but it is getting into a very electronegative atom. So electronegativity difference is large enough. Remember, in case of nitrogen and chlorine, we didn't accepted that back bonding because their electronegativity difference was not large enough. So in order to have effective back bonding, we always need at least one atom to be of second period, because it is an electronegative atom. It is an atom who can have effective overlap. So In AlCl3, no back bonding is seen. No back bonding is observed, and because there is no back bonding, so in nature it always tries to satisfy its electron deficiency by becoming a dimer. And BCl3, why not existing as a dimer? Because its in-house electron deficiency has been overcome by effect of back bonding. Now, one more block chemistry logic. So I've made a beautiful picture for you. Some other examples of three-centered 4-electron bond, like in case of AlCl3. Now, people say only AlCl3 exists as dimer. There is a very beautiful example given in NCERT for boron also. No, for beryllium also. Now, if someone asks you what is shape and hybridization of BeCl2, then you should, this is a factual thing also and very beautiful concept also. BeCl2 in gaseous state, but when gaseous at temperature, at very high temperatures, somewhere around more than 1200 Kelvin. So BeCl2 at a temperature of around 1200 Kelvin, it exists as what you know through your VSEPR theory, sir. Beryllium has 2 electrons, will form 2 bonds, so 2 bond pairs, so shape will be linear, hybridization will be sp, and it will have a bond angle of 180 degree. Simple. Now, but if temperature is reduced, ultimately BeCl2 in beryllium also, it is a second period element, beryllium. Lewis acidic, for second period element, octet has to be complete because they are very electronegative in their respective period. So this BeCl2, even in gaseous state, at a temperature below 1200 Kelvin. So even in gaseous state, but at a temperature below 200 Kelvin, now it has got that temperature also. Even in gaseous state, it will also exist as a dimer. How? This is one BeCl2. This is another BeCl2. It will also have an in-house receive of electron, and the chlorine having excess of lone pair in the 3p orbital will coordinate to this beryllium. Its chlorine will coordinate to this beryllium. Now just have a look at this bond. So this is not a banana bond. There is no electron deficiency. There are 2 electrons plus 2 electrons. So it is a 4-electron 2-centered bond, just like in case of AlCl3. So BeCl2 also exists as a dimer even in gaseous state, but temperature should be below 1200 Kelvin, because if you increase the temperature, then the molecules will go far apart from each other, because then this coordinate bond also gets broken, but at a temperature above 1200 Kelvin. And if at temperature below 1200 Kelvin, if someone asks you what is its hybridization, sir, it is sp2. Here it was linear, here it is trigonal planar. And if you still go to solid state, in solid state, BeCl2 molecules approach each other so closely because still octet of beryllium is not complete. After this, getting lone pair of this chlorine also, it has reached to 6 electrons in its valence shell. So in solid state, if one BeCl2 is approached by another BeCl2, it will say, come one more. So you can beautifully see this picture. When lot of BeCl2 are closer to each other, that is in solid state, they will be getting lone pair of chlorine from this side also and from this side also. So can you see what is the hybridization of beryllium chloride BeCl2 in solid state? It is sp3 and forms a tetrahedral solid. A very beautiful example. One more example, ICl3. Now in gaseous state, you do not have to remember temperature for ICl3, but that example is given in NCERT of BeCl2. ICl3 in gaseous state exists as what VSEPR theory we know, that it exists as a bent T shape with sp3d hybridization, because geometry is trigonal bipyramidal. So because of lone pairs, it will acquire a bent T shape. But in solid state, because now this is a fact that you should know, that in solid state, iodine also receives electron from chlorine, although iodine is not a Lewis acid. So this is a halogen example. As a dimer, it becomes I2Cl6. So this I2Cl6 has been asked by JEE, so I'm mentioning it separately, because here also this is also coming to a case of this becomes a 3-centered 4 electrons. So where are 4 electrons? 1, 2, and the coordinate bond 3, 4. So ICl3 also in solid state exists as a dimer. And because the geometry will be octahedral but lone pair, because it will be containing lone pair, so lone pair will be opposite, so the shape will be square planar. So this whole molecule will be a planar geometry with sp3d2 hybridization, a very beautiful application of VSEPR theory and a fact of halogen family. Moving ahead, so finally and ultimately coming to the most famous and probably most intermolecular forces of attraction will be, I mean, a very small topic will be the last topic, but almost the last topic of chemical bonding and most loved by JEE, a very scoring topic also, the molecular orbital theory. Now, first of all, why it is needed? Sir, we know why atoms exist as molecule. VBT told us atoms exist in form of molecule because the electron waves, as in their orbitals, overlap. And why do they overlap? They overlap to pair their unpaired electrons. So what VBT mostly thought, because VBT was an outcome of quantum mechanical model of an atom. Quantum model, what is an orbital? Sir, electron, the probability of finding electron is orbital. How quantum theory has formulated electron to be an electron wave represented by wave function psi. So let's say two atoms A and B are combining, then VBT thought they will be combining constructively, but through wave mechanics, which you know through in your physics, two waves can interfere maybe in a constructive fashion and may also be in a destructive fashion when they are out of phase from each other. But this was accounted by molecular orbital theory. VBT just thought that when atomic orbitals interfere with each other, they always result in a bond formation. If they are out of phase, then they will not get into any type of orbital. But molecular orbital theory said that when two atomic orbitals interfere with each other, probability of both the cases exist. They can even do it in a best possible way, that is constructive interference, but they can even do that thing in a most destructive way, that is destructive interference. Now, sir, but why it is required? Why you are saying all this? Because when we started looking in atomic structure also we have learned this, but I'm using that knowledge and again telling you, by just knowing the number of unpaired electrons we can easily predict the magnetic nature of any species. So as per VBT, every atom forms a molecule to pair their unpaired electrons, and as per magnetic theory we know that if an atom contains all the paired electrons, then it should be diamagnetic, because if all of my electrons are paired, then I will be repelled by external magnetic field. Those are diamagnetic substance. People thought, okay, a scientist did this magnetic experiment on the most famous gas, oxygen, the gas which is responsible for the existence of every life. As per VBT, oxygen is forming a bond with oxygen, so it should be all paired molecule. It should be diamagnetic because all electrons are paired. But to the surprise to the scientific community, what they got is the magnetic nature of oxygen was paramagnetic. So everything was blown and bursted. So in order to, because oxygen is definitely paramagnetic, but then VBT failed. And if VBT failed, then everything around us we know as of now will be failing. So this independent theory of molecular or orbital theory was theoretically designed just as an add-on to VBT, which said that VBT, while saying this, when two atoms combine with each other, when atomic orbitals overlap with each other, you just add this principle in your head, then they do so as linear combination of atomic orbitals. So the principle of Lacau, LCAO, Lacau, linear combination of atomic orbitals. We very well know when these two atomic orbitals as an electron wave will interfere, they can do so in best possible way, constructive interference. They can even do so in the worst possible way when they are out of phase, that is destructive interference. So how many atomic orbitals are linearly combining? 2. So molecular orbital said that because linearly 2 atomic orbitals are combining, so after their combination, atoms will not come and they say this is my orbital. They said that after linearly combination of atomic orbitals, existence of atomic orbitals cease to exist. Now you will become a molecular orbital. Now we will not think of what participants were there. After participation, you have formed a company. What company you have formed? You have formed a molecule. So what now we will only talk of the molecular orbital. So post combination of atomic orbitals, molecular orbitals theory said that molecular orbitals are known to exist in nature. Now atomic orbitals you do not even think of. For example, let's say this atom is A, this atom is B. Atom as in having an unpaired electron. So electron will be designated by its wave function psi A. The other unpaired electron of another atom is designated with wave function psi B. When they are linearly combining, as we all know, combination of those electron orbitals will take place which are of equal energy. So let's say they have an energy of 20 rupees, for example. So in the company, 21 participant, 20 another participant. The company which they have formed, the molecule which they have formed has a total amount of how many rupees? 40 rupees. Energy cannot be created nor can be destroyed. So how much total rupees you have? 40. But after linear combination of atomic orbitals will have no existence in nature. What will be formed? Molecular orbitals. How many atomic orbitals participated? 2. So how many molecular orbitals will be formed? 2. One having lesser energy, one having higher energy. Sir, how this energy is coming? They brought some energies. Let's say 40 rupees they had. So this is having energy, let's say 10 rupees. And this is having an energy, let's say 30 rupees. Total energy is 40 only. Now, sir, but why this and its energy is less? Because when two atomic orbitals are overlapping in a constructive fashion, when the waves are in phase with each other, so it will result to a constructive interference. Now, for example, this A and B, you apply your wave logic. Sir, the amplitude will increase definitely. So if this is psi A, this is psi B, so this becomes psi A plus psi B. But through atomic structure also we know that what is actually orbital? Orbital is probability density, where probability density of finding electron is maximum, and instead of psi for probability density, what value we take? Sir, we are interested in psi square. So just do that mathematics. If resultant is psi A plus psi B, then square of psi A plus psi B will be, sir, A square plus B square plus 2AB. That means psi A square probability density of A plus probability density of B plus 2AB, 2 psi A psi B. Now, this simply means that when two atomic, for example, we are trying to picturize this through an example. When two s and s orbitals are overlapping with each other. Now, if they are in phase, remember s is the phase which s orbital have, they are all plus or all minus, hence use the similar color. So it may be plus or it may be all minus. This is not a charge. So when they are in same phase, let's say this is also positive phase, this is also positive phase. When they will interfere, then this will result to a constructive interference. So the bond formed will be a bonding molecular orbital. Now what is a bonding molecular orbital? When constructive interference of electron wave take place. Now you just look at the, now this was your participating atomic orbitals, and this becomes your molecular orbital. Now if you just check this molecular orbital, you will definitely find this common area. Whatever probability you had, it's still there. A had is still there, B had is still there. But the probability density has increased by a factor of 2 psi A psi B. This common region represents that probability of finding electron of both the electrons, because in covalent bond we say na that whatever is the overlapped area over there, the two electrons exist with opposite spin and hence they get stable. So mathematically also you can predict through this molecular orbital theory that this results to a constructive interference where probability density of finding electron is increased by a factor of twice of psi and psi b. If they are interfering in a destructive interference, so that means they are out of phase from each other. That means this minus is interfering with this plus. So obviously they would not like to be with each other. They will have a destructive interference. So this orbital, molecular orbital picture is showing you what? That this minus is getting far because electron does not want to have a destructive interference. This lobe is also turning away from that lobe. So this becomes whole plus, this becomes whole minus. So this becomes, but this will also, you cannot live your life by just thinking of all positive. If you have day in your life, obviously after 12 hours, you will get night. So this is the nature of life, that when two atomic orbitals overlap, they linearly combine. When we say of molecular orbital, we start using, instead of overlap, we say they are linearly combining. So when two atomic orbitals linearly combine, they form two molecular orbitals. One with constructive interference, one with destructive interference. Because when S and S combine with each other, what type of bond they form? Sir, sigma bond. So this becomes sigma 1s, because if the participating orbitals are 1s 1s, then this becomes sigma 1s. And if this 1s and 1s are combining, then they will do so in both these ways. So they'll form a bonding molecular orbital of lesser energy, and when they are doing this in a destructive interference, they will form an anti-bonding molecular orbital represented by this asterisk sign. So, but they are still doing an head-on. So this is a sigma bond, but so this molecular orbital is designated as sigma asterisk, done by whom? 1s. So how many atomic orbital participated? 2. How many molecular orbitals we formed? 2. One known as the bonding molecular orbital of lower energy, because energy is low, so it is highly stable. Now, other one is anti-bonding molecular orbital, having higher energy formed by destructive interference. Now, sir, why there is a gap? If you square this value, resultant, if resultant is psi a minus psi b, if you square, because orbital is probability density, so just what is square of a minus b? Psi square, psi a square plus psi b square minus, that means probability has to reduce, probability has to decrease. That's why you get this empty place. And the region where probability of finding electron is 0 becomes your nodal plane. So we are dealing with everything over here. So what is the number of nodal plane which is contained by a sigma asterisk 1s molecular orbital? Sir, one nodal plane. How many nodal plane sigma 1s has? 0. So it has one nodal plane, it has 0 nodal plane. Now, because its energy is less, it is more stable. So whenever we have to fill the electron in a molecule, now molecules will be filled with the electrons. How they will be filled? All the rules of atomic structure that we have read, that is Aufbau rule, Hund's rule of maximum multiplicity. Aufbau says that orbital is filled first, which is of lower energy. Hund's rule says you will only pair when orbitals that are degenerate are singly filled. Pauli says you will fill 2 electrons in one orbital, so do everything the same. But now for molecular orbital, because when atom forms a molecule, now who all are existing in nature? Only the molecular orbitals. So who will be filled? Those molecular orbitals. So This molecular orbital, which is of lower energy, the bonding molecular orbital, I'm saying for the last time, will be highly occupied. So these bonding molecular orbitals are also known as highly occupied molecular orbitals, the HOMO, highly occupied molecular orbitals. And because the anti-bonding molecular orbitals are of higher energy, so they will always be filled once they are filled. So they are least unoccupied molecular orbital, although they will be occupied. When they will be occupied? After filling of HOMO, that is highly occupied molecular orbitals. So bonding molecular orbitals are also termed as HOMO orbitals. Anti-bonding molecular orbitals are also termed as LUMO orbitals. Now, sir, give us another type of Lakaw linear combination, because SS we saw two S combined, two molecular orbitals formed. So similarly, P can also combine. Yes. NCRT always assumes Z axis to be the internuclear axis. So out of PX, PY and PZ, who will form the sigma bond? Because we are assuming that two atoms are combining along the internuclear axis, which is Z axis. So let us have a PP overlapping as well. Let us see, because after overlapping, who will be formed? Molecular orbital. Atomic orbital will cease to exist. They will now do not exist. Molecular orbital will exist. Okay. So let us picturize those molecular orbitals. Okay. So sir, you said this is molecular axis, Z axis. Okay, perfect. This is molecular axis, Z axis. Okay. When p orbitals are approaching each other, again sir, they will do so best possible way and worst possible way. We will consider both the ways. So you tell me this picture, sir. If this is in phase, the electron lobes are, I am intentionally giving you a color, but in question paper what you see is this plus and this plus. So this will minus, this will minus. So you tell me what type of interference it is showing, sir. Constructive interference. So overlapped area will be beautiful. The unpaired electrons, the paired electrons will be having so much of area. All the logics of VBT is still applied, but they'll do so in a best possible way also, and they will do so in the worst possible way also. And this plus will not at all like this minus, because they are out of phase, so they'll have a destructive interference. So when this plus is approaching this minus, it will fall back, and probability of finding electron will increase in this lobe, because these plus do not wish to get interfere with that minus. So this lobe will get shortened up, because I do not like you and I will try to be over here. So this lobe will increase and this will decrease, because probability of finding electron has increased this side. So this represents a destructive interference. What type of overlapping PP will have along Z axis? Let's say this is Z axis. Sir, PP will have a sigma overlapping. So this molecular orbital I will term as sigma. But who is making this sigma bond? The 2pz orbital. So this molecular orbital will be designated as sigma 2pz molecular orbital. This will be a molecular orbital. Obviously its energy will be less. Now if it is having a destructive interference, that is, this is plus, this is minus. So but destructive interference of what? Of p were approaching each other in what sense? To do a sigma overlap. So this molecular orbital will be termed as sigma estic 2p z. Now which is of low energy? Sir, this is of low energy. Which is of, this is of high energy. Now again, what is nodal plane? Sir, where probability of finding electron is 0. Can you, what is the number of nodal plane for sigma 2pz? Sir, easy. This is one nodal plane, this is one nodal plane. So nodal plane for sigma 2pz is 2. Nodal plane for sigma astic 2pz are clearly visible, 1, 2, 3. So nodal plane becomes 3 in number. Coming to, sir, if I'm having unpaired electron, I will be pairing by head-on overlapping. But if I'm having more unpaired electron, then I'll have a lateral overlapping, pi overlapping. But after overlapping, molecular orbitals are formed. How many molecular orbitals are formed, sir? number of participating orbitals becomes equal to number of formed molecular orbitals. So I can also have a pi bond. If I'm laterally overlapping also, I will again do that in constructive interference. Plus plus will form a plus, large plus, minus minus will form a large minus. So obviously you can see this is a constructive interference. So it becomes pi 2px or even pi 2py, because we consider zx the molecular axis. So it can be pi 2px, pi 2py, or pi 2p anything. Now, so what type of molecular orbital it has formed, sir? Again, it is bonding molecular orbital, energy less. If this plus is interfering with this minus, they will not like each other, so they'll fall apart, fall away from each other. So this becomes, this type of molecular orbital becomes pi-estic 2px or pi-estic 2py. Now, how many nodal plane this has, sir? One nodal plane. How many nodal plane this has, sir? Clearly visible, two nodal planes. These are all very famous points. Every slide over here is a JEE mains question for you. So please and please do this. Listen to this. If you are feeling that you know these things but still need revision, you can even do it in 2x speed. But at least revise all these things. Although with me, use me with a 2x of speed. It will be very fast for you and you will be able to get and remember everything very easily. Now, one more thing. While discussing atomic orbitals only, we have also classified atomic orbitals as Gerade and Ungerade. Gerade were those which were symmetrical about the center. Ungerade were those which were not symmetrical. So let us categorize these molecular orbitals also with the designation of Gerade and Ungerade. Okay, sir, let us do it. Now, can you tell me, let's say this is a center. Let's say I'm going this much distance this side and this much distance this side. I'm still here seeing the plus, seeing the plus. So because it is symmetric with respect to the center, so sigma 1s becomes a Gerade molecular orbital. What about this? Sir, from the center, if I'm moving x distance, I'm having a positive notion, but here I'm having a negative notion. So it is not symmetrical about the center. So it becomes an Gerade molecular orbital. Remember, Gerade and Ungerade. Now, further, obviously, we can see when sigma bond is taking place, when head-on overlapping is taking place. Who won in case of S? Sigma. Let us see. Sir, let's say this is the center. I've moved this distance. Again, this red lobe, that is say plus. Sir, again that plus. So I'm symmetric about the center. Let's say I move some more distance. So I reach some minus, walk the same distance this side. So the same minus. Obviously, this is also symmetric about the center. So this is when I'm having a head-on overlapping. Just remember this as this observation. When I'm having a head-on overlapping, bonding molecular orbitals are Gerade and anti-bonding molecular orbitals are Ungerade. But this is for head-on overlapping. Let us jump to sidewise overlapping. Opposite is true. See, this is the center. I'm moving some distance, let's say 45 degree, I'm getting a minus. Again moving the same distance opposite side, I'm again getting a minus. So this is a symmetry with respect to center. So this becomes a Gerade molecular orbital. So for pi bonding, who becomes a Gerade molecular orbital? Anti-bonding molecular orbital. And pi bonding molecular orbital, sir, from the center, I moved to the top, I got a plus. I moved to the same distance at the bottom, sir, I got a minus. I'm not getting the same environment. That means it is Ungerade. Very important conclusion. Directly you will get questions. Now, sir, okay. Now we know. Electron of molecules will be filled in molecular orbital. But sir, how they will be filled? Using Aufbau, Pauli, and Hund's rule of maximum multiplicity. Let us work out all those electronic configurations and see why we have started this at first place. Because we said As per VBT, every atom forms bond with another atom to do what? To pair their unpaired electrons. So as per VBT, every molecule should have all paired electrons. And if molecules are having all paired electrons, they are always diamagnetic, because diamagnetic species are those which have all paired electrons. If any species has unpaired electrons, then only it can become paramagnetic. That is, you can be attracted by external magnetic field. But oxygen, to a surprise, was a paramagnetic species. But VBT said that all atoms are paired. So this is the basic reason we have started, the scientist community have started with molecular orbital theory. So let us first do that electronic configuration and see whether oxygen is paramagnetic or not. Then only our purpose of learning MOT will be solved. Although our purpose is, we get lot many questions of this energy level diagram. So directly jumping to the energy level diagram. Now, sir, hydrogen. How many electrons hydrogen have? 1. But as a molecule, I have 2. So 1 electron will be brought by one hydrogen atom. 1 electron will be brought by another hydrogen atom. So how many total electrons I have? 2. But now I will not think of these atomic orbitals. You go to hell. When 2 atomic orbitals linearly combine, what are formed? Molecular orbitals. How many? 2. One is sigma 1s, another one is sigma 2s. Its energy is less, its energy is more. As per Aufbau rule, who will be filled first? The orbital which is of lesser energy. So who will be filled first? Sigma 1s. How many electrons we have? 2. So first electron will go over here. Because this energy level has only one orbital, so it is singly filled. So what does Pauli say? An orbital can have maximum 2 electrons. So what is the electronic configuration of hydrogen molecule? So for hydrogen molecule, the electronic configuration becomes sigma 1s2. Simple. Now, sir, what about its bond order, bond length, its energy, the magnetic behavior? VBT also helped us to calculate these stuff. How? VBT said you can simply calculate bond order of any molecule, but again, a caution. Whatever VBT is there, VBT has been designed for everybody. But for JEE and for NCRT syllabus, even advanced, VBT for us in our syllabus is valid for homonuclear diatomic molecules, and that too we have to learn this VBT only till fluorine. Although we make it for neon, but what VBT is there in our syllabus, what amount of content of VBT we need to know is only till F2. Although we can also do it for neon, but beyond neon we will not go. Even JEE Advanced do not want you to go. Moving ahead. So our VBT is only valid for homonuclear diatomic molecules. Now, so starting with the simplest molecule, hydrogen. Now, how to calculate bond order? NB minus Na upon 2. What is NB? Number of electrons in bonding molecular orbital, the stable one. What is Na? Number of electrons in anti-bonding molecular orbitals, the higher energy and less stable one. Take the difference, divided by 2, you will get your bond order. If a molecule has a bond order which is positive, then obviously that molecule will exist in nature. That molecule will be stable. If this bond order is coming out to be negative or maybe 0, then this apply that the molecule will not exist in nature. Because in nature, even inert gases were known to form compounds. So do VBT has this reason why you cannot find helium as a molecule? MOT will now give you a reason. First, let us check for hydrogen. We know how to calculate bond order. We know how to justify that whether a molecule is stable or not. Yes, by calculating its bond order. So let us do it for hydrogen. Now, so for hydrogen, bond order will be number of bonding electrons are 2. Number of anti-bonding are 0 upon 2. So bond order of hydrogen is 1. Through VBT also we know H bond H has a bond order of 1. Through MOT also we know. What can you comment about its magnetic behavior? Sir, because it has all paired electrons, so its magnetic behavior will be diamagnetic. Again telling you that also. What is a diamagnetic substance? Where unpaired electrons must be absent. It should have all paired electrons. And if I have unpaired electrons, I will be paramagnetic, and paramagnetic substances are attracted by magnetic field. what is my extent of getting attracted to that magnetic field can be calculated by the term of magnetic moment. We already know this through atomic structure. How to calculate magnetic moment? Under root of n into n plus 2, where n is number of unpaired electrons. The unit becomes Bohr magneton. All these stuff are loved by JEE. So directly giving you that. Now, again coming to hydrogen. Sir, what is its magnetic behavior? Obviously diamagnetic. Why? Because all paired electrons. It has no unpaired electrons. Now, bond order or bond length. Sir, why? What is bond length and bond energy? Can we calculate this value also? No. We cannot calculate this value, but you can always have a comparison. This we have done for whom? Sir, this we have done for hydrogen. Compare it with its ions. For example, let's say I have H2 minus, or let's say I have H2 plus, because JEE loves these type of questions. Sir, but how will we compare? Why are you worrying? Now, the orbitals of whom we are studying and we are considering into our study and consideration, sir, molecule. So this hydrogen molecule has taken one more electron. So number of electrons over here were 2. So if this molecule has taken one electron, so it will become H2 minus. So number of electrons for H2 minus will be 3. Simple. Number of electrons for H2 plus, if H2 has 2 electrons, and if as a molecule I give 1 electron, I'll attain a positive charge. So number of electrons for H2 plus will be 1. Simple. Number of electrons, you know. Electronic configuration of the molecule, you know. So if I need to put 3 electrons, so 2 will go over there. Then the other one, Pauli says one orbital will have 2. So third one will be coming over here. So for H2 minus, I will be having 2 electrons as in the bonding molecular orbital, and 1 will be coming in the anti-bonding molecular orbital. So its bond order will be 0.5. Similarly, for H2 plus, sir, 1 electron is gone. So I'll be having only 1 electron in 1 sigma 1s. So what will be my bond order? 1 minus 0.2. So our bond order is still 0.5. Okay. Now, you calculated bond order of all the species, which was almost impossible for VBT. Now, what can we comment about their bond length and bond energy? First, I'm telling you about bond energy. Why? Because we very well know if bond order is high, then constituents are closer to each other. And if bond order is large, then bond energy, because bond order is large, then constituents are attracted towards each other to a larger extent, and it will be difficult to break them. So bond order is directly proportional to bond energy, and it is inversely proportional to bond length. We very well know this. Now, why I'm saying you should always see at bond energy first, because sometimes, like in this case, bond order for hydrogen is 1. Okay. But for these two ionic species, it is 0.5. So obviously, who will have the maximum energy? So bond order high, bond energy is high. So H2 will be having highest energy. No problem. But these two have similar bond order, but their energy is not same. How can we predict that? Then we have to, again, it's a factual thing, you will say. No. If somebody is containing electrons, for example, this H2 minus was having how many electrons? 3. The third electron will be going to sigma 1s. Sigma 1s is a anti-bonding molecular orbital. So because this third electron of H2 minus is having higher energy, so molecule will attain that higher energy. And if energy is high, my stability will be less. So my bond energy, my stability will be less. So H2 plus will be having more stability, more bond energy as compared to H2 minus. Why H2 minus? Although bond order is same, but it is less stable, so it will be broken easily. So if it is broken easily, that means it is less stable. If somebody is less stable, that means its energy is high. Why its energy is high? Because although its bond order is 0.5, but the third electron is acquiring a highly energized molecular orbital. If energy increases, stability decreases. This is an unstable molecular orbital. Whereas H2 plus will have only 1 electron. no extra electrons, no extra energy, more stability. So this is a beautiful energy, and obviously this will be the order of bond energy. So opposite will be the order of bond length. So for bond length, what you'll say? For bond length, what you will say? Because this is most stable, that means constituents are more closer to each other, so bond length will be least, followed by H2 plus, and the highest will be of H2 minus. These type of questions are loved by JEE. Now, what can you say about their magnetic behavior? Sir, H2 is diamagnetic, already seen. After getting that extra electron, it will become paramagnetic. After leaving that electron, it will become sigma 1s1, so it will also become paramagnetic. Now, moving ahead, I guess I'm making sense and these things are quite clear to you. Okay, let us test what we have studied. We know or not. Now, helium has how many electrons? 2. So He2 will have how many electrons? 4. So this molecule has how many electrons? 4. Let us fill those 4 electrons. Where? First sigma 1s, then sigma asterisk 1s. Okay, 1, 2, 3, 4. Again tell me bond order. Now I'm not writing it also. Sir, this is NB, this is Na, so this will be cancelled because 2 minus 2. Okay, I've written. So bond order is 0. See, VBT cannot tell you that helium does not exist, but because bond order is 0, that means they will not have any relationship in nature. But He2 plus and He2 minus will exist, because in that case bond order will not be 0. You have to check. So whatever possibility of bond order will be coming out through the formula, you can always predict about the stability of that particular molecule. So for now, for helium, we can definitely say it will not exist in nature. So if it is not existing, just leave it, move ahead. Now, coming to Li plus 2. Okay, sir. Lithium has 3 electrons, so Li plus 2 will have a total of 6 electrons. Okay, sir. Let us fill these 6 electrons. First, sigma 1s, so 1, 2, 3, 4. Sir, after 4? After 1s, what orbital participates? 2s. But when 2s also do what? They also have head-on overlapping. So sigma 2s and sigma asterisk 2s bonding and anti-bonding. Who will be filled first? Bonding. So 4th electron I have placed over here. This is 5th. This is 6th. Done. These two are cancelled because, sir, obviously NB minus Na. I am giving you a method to calculate easily. So these will be cancelled. How much electrons are remaining? 2. So bond order will be 2 by 2. That is 1. You can do complete also. That bonding is 2 plus 2, 4 minus 2. But obviously I know this 2 will be cancelled by this 2. Bonding will be cancelled by anti-bonding. So why bother? These are cancelled. I am just left with 2 bonding. So 2 by 2. So what is bond order? 1. You can even do for Li plus and Li minus, simply the way we have done. So that will be your homework, because such questions are loved by JEE. Now you can compare bond length, bond energy. I'm just commenting for Li2 plus. So what is our comment for its magnetic behaviors? Are all paired electrons, so it will also be a diamagnetic species. See, most of the molecules are coming out to be diamagnetic. That's why VBT would not be failing till oxygen. Over in oxygen they failed. Let us check why. Now, okay, so beryllium has how many electrons? So 4. So Be2 will have 8. So 1, 2, 3, 4, 5, 6, 7, 8. So again, these two will be cancelled. These two will be cancelled. So obviously beryllium bond order will be 0. So it will also not exist in nature. But who can exist? You have to check if bond order is coming positive, Be plus or Be minus, Be2 plus or Be2 minus. You can also calculate their bond order. Now, directly going to oxygen. This was the reason we first started MOT. I mean, the study of MOT actually started because of this reason. So let us check that whether you are right or not. Sir, first now tell us electronic configuration completely. Okay. First, who is filled? Sigma 1s. Keep iterate with me, loud and clear. Lowest is sigma 1s. After that, sigma asterisk 1s. Then who will be filled? Sigma 2s. Then sigma asterisk 2s. Now, coming to the 2p orbital, obviously, who will be having a head-on overlapping? So sigma. Head-on overlapping is more stable. If bond forms is more stable, bond energy is less. If energy is less, it will be filled first. So sigma will be having more stability, so less energy. Pi is less stable than sigma, so pi will be of higher energy. So who among p orbital, who will be filled first? So sigma 2pz, because z axis we consider as the molecular axis. After sigma 2pz, who will be filled? Sir, pi 2px and pi 2py are of equal energy. That's why these two orbitals. Now, these are the three. How many orbitals were participating? 3 and 3. That is 6. So 3 becomes bonding and 3 will become anti-bonding. Now, because when I'm having a head-on overlap, if plus is getting head-on overlap with plus, they will be very stable, sigma 2pz. But sir, if plus is head-on overlapping with minus, I do not like that minus. If I'm forced linearly combined, I will repel to the maximum. So if I was having a lesser energy where I do not wish to, that is not my friend, and you are asking me to stay at his place to have an head-on overlapping, sir, I will oppose this thing by anything. So because sigma 2pz was most stable, so when destructive interfering, sigma astic 2pz will be of highest energy. So I'm again iterating this electronic configuration of oxygen. Sigma 1 is sigma astic 1 is, sigma 2 is sigma astic 2 is, then sigma 2pz, then pi 2px and pi 2py becomes the degenerate orbitals. Both molecular orbitals will have equal energy, followed by pi astic 2px and pi astic 2py with equal energy but higher energy than the pi 2px and y. And the highest energy would be carried by sigma astic 2pz. Sir, why not going beyond? Because as said, for our syllabus, the molecular orbital theory which we should know is still sigma 2pz only, because here we can easily fill 20 electron, that is still neon. As per NCERT, they only say you should do till fluorine, because neon we'll definitely see it will not exist in nature. So now, sir, electronic configuration we know. Now prove that it is paramagnetic. Let us fill the electrons. How many electrons oxygen has? 8. So how many electrons? O2 will have 16. So let us fill those 16 electrons. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, make note of this. 11th will go over here. Till here, I was having no degenerate orbital, but pi 2px and pi 2py are degenerate. So 11th is going over here. So this will be 12th, then 13th and 14th. After that, I'll have pairing. So I've filled till 14. So this will be 15 and this will be 16. So I can clearly see these two electrons are not paired. Because they are not paired, so magnetic behavior of O2 will be paramagnetic. Bingo. This is the reason MOT was primarily developed. Now moving ahead, let us calculate its bond order. So I'm simply doing it with the trick that I told you. These will be cancelled, plus minus 0, bonding anti-bonding 0. These are 2 will be cancelled by the anti-bonding 2, but these will be left behind. The bonding one will be left behind. So how many are left behind? 4. So 4 by 2 equals 2. So bond order is nothing but 2. Now, because bond order is 2, so molecule is definitely stable. Can you compare it with its ions? Definitely yes. How? O2. For O2, I already know, because for O2, I have how many electrons? 16. Let's say for O2 minus, for O2 2 minus, for O2 plus, for O2 2 plus. I'm just giving you the number of electrons. Sir, if the neutral one is having 16, it will have 17, it will have 18. If it is positive, then 1 is going. So if the neutral one is having 16, it will have 15, it will have 14. Fill these electrons. We have filled till 16th. Nb minus Na upon 2. The one which will have more bond order will be more stable. If bond order is getting tied, the species having electrons in the anti-bonding will be, you should have less electron in your anti-bonding. That means anions. If I'm taking electrons, I'll be filling my anti-bonding. So these will be less stable. That is your practice. But But actually in JEE, number of question comes. They give you a bunch of 5, 6, sometimes 7 species and ask you to calculate its bond order. So many of my students have come to me, sir, JEE is a process of time. I mean, we know we can always make this MOT diagram and calculate. Obviously, we have to. Sometimes we have to. But at least for some questions, give us some trick. So I'm giving you a trick. If you have, let's say, 5, 6 molecules for bond order calculation, then you can save your time in JEE mains. How? Make 3 triangles. Directly make a photo, make a picture. Y-axis is having bond order. X-axis, you do not have to worry. Just make 3 triangles. 2 triangle of equal size till 1, 1. And the third triangle till 3. Point of difference will be 0.5, 0.5, 0.5. This is bond order 0. This is bond order 3. So difference of these 7 lines 0, 0.5, 1, 1.5, 2, 2.5, 3. Just write them. Wherever I am touching, this is number for if I'm having 1 electron. If somebody is having, you just have to know the total number of electrons. Like over here, I've written total number of electrons. You just have to know the total number of electrons. For example, if total number of electron is 16, bond order is 2. See, from the electronic configuration also, we found this bond order is 2. So this bond order, I'm directly telling you, you check. I've given you the electronic configuration for the species, but this is your homework. I've given you a trick also. You check that whether it is perfectly right. For example, if number of electrons is 17, sir, 17 bond order will be 1.5. If it is O2 minus, okay, O2 minus has number of electrons 18. Okay, 18 bond order is 1. O2 plus, that means 15 bond order is 2.5. O2 2 plus 14 electrons. 14, okay, you have to 14, it is 3. So who has highest bond order? So its bond length will be least, followed by this 2.5, followed by this. This will come in between because more be the bond order, lesser will be the bond length, more is the bond energy. But this is a trick. Some of you would be loving it because it will be saving your time like anything. But obviously, you should know how to make the electronic configuration as well. But, sir, after boron, I mean, after beryllium, you directly jump to oxygen. Why? For oxygen, I have told you. Similarly, for fluorine also you can do. For fluorine also you can do. Sir, sigma minus, this sigma 2s will be cancelled by this. This sigma 2p will be cancelling. Okay, this sigma 2p and this pi 2px will be cancelled by these two. So I'll be having these 2 electrons in the bonding molecular orbital. So for F2 it will be 2 by 2. So bond order is 1, definitely correct. For nitrogen, everything gets cancelled. So bond order will be 0. Therefore, neon, not nitrogen, I'm sorry. So neon will not exist. So for O2, F2, Ne and boron, we have already done it. So, sir, why this picture? Because actually for till beryllium, filling of P was not even required. So I didn't even tell you. What the scientist community has given to us. The concept of intermixing. What happens is, for elements which are having very small size, but till nitrogen, after nitrogen when we reach oxygen, we already know what is the electronic configuration. And how we know that electronic configuration? It's a common sense. The electronic configuration that we made for oxygen, that we will be following for fluorine and neon as well, is a common sense which we have made as per the energy level diagram. What we do not know is the concept of intermixing, which was introduced by MOT, that they said whenever atom is very small, so if it is very small, energy difference between 2s and 2p, we very well know 2s is more stable, 2p is relatively of higher energy. But for smaller orbitals, for smaller, lighter atomic orbitals, from till nitrogen and I mean smaller, lighter than nitrogen. So for nitrogen and lighter elements, the 2s and 2p atomic orbital intermixes. Sir, I do not understand this. Actually, these two energy level, it gets interchanged. Sir, please explain more. Explaining. What I'm saying is, suppose you and your smaller brother, for example, you and your smaller brother are there at your place, at your home. Somebody knocks from outside and the person is giving some dhamki, is abusing from the outside. Nobody, no elder is there. You are there and your brother is there at home. So when you are attacked by, I mean, not attacked essentially, I mean, do not take it personally. I'm just giving an example that you and your smaller sibling is there at home. Somebody is abusing from outside. Who will be going outside? If at all you have to go and outside and just have a chat, that what is it? Who will be going? You or the smaller brother or the younger sibling? Obviously you. What my point is, whenever people are very close, 2s and 2p energy difference is quite small. One is smaller, another one is higher. Although the higher one is not you, I mean, you are not your father. You are just elder than the younger sibling of yours. So 2p is of higher energy, 2s is of lesser energy. But whenever these smaller species are intermixed, energy distribution take place. So whenever this distribution take place, what happens is energy cannot be created nor can be destroyed. The one with lesser energy loses more energy and it is gained by the other person. Now this is intermixing. Again, not understanding, sir. Giving you a very beautiful example. I'm just giving you an example. For example, this is the electronic configuration for oxygen and all species after oxygen, which we already know. Sigma 1s, asterisk 1s, 2s, asterisk 2s, sigma 2pz, then pi 2px, pi 2py, pi asterisk 2px, pi asterisk 2py, and sigma asterisk 2pz. What I'm saying is these two will interchange. Why? Because S and P will have redistribution of energy. 2s and 2p. Who will have redistribution again? 2s and 2p. For example, let's say their energy I've written 5, 10, 30, 60, 90, 100, 200, 210. For example, this is their energy. Example. Now, what I'm saying is the younger brother, that is 2s, and the elder brother, I mean not daddy, just elder brother, which is 2p, they will undergo redistribution of energy. Let's say this 2s loses some energy. For example, let's say it loses 15 rupees. So if I had 30 rupees, 15 rupees I have given to you because you are going outside to fight. So I'm giving this extra energy to you because energy cannot be created, not can be destroyed. Excitation has to be jugadified, has to be arranged from house within. So this 2s guy is contributing 15 rupees. That elder brother you take is 15 rupees. So if its energy is getting reduced by 15 rupees, so 30 minus 15 becomes how much? 30 minus 15 becomes 15. So 15 rupees is still higher than 10, but still lesser than 60. So if at all it is losing 15 rupees, its relative position is not changing. That means here also it is having 15 rupees. And this 15 rupees is more than 10 rupees, but still less than 60 rupees. So although its energy is reduced, that is 15 rupees, but its relative position with respect to other atomic or molecular orbitals are not changed. But when that extra 15 rupees is carried by sigma 2p, it was, let's say, having an energy of 90 rupees. 90 plus 15 is 105. 105 is higher than 60, so it will be higher than sigma 2s, but it is even higher than this 100 rupees. So its position will come above pi asterisk 2 pi 2px and pi 2py, but obviously it will be lesser than 200 rupees. So it will be reaching this 105 will be reaching to the top, and this 100 rupees will be coming to the bottom. This is called redistribution, a very, very basic example which I have given. I hope you can also, although you have to remember this also, that for nitrogen, so this configuration is valid for nitrogen and lower atomic number species, and this is valid for oxygen and higher till neon, because till neon we have in our syllabus. Now, quickly applying what we have read, let us do it for boron B2. How many electrons boron has? 5. So B2 will have 10. Quickly fill it. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, because now they are degenerate and they will be filled first. And because they are degenerate, so Hund's rule says 1, 1 is filled and then pairing will take place. Again, what short trick we have read for bond order? These are cancelled. These are cancelled. So 2 bonding are remaining. So 2 by 2 is 1. So what is bond order for B2? Boron 1. But one more type of question is loved by JEE. They ask you, now this is of one atomic orbital, this is of another atomic orbital. They are not cancelled, but they are present where? They are present in the pi orbital. So this one and that one, for example, I'm giving in JEE, this is also asked that what is the number of bonds they are forming and what type of bond it is. So if one orbital, if any molecular orbital, this is also a very beautiful and important trick. If any molecular orbital is containing one electron, you will say it is forming 0.5 bond. What bond? If it is a sigma molecular orbital, it will be a sigma bond. If it is a pi molecular orbital, it will be a pi bond. Sir, if it is containing 2, then it will be containing 1. It will be containing 1 bond. Sir, then I have 1 electron here, 1 electron. So 0.5, 0.5. 0.5, 0.5 is 1. What type of bond it is present in? Pi. So what is, if bond order is 1, then what type of bond it is? This is 1 pi bond. Sir, pi bond can also exist in a molecule. VBT is drastically failing to explain this to us, but molecular orbital theory tells us that bond order for B2 is 1, and what type of bond is formed between 2 boron atoms? The molecule has 1 pi bond. Again, a very beautiful concept asked by JEE many times. Again, do it for C2. C2 has 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then pairing 11, 12. In order to calculate bond order, these are getting cancelled. These are getting cancelled. Those are remaining. So I'm calculating bond order only for those electrons that are remaining. If I'm getting cancelled with my anti-bonding, why I'll count them? Because they'll cease to exist. They'll be becoming 0 and B minus Na. So how many electrons? 4. So bond order for C2 will be 4 by 2. That is 2. Sir, but this 0.5, 0.5 is 1. This 0.5, 0.5 is 1. So total bonds are 2. What bonds? 2 pi bond. So actually C2 exists in nature. This C2 molecule exists in nature with 2 pi bonds. Sir, without sigma pi? Yes. Although when we have gone to Mother Nature and checked, we found that this C2 exists with 2 pi bonds. Although it is only found in gaseous state and also at very, very high temperature. So this is a factual science which you should not know, because these are what scientists have discovered later on. But this is the beauty of molecular orbital theory and type of questions which are asked, loved and asked by JEE. So let us now compare bond order of the nitrogen and the molecular nitrogen ions, the bond order and their strength post my complete day's break. Let us continue with it. Sir, we already know that for nitrogen, what is filled first? Pi 2 px and pi 2 py. So first doing it for nitrogen. How many electrons nitrogen has? Sir, 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, 11 and 12, and then 13 and 14. Sir, we can clearly see the bonding and anti-bonding got cancelled. So this becomes 0. Sir, this also becomes 0 because these are only bonding. So how many electrons are there? 6. So 6 by 2 is 3. So bond order of nitrogen is 3. We can definitely do this through the 3 triangle theory also, because I have told you in JEE many time a question comes that you have to find bond order for more than 5 or more than 4, more than 6 species. So doing this energy level calculation will be taking a bit of more time. So that 3 triangle graph that we have seen, you can obviously do that with a quick of time. But now here we are learning some concepts also. So finally wrapping it out. Now, because bond order is 3, so now through VBT also we know that nitrogen has bond order 3. One bond is the sigma bond and 2 bonds are the pi bond. So that 2 pi and 1 sigma can even be predicted by VBT, but there are, so like in case of C2, there were 2 pi bonds. For example, let us first do the bond order comparison, because this is also a very famous question. Sir, now this is very easy. 13, you remove 1 electron. Let's say 1 electron is removed. So how many electrons you are left, sir? 5. 5 by 2 becomes 2.5. So its bond order will be 2.5. Now, if I'm adding 1 nitrogen, so adding 1 electron, because N2 minus will gain 1 electron, so total number of electrons will be 15. So I have to add 1 electron. If that anti-bonding electron is added, it will cancel one of it. So again, how many are left? Sir, 1 is gone, so at least, and now 5 are remaining. So 5 by 2 is again 2.5. Now N2 2 plus, so in that case I have to remove 2. I have to remove 2. So if these 2 are removed, how many are left? 4. 4 by 2 is 2. So its bond order will be 2. Similarly, if 16 electrons are there, then after filling of this will also be filled. So one more will get cancelled. So how many is left? So 4. 4 by 2 is again 2. So bond order we can definitely see. But if you are asked to compare the bond energy, the stability, who is more stable? So more be the bond order, more is the stability, more is the bond energy. So obviously N2 is most stable. But out of N2 plus and N2 minus, as we have already discussed, when bond order is same, go to number of electrons. Sir, in N2 minus, it has got its bond order 2.5, but it is having an extra electron in the anti-bonding. Anti-bonding electron has higher energy as in less stability. So although bond order is same, but since number of the extra electron is going to the anti-bonding higher energy orbital, so its energy will be less. So then obviously this is more stable than N2 minus. Similarly, N2 2 plus will be more stable than N2 2 minus, I guess. Now these are some very probable question for JEE, so please make note of all these things, revise them very thoroughly. Now obviously order of bond order is this, bond energy is this, stability is this, so bond length will be of opposite order. Now let us comment on their magnetic behavior. N2, when everything was filled till here 14th electron, N2 will be, because all are filled, so it will be diamagnetic. What about N2 plus and N2 minus? If I remove 1 electron or add 1 electron, obviously it will attain a paramagnetic nature. So it will be P while it is D, diamagnetic. What about N2 2 plus, sir? If I remove 2 electrons, then these 2 will be removed. Then it will again become diamagnetic because all will be present. So this will be diamagnetic. What about N2 2 minus? If I'm adding 2 electrons, but they are acquiring pi-istic. So again, I'm having 2 unpaired electrons. So it will also be paramagnetic. Now what the difference that I'm trying to make is, let me give you a question for that. Now you have to calculate pi and sigma bond in N2 2 minus. Sir, we have already done it. N2 2 minus has how many electrons? So 14 plus 1 15. So 15 electrons you have to fill. Sir, 1 2 3 4 5 6 7 8 are filled. Now 9 10 11 12 13 14 and 1 extra 15. So what all things are getting cancelled? Sir, bonding will be cancelled by anti-bonding, bonding will be cancelled by anti-bonding. These 6 are left but will be cancelled by this pi-istic. So 1 will get cancelled. How many you are left with? 5. So bond order will be 5 by 2 2.5. Sir, this we have already. Why you are telling us again? Remember, in a molecular orbital, if 2 electrons are there, then you will have bond order 1 for that particular type of bond. Now, how many electrons we are left with? So these are the electrons we are left with. So you tell me, out of this 2.5 bond order, what type of bonds you're having? Sir, this orbital has 2 electrons, so it will have a bond order contribution of 1. What type of 1 bond you will have? 1 sigma. So you will have 1 sigma bond plus. These are pi bonds, sir. And this orbital is completely filled, so it will have a contribution of 1. But it is half filled molecular orbital, so it will have a contribution of half, as in 0.5. So 1 plus 0.5 is 1.5. So 1.5 bond order do you have, but this bond order is contributed by the pi bonds. Just like in case of C2, we were having 2 bond order, but that 2 bond order was there because of pi bond. So C2 has 2 pi bonds. Similarly, this has 1.5 pi bond and 1 sigma bond. Very, very beautiful concept which you can only do via MOT. Now, sir, we know now how to do molecular orbital theory application on molecules. Now you tell me about discussing a bit about the magnetic nature, extending magnetic nature to a bit. Whatever substances who are having unpaired electrons, because of the presence of unpaired electrons in atomic structure, through atomic structure, I'm iterating it again, through atomic structure, we know that radiation from outside, that is from any source, that is a white light. When white light comes to a species, and if that species has unpaired electrons, then that unpaired electron can easily get excited. And we know atoms are a black body. What energy they will take, they will also give back that energy. So whenever some free electrons, some unpaired electrons that are generally present in a system receives energy from outside, take up that energy packet, quantum of energy, gets excited, revolves around the higher orbit and completely throws whatever energy it has taken and again comes back. Now, the energy packet that I have received is from a visible range. So generally, a paramagnetic substance, whatever packet it throws, that electromagnetic radiation, the energy that it is throwing, comes in the visible spectrum. So that's why we see color. That is the reason we see color. So generally, who all compounds can show color? Only those compounds can show color who are paramagnetic in nature generally. And generally, whenever electrons are paired, as in substance is a diamagnetic substance, it will not show you any color. Now this is an extension of MOT with the block chemistry of halogens. That's why I'm discussing some 12th thing with relating to MOT. So if at all we know MOT of, let's say, fluorine, sir, fluorine will be having all molecules. I mean, let us just go into MOT of fluorine again. Now, this is fluorine. Sir, fluorine has 9 into 2, that is 18 electrons. So 18th electron is filled till here. Sir, this will get cancelled. The pi electrons you will be having. So number of electrons are 2. So bond order will be 2 by 2 as in 1. So definitely fluorine will exist in nature. And sir, but it is diamagnetic. And generally whatever species are diamagnetic, they should not show any color. Now, you just make note of this thing. What is the highest molecular orbital that is filled for fluorine? Sir, it is pi s-tick. So this pi s-tick will be termed as highly occupied molecular orbital. As in, this is that orbital, although it is anti-bonding molecular orbital, but it is getting occupied. So for fluorine, for halogen I'm talking, this pi s-tick behaves as a occupied molecular orbital. And what is the next orbital which is not occupied by these electrons? This one. This will become the least unoccupied molecular orbital. Now, this molecular orbital, both these homo and LUMO molecular orbitals are anti-bonding of same energy level, second 2p. So actually, in general, whenever molecules are having paired electrons, it cannot get excited with visible radiation. And therefore, they cannot get excited. Then they will not give back that electromagnetic radiation after, because I'm not receiving, so while I give back. But for case of halogens, this excitation is quite easy, because the molecular orbital that is available is not very far, is not of that high energy difference. So easily electromagnetic radiation from outside can be taken up by this paired electron also, because the level to which they have to excite is the energy difference is very small. So if this electron takes up this energy, gets excited, revolves in the higher energy state, and then give back that energy, so this energy is again given back to you. So whenever this electron will give back that energy, it will again come back to its ground state. And because of the throw of this energy packet, you will see a corresponding color. And that's why, although halogens are diamagnetic in nature, but still they show you color. And their beautiful color shown is loved by JEE. Let us learn those color also. Fluorine is a gas, and it is a yellow colored gas. Chlorine is also a gas, a greenish yellow gas. Bromine at room temperature is a liquid. What colored liquid? A brownish, reddish brown liquid. Iodine is a solid at room temperature and a violet solid. Sir, so they all are showing color? Yes. Why they are showing color? Because the reason, although they are diamagnetic in nature, but still they are showing color because from HOMO, which is highly occupied molecular orbital of there, which is pi-istic, and least lowest unoccupied is sigma-istic, and both are of almost similar energy. So the excitation is quite easy, and because excitation is easy, so any light will make that excitation happen. And because that excitation happen, electron jumps. Whenever it comes back, it throws back electromagnetic radiation, gives us to that electromagnetic radiation, and to our eyes that electromagnetic radiation is visible because that radiation is lying in a visible range. Now, so halogens are colorful due to this HOMO-LUMO transition. This is the point number 1. You will get various theoretical questions. It is actually an asked JEE mains question. Now, advanced asked a bit more, but I guess for mains also, because all the things we have discussed. So let us spend 1 more minute to it. Now, this is a complementary color wagon wheel, because this will be helpful in D block also. So discussing now only inorganic chemistry, this chemical bonding, I'm giving everything. Now, how to draw this wagon wheel? You can draw in your rough copy whenever such question come. From 9 p.m., this is 9 p.m., write Vibgyor. How? Anti-clockwise. So V, I, B, G, Y, O, R. Make a circle, 9 p.m. as in at the side 9 p.m. of your clock. From 9 p.m. start with a V, violet, and then write a Vibgyor. Now, what wheel you get is a generally it is developed by our statistical scientist, and it is known as a complementary wagon wheel, which says the opposite color. If violet color of light is getting absorbed, then the electron will come back to its ground state, will release energy. And what color it shows? It generally shows yellow color. So complementary colors are shown. For example, if yellow color radiation is absorbed, I will get excited, I will throw back some electromagnetic radiation, and I'll come back to, but the electromagnetic radiation that I emit contains what color? The complementary color. So if I absorb violet, I will throw back yellow. If I absorb yellow, I will throw back violet. Similarly, if I absorb orange, I will throw back some bluish radiation. If I absorb radiation of blue color radiation of that magnitude of frequency and wavelength, if I absorb blue, I will give orange, I'll show an orange color. So if I absorb red, I'll show green. If I absorb green, I'll show red, vice versa. So this is a wagon wheel which shows what I'm absorbing, the complementary I'm showing. Now, point number 1. Point number 2, we know through atomic structure. If you do not know it, I'm giving you again the revision, the recap. This is the direction of increase of frequency. So violet color radiation is of highest frequency. If the frequency is highest, then its corresponding energy is also highest. Because frequency and wavelength are inversely proportional, so violet has highest frequency, so red has highest wavelength. This we know through atomic structure. A quick revision. Now, why you are telling us this, sir? Because one more question is very important for this. Observe the color. Fluorine is giving you what color? Somewhat yellowish color. Sir, if fluorine is giving us yellowish color, then it must be absorbing a violet color light. Absorbing a violet color light means absorbing such an electromagnetic radiation frequency which is highest. Go directly down the group to iodine. Iodine is showing you violet color. So because it is showing you violet color, so it is receiving yellow radiation. Yellow radiation has low frequency, violet radiation has high frequency. High frequency as in high energy difference. That is what I'm telling you. When you talk of fluorine as an F2, in case of F2, the amount of energy required, because they are all paired, so amount of energy required for an electron to make a transition from HOMO to LUMO, this energy difference must be large, because if energy difference is large, then only what radiation you will require of higher frequency. So because fluorine is appearing yellow, that means it is receiving an electromagnetic radiation of higher frequency, of higher energy, because that means the transition to which it has to make is higher in magnitude. So for fluorine, the energy difference between HOMO and LUMO is largest. And for iodine, because it is appearing violet in color, where we have iodine, yellow, green, okay, this is reddish brown. This one is for bromine. So this one is of Cl2 and this one will be of I2. Okay, that violet thing, I guess you must be seeing. Violet in black is not appearing very beautifully, but because it is appearing violet, which is appearing violet? I2. So because I2 is appearing violet, so it must be absorbing an electromagnetic radiation of less, smaller frequency. So because if I'm requiring lesser frequency, that means my energy difference will be less. So the theoretical point out of that observation I'm making is, down the group from fluorine to iodine, the energy gap between HOMO and LUMO decreases. It is a JEE advanced question, directly an observation of molecular orbital theory. Now, ending this molecular orbital theory with one last topic, that is molecular orbital theory for heteroatomic. Sir, but you said if for JEE syllabus only we have for homatomic. Homatomic we have done. Sir, we will not do for heteroatomic because it is not in our syllabus. Generally, mains you will only have that homatomic, but because advance has asked them so many number of times, so let us spend 2 minutes, 3 minutes also on the heteroatomic molecules. Now, the trick, I'm giving you a trick also. The trick that you should know is, in order to calculate bond order, you apply MOT only. But whenever the question is asking you its magnetic behavior also, magnetic behavior of some heteroatomic molecule, then do not apply MOT. Go with the VBT. What does VBT say? If I've all my Lewis structure have all paired electron, then I'm diamagnetic. So what I'm saying is, for heteroatomic, I'm giving you a trick. This is not a fact. This is a trick of the questions that you will be getting in your competitive examinations. If for heteroatomic molecule you are asked by the question that you have to calculate bond order, apply MOT. But if you are asked this magnetic nature, then you should think like a Lewis structure VBT concept that we've seen. For example, if I have to tell you the bond order and magnetic nature of HF. Sir, HF is a heteroatomic molecule. Okay. Sir, so for bond order, you said you apply MOT. Sir, how will apply MOT? We know MOT only for homonuclear. For that also, there is a trick. What is the trick? If how many electrons nitrogen has? 14. So if a molecule has 14 or lesser electrons, go with electronic configuration of nitrogen and the lesser one. If the species having electron greater than 14, then go for electronic configuration as per oxygen. That is sigma 2pz will be filled first. So although this is not this you cannot grab my neck, sir, or anybody's neck. It is for questions per se, every reference says that in order to get, or else you have to learn MOT of every heteroatomic molecule, which is different for every molecule. So instead of learning that MOT for heteroatomic molecule, we are generalizing a statistical observation which is generally true. You cannot grab neck. That what is generally true, that if a species having electrons less than 14, go to nitrogen configuration, follow that nitrogen configuration for filling of molecular orbitals. And if the species having electrons greater than 14, so I'm just iterating it, not writing this 14 because I do not feel comfortable, but for questions you can definitely do it. Now Sir, how many electrons HF has? Sir, fluorine has 9, hydrogen has 1, so 10. So what configuration you follow? Nitrogen. So that's why I've made this configuration. Then for nitrogen, what configuration will follow? This one. Sir, how? We cannot predict. Sigma 1s, sigma asterisk 1s will get cancelled. Sigma 2s, sigma asterisk 2s will get cancelled. So those 8 electrons are cancelled. You can also do this, do like this in exam to be quick. So 8 electrons done, bond order contribution will be 0 because NB minus N will be 0 because of these 8. Now HF is having 10 electrons. So 8, 9, 10 done because 10 electrons. So nitrogen is pi 2px equals pi 2py will be filled first, filling them. Now because these are bonding, so how many electrons we have? 2. 2 by 2 is 1, so bond order will be 1. Simple. Now if you just go to MOT, you will say, sir, it is paramagnetic. But for magnetic nature, what I said, go to VBT, draw draw Lewis structure of HF. Sir, it is simple, H bond F. Fluorine has all paired electrons. Nitrogen, fluorine and hydrogen recently got electrons paired, so it should be diamagnetic. That is the trick that I'm giving you, because HF is actually diamagnetic. So if you just have to calculate magnetic moment, magnetic nature, go to VBT, what you already know, and for MOT you can apply. How apply? 14 less nitrogen, 14 more oxygen. I've given you a few more examples. You can obviously check this at your home. That will be homework. I'll just do for one. Let us say we do for CN. Let's say we do for CN and CN. For one CN. Okay. For CN I'm doing. Rest is your homework. If you feel any doubt, go to the description box, comment. I'll come back to you. Now, carbon has how many electrons? 6. Nitrogen has how many electrons? 6 plus 7 is 13. So 13, that means whose configuration will follow? Nitrogen. So because I'm having 13, sir, 8 are already done. 9, 10, 11, 12, 13. Okay. These are bonding only. So nothing, these will not get cancelled. So how many electrons you are having? 5. 5 by 2 is 2.5. So bond order will be 2.5. Done. What about magnetic nature? Sir, I can see one unpaired electron, so it will be paramagnetic. Okay. Sir, but this you are doing through MOT only? No. Although I have written paramagnetic, but then I have stopped and I'm now thinking, sir, CN, okay, CN, C triple bond N. Nitrogen octet is complete. Carbon has how many electrons in its valence shell? Carbon has 4 electrons. So out of those 4 electrons, this is not paired. See, I'm drawing its Lewis structure. This is not paired, so unpaired electron will make it paramagnetic. So obviously through MOT also sometimes you can be right, but for heteroatomic you should preferably go to the Lewis structure, the VBT of that molecule, in order to calculate its or predict its magnetic nature. Moving ahead. One molecule, because it is also loved by JEE Advanced and mains also has asked this few times. You should actually know the molecular orbital energy level diagram for carbon monoxide. Why? Because JEE loves asking bond order of CO and CO plus. Their bond order are always loved by JEE, and in order to exactly predict the bond order and bond length of CO and CO plus, you have to know the molecular orbital diagram for CO. Not a very rocket science, just giving you a very basic. I mean, people explain this through bonding and non-bonding atomic orbitals, but I'm giving a very easier picture of the same explanation. Now, the basic point of difference is carbon and oxygen. Sir, both have different Z effective. Whose Z effective is larger? Sir, oxygen. Oxygen has more number of protons. So because oxygen Z effective is larger, so it will attract its electron more. So if it attracts its electron more, the energy levels are less or stable as in they are having less energy. So if that energy level diagram here we draw as considering their energy. So if this is the energy, then energy of 1s orbital of carbon and energy of 1s orbital of oxygen, if you just look it closely, I have made that this is of higher energy and that one is of lower energy. So this will be happening for all the orbitals. Yes. So 2s of carbon will be of higher energy and 2s of oxygen will be of lesser energy. Similarly for 2p. So now when dissimilar orbitals are linearly combined, the structure, the basic structure of molecular orbital will also change. So that's why I told you you should have to know for all molecules, but for CO you have to learn this, although it is a very common sense. What is the common sense giving you now? So these are the molecular orbitals. So what molecular orbital will be having minimum energy? Again, what we know, sigma 1s. After that, sigma s-tic 1s. So this is the same which we have learned. Yes. After that, sigma 2s. But as soon as you reach the second energy level, bonding molecular orbitals, all the bonding molecular orbitals will be of lesser energy, and all the anti-bonding molecular orbitals will be of higher energy. This is the point of difference which gets created in nature in the molecular orbital organization of CO. So after 2s, in general, if you are not knowing this, then what you'll think, sir, carbon has how many electrons? 6. Oxygen has how many electrons? 8. 8 and 6 is, sir, 14. So if this has 14 and this has 13, so whatever it may be, what electronic configuration you will think of nitrogen. So what you will be filling? Sigma 1s, sigma s-tic 1s, sigma 2s, then you will be filling sigma s-tic 2s. That's what I'm saying. Do not fill sigma 2s, because in case of carbon monoxide, that anti-bonding orbital energy is not increased, it is increased to a much larger extent. So this is the space, this is the energy level position of sigma 2s. After that, for nitrogen, you think, what do you fill next? Sir, because it is 14, so electrons are equal to that of nitrogen, so we'll follow nitrogen electronic configuration, that is pi 2px equals pi 2py. After that, sigma 2pz. So this is what I'm telling you. Molecular orbitals are filled first, and all the anti-bonding. Sir, you have written only one anti-bonding. What about others? You will not even be requiring, although you can fill. That's why I've given this line, but it is not required. Sir, why it is not required? How many electrons you have to fill? For CO, 14. So let us fill those 14 electrons. So 1, 2, 3, 4, 5, 6, 7 and 8, because now they are degenerate. 9 and 10, 11 and 12, 13 and 14. So this will be the electronic configuration of CO, molecular electronic configuration of CO. Calculating its bond order, bonding, anti-bonding got cancelled. These are all bonding. So how many bonding we have? 1, 2, 3, 4. That is 8 electrons. 8 will be cancelled by 2. So how many are left? 6. 6 by 2 is 3. So bond order of CO is 3. Sir, but bond order of CO is 3 we know through VBT also. Why know this? Do for CO plus. For CO plus, 1 electron will be removed. It will be going from here. So because it will be going from sigma s-tic 2s, it will be removed from this. So only 1 will be getting cancelled over here. So how many bonding electrons you will be having then? So 2, 4, 6 plus 1, that is 7. So here I will be getting 7 by 2. So bond order will be 3.5. So because bond order of which you can never calculate using VBT. So bond order of CO plus is 3.5. So if bond order is large, then its bond length is less. This is a very beautiful concept which you should only know by molecular orbital theory of heteroatomic molecules. Moving ahead. So quickly moving to the last topic of chemical bonding, let us discuss some attraction forces that are physical forces. Although states of matter is removed from JEE main syllabus, but it is there in advanced syllabus, and knowledge of intermolecular forces of attraction per se is also essential part of a chemical bond, because chemical bonding is also a force of attraction. So remember this first slide, remember this slide that we have done in the initial stages. Chemical bonds, there are strong bonds which we have read, but there are also some weak bonds, the hydrogen bond and the van der Waals forces, where the energy required to break them, or when they are formed, because bond formation is always exothermic, so energy is released, but the energy released in these weak bonds are of the magnitude of 4 to 20 kilojoule. So discussing about these weak bonds, first we should understand what are physical forces of attraction. First we should understand what are attraction forces that we know through class 9th physics. So two plus minus attract each other. Now the attraction between plus minus is a physical force of attraction. because of which, if like ionic compounds are complete plus complete minus, they are physically so much attracted to each other that they exist as a solid in nature. So physical force of attraction results in the to define the state of a matter. If it is large, then it is solid, liquid and gas. So discussing about those intermolecular forces of attraction, let us first understand the first type of intermolecular force, which is dipole-dipole attraction, a basic attraction force, which like between two HCl molecules, because now we know through the polarity that HCl is a polar molecule, although it is covalent, but a covalent molecule. Delta minus, delta plus, the polarity because of electronegativity difference, this minus will be attracted by this plus, the attraction force to which we refer as intermolecular forces of attraction. This intermolecular force of attraction, we'll say it is a dipole-dipole attraction. Now, some statistical thing, because JEE has asked these values also. If we statistically calculate the energy, how much they are attracted towards each other, then the energy has a relationship, inverse relationship with distance between these constituents raised to the power 6, when these molecules are supposed to be rotating, because molecules will have some kinetic energy. But statistically it was found that when these molecules were given very low kinetic energy, or maybe they are assumed to be at rest, stationary, so when they are stationary, obviously this minus will attract that plus to a larger extent. So statistically it was found that the energy became proportional to distance between these constituents raised to the power 3, r3. Now, so these are, but sir, these are plus minus attraction, so people know that, yes. So these are intermolecular force. One more intermolecular force of attraction, which is a basic plus minus attraction. You can, if you have an ion, like you have some sodium ion, potassium ion, Cl minus ion, then this ion, for example, a Cl minus ion can also attract this HCl because it has a plus. If I have a Cl minus, so that ion dipole attraction can also be very well understood by the basic Coulombic forces of attraction. This ion dipole, as in it's a dipole, and if I have ion, this ion dipole is also a basic plus minus attraction. When statistically seen, the energy between those constituents came out to be proportional to 1 upon r. Now these are some statistical facts which I have given, although JEE has asked them very few times, but I have given all the necessary information. Now, after these forces, people at that point of time thought that non-polar molecules or non-polar species can never have attraction. A scientist called Van der Waal came into being and therefore gave an equation known as the Van der Waal equation. We study that in states of matter. But here we have to study first the Van der Waal forces. They are physical forces, but what are these Van der Waal forces? So except these two, because these two forces are not Van der Waal forces, these two forces people know through just basic Coulombic force of attraction, plus minus attraction. But what Van der Waal told to the science community, that even a dipole can have an attraction with a non-polar molecule by making it a induced dipole. For example, let's say HCl is a polar molecule, so it will have a permanent dipole. This permanent dipole can also attract a non-polar molecule. It can be Cl2, it can be any inert gas, because they are also non-polar. Sir, how can they attract? There will be concentration of negative charge, so this minus will induce. This is also a molecule is made of nucleus and revolving electrons. So if I experience a permanent minus, I will attract, in fact I will repel the electron cloud. So the electron cloud will be induced to the opposite side, because electrons are forced to the opposite side, so there will be a deficiency of electron. And what is deficiency of electron? It is plus. So this induced dipole can be attracted by this permanent dipole. So here also Van der Waal statistically observed that they were also attracted towards each other, and these forces were named as Van der Waal force. So what is the first type of Van der Waal force? Dipole can induce a dipole in another non-polar molecule, have an attraction force. Statistically it was found that energy was proportional to radius, I mean distance between these constituents, to the power 6. That was also radius to the power 6. Now Sir, it is almost of similar energy, yes, and this was told to the science community, to the nature, to all the academic community, and therefore these forces were named as van der Waals force. So, what is the first type of van der Waals force that we have recently studied? Dipole, induced dipole. Some other type, yes. Instantaneous dipole and induced dipole interaction can also take place, which is also known as London or dispersion force. Sir, what is it? Just by the name you can understand. Let's say it is instantaneous. For example, this was the breakthrough because it was thought that inert gases and non-polar molecules can never attract each other. They can. How? Let's say it's helium is a non-polar molecule. Yes, it is. Oxygen is a non-polar molecule. Yes, it is. But ultimately it is made of nucleus and revolving electrons. Sir, if you take this instant, I mean this instant as an exact at this microsecond. Sir, let's say at this instant, if electrons are revolving, then at least at this point of time, at this microsecond, if electrons are there, if they are here, then they are not here. If revolving electrons have an electron cloud here, then they are not here at this instant. In the other instant, the direction will change. But at this instant, this T, let's say it is their electronic scenario. Now, if at this instant I am minus, then I will force your minus away from me. So at this instant, this species will have its electron on the opposite side because electrons are gone. So here will be a. So at this instant, this is an instantaneous dipole. It is not a polar molecule, but at this instant it can at least have some polarity, and this polarity will induce the instantaneous polarity in the another non-polar species, and obviously this attraction will be weaker. But when van der Waals and the scientific community found this attraction force, the energy again came out to be proportional to 1 upon distance between these species raised to the power 6. Sir, it was of similar magnitude? Yes. And these forces are also termed as van der Waals forces. So these are the two type of van der Waals forces, and the third type of van der Waals forces, an ion, if let's say I'm a permanent ion, Na+, you are a non-polar molecule. But if this instantaneous dipole can induce a non-polar molecule, then definitely a permanent ion can definitely induce the non-polar molecule. They will also have some attraction, and obviously you can see that attraction energy was proportional to distance raised to the power 6. So this is a stronger intermolecular force of attraction, strong van der Waals force, where energy is proportional to distance raised to the power 4. Now this distance you can, I mean, if you can learn, you should. But for dipole and dipole induced dipole, this value is approximately, for dipole, it is 1 upon r raised to the power 6 only for rotating molecules. But it is definitely the same energy for ion, for dipole induced dipole. So this energy is proportional to 1 upon r raised to the power 6. You should learn, because this r raised to the power 6 for these two have been many times asked by JEE. Moving ahead. Okay, sir. Now we know what are physical forces. Then still they are physical forces. Why you are teaching this in chemical bonding? Now, some application of what we have learned. For example, in organic chemistry, it will be loved. So again, a chemical bonding basic used in organic chemistry as well. So discussing that also. Some example. For example, I have to compare boiling point of two molecules. This is N-ethyl. So ethyl is 2 carbon with the bromine. Hexyl is 4 carbon. 3, 4, 5, 6, 6 carbon, I'm sorry, with the bromine. Now, there will be polarity. Yes, sir. So, is it a polar molecule? Yes, this is minus and this is plus. This is also a minus, this is also a plus. So, will these molecules, sir, but these two are same? And the rest carbon chain, sir, it is non-polar. So how can we say which is having higher boiling point? One common sense we already know. If I have to cook 1 kg dal or 10 kg dal, which will be taking higher boiling points at 10 kg, because higher be the mass, higher be the boiling point. Why it is so? Because whatever be your nature, this increasing carbon chain, this increasing mass will also increase the surface area. We know, although this chain is non-polar, but still with the help of van der Waal we can say even non-polar species can attract each other, although to a very smaller extent, but they will also have some London dispersion force, instantaneous dipole, induced dipole attraction. So more be these lines of attraction, you will have to supply more temperature to break these intermolecular forces lines, and then only the molecule will be boiling. From this liquid it will changing to gas. So why it is said that more mass has large size has more boiling point? Because this will increase the intermolecular forces of attraction. So who will be having higher boiling point? Which will be having higher mass. Sir, if masses are same, so I'm talking for isomers, because isomers have same molecular formula, that is same mass. Let us compare these three isomers. N-butyl chloride, okay sir. Butyl chloride is this, sir. So one molecule will be attracting by another molecule through these intermolecular forces of attraction. Tertiary butyl chloride, tertiary is a 3-degree carbon. This is compacted. I mean, its nature, its surface area has been reduced. So it will be also attracting its another molecule, but because surface area is reduced, so this attraction force will get lessened because surface area is reduced. What about the third one, isobutyl chloride? What is iso? First carbon, second carbon, and a methyl group. So these are 3 numbers. So this is a picture of iso group, but this is isopropyl. Question is asking isobutyl. So I'll add one more carbon and a Cl. So you can see with branching here, branches are 2. Here branching is 1. So it will also have at least some surface area. Although this surface area is lesser than this, but definitely more than this. So as branching is increasing, molecule is getting compacted and surface area is reducing. So as surface area is reducing, boiling point will be reduced, because now only few intermolecular forces attraction lines are to be broken by the high temperature. So for isomers we know boiling point is inversely proportional to branching. But how do we know this? Through the logic of intermolecular forces. So who will be having highest intermolecular force among these 3? A. Followed by C, because it is less branched, its size will be more. And who will be having the least boiling point? B, because as branching increases, molecule become compact, so surface area decreases, and surface area decreases, so this molecule will attract the another molecule to a lesser extent, hence boiling point decreases. Moving ahead. Sir, but you are discussing all these physical forces in chemical bonding chapter? No. The extreme case of because dipole attraction, which we now know, what is an extreme case of dipole attraction? The extreme case as in, let's say if the dipole is formed by H bond F, H bond O, and H bond N, only these 3. So what is so special about these 3? Because they have the highest electronegative atoms. So this minus, I mean, if I'm more highly electronegative, I will snatch your electrons. So I'll get huge delta minus. Your electrons are snatched for hydrogen, so it will be huge delta plus. So magnitude of charge is increased. We know Coulombic force of attraction, it is proportional to charge and distance between charge. Moreover, fluorine, oxygen, nitrogen are the highest electronegative and second period element. So they are not small, they are very small. So their radius, their distance is quite small, and their charges, because of electronegativity difference, the magnitude of partial charge generated is quite high. So this intermolecular, this force of attraction, these lines of force that I'm mentioning with the dotted lines, this magnitude is not large, it is very large. It is so large that although this is a physical force of attraction, but when this physical force of attraction acts upon in a molecule, this force is regarded as that of a chemical bond. What is a chemical bond? Like ionic force of attraction plus minus attraction, the energy is proportional to 1 upon R. See, this energy is proportional to 1 upon R. For hydrogen bonding also, in some cases when this attraction energy was statistically quantified, it exactly came out to be of the order of 1 upon r. So therefore sometimes this hydrogen bonding is also referred as ion dipole interaction, as in some ion is attracting. That's what I've written also. Sometimes hydrogen bonding is even considered as an ion dipole interaction because the statistical value of energy comes out to be so strong. So hydrogen bond is also regarded as a chemical bond, although its logic, it is a type of physical force of attraction. But this physical force of attraction is of so much higher magnitude that its magnitude is approximately of the order of a chemical bond. So this special type of dipole-dipole attraction is called hydrogen bond. Now, some block chemistry regarding hydrogen bond, although we'll see so many applications, but starting with the first application, inert gases, they are inert, but now we know inert gases can also, they attract each other also. And if these inert gases will find water molecule, so if one inert gas has attraction from another inert gas also, that attraction force is van der Waals attraction. Van der Waals told us. But sir, if I am water, I'm highly polar. We have seen it has capacity to do hydrogen bond. So this high water will form that hydrogen bond with inert gases also. And because this has so much attraction tendency, hydration tendency, therefore inert gases are also soluble in water and they form water complexes. And those water complexes of inert gas are theoretically termed as clathrate compounds. So clathrate compounds are inert gases complexes with water. And you tell me, what can you comment about their solubility in water? Sir, if water is in excess, then they get soluble. What can you comment about their solubility? Their solubility will definitely increase down the group, because as the size of inert gas increases, it can be attacked by more number of water molecules. So it can be surrounded by more water molecules. More water molecules surrounding will force the inert gas to be more soluble in that particular case. Moving ahead. So moving to extent and strength of hydrogen bond. So extent, by the name predicts, is the number of hydrogen bond formed by a molecule. So HF as a molecule forms 2 hydrogen bond, very well predicted also. This plus will attract another molecule minus, this minus will attract another molecule's plus. Now this is a fact you should keep in mind. Water as a molecule forms 4 hydrogen bond, 2 by oxygen, 1 by hydrogen. H2O2 sir also has O bond H, but this O has an oxidation state of -1. It is one bond is connected to an equally electronegative oxygen, so its extent will be lesser. So how many hydrogen bonds? But number of hydrogen bond, that is extent, is 6. 2 by each oxygen, 1 by hydrogens. So number of hydrogen bond forms are 6. Talking about the strength, as I have already mentioned, using the thickness of the dotted lines, you can very well see which bond is strongest. Sir, HF, fluorine is more electronegative. Oxygen in case of H2O2, in case of water, is of -2 state. Not writing it because we already know it through redox reaction. So its strength is second. Then out of these 3, H2O2 in -1 oxidation state will have the least strength of hydrogen bonding. Now, for example, I mean, this is a practical fact. You can even calculate bond dissociation energy, and it has been calculated, but I do not wish to tell you do not need those details for examination. This is a common sense we got. Now, for example, I'm saying HF is strong, so let's say it has a strength of 20 rupees. Water is weak, so less, 15. H2O2 is even weaker, strength of hydrogen bond, let's say 9 rupees. Now, if I have to compare the boiling point of a molecule, sir, I have to break that hydrogen bond, then only those molecules will fall apart. So HF has how many hydrogen bonds? Sir, 2. So its strength is more. So 20 rupees is 40. So HF is attracted by another HF molecule with a strength of 40 rupees. For example, water, sir, it has a lower strength, 15 rupees. But the extent to which it is attracting another molecules are 15 into 4. So this will be attracted via strength of 60 rupees. So what, 60 rupees is higher or 40 rupees is higher? Sir, 60 rupees is higher. So combined effect of boiling point can be predicted by comparing both the extent of hydrogen bonding and the strength of hydrogen bond formed, and because of this, water will have a higher boiling point than HF, and similarly water will also have a higher boiling point than hydrogen peroxide. Now, summing all these things up, the intermolecular forces of attraction that we just read, we definitely can predict also, and we can definitely say also which is the strongest bond. Sir, hydrogen bond is not even a physical force of attraction. It's equivalent to that of a chemical bond. So remember this slide for the whole of organic chemistry. So I'm summing it up. Hydrogen bond is the strongest intermolecular force of attraction. This physical force is even treated as a chemical bond, followed by dipole-dipole attraction, and the weakest intermolecular forces of attraction are van der Waals forces. Now, the one question we have done for clathrate compounds. So basically discussing, a bit about clathrate compounds more. Actually, clathrate compounds are cage-like structures. So we definitely in water can form 4 hydrogen bonds. So it forms a tetrahedral geometry. It can, because it's a universal solvent, have so much of hydrogen bonding extent, that is the hydration enthalpy. It can make any molecule soluble in itself. So we'll see more applications of hydrogen bonding in organic chemistry. But I'm just summing hydrogen bonding for you, because hydrogen bonding application you will find in organic chemistry also. So whatever compounds are cage-like compounds are called clathrate compounds. Many many other species form clathrate compounds, but for our JEE syllabus, water is one of the famous example of a compound which can form cage-like structures in its cage. It can imprison all the molecules because it has such a high hydration enthalpy. Now, having known this fact, the question is number of molecules which form clathrate compounds. They have to get inside the cage. Water will take everybody inside them. So water can form a clathrate compound with mostly all of them. So yes, oxygen, CO2, SO2, H2S, methyl cyanide, MeOH, HCl, HBr, all will form a clathrate compound, H2O2, and this helium and neon we have recently seen. But by this question I'm tricking you. Point is, size of helium and neon are so small that if water needs to hydrate them, it has to surround these constituent atoms. All the other molecules are having atomicity more than 1. Inert gases, especially helium and neon, because their size is so small, so these are some exceptional examples that they do not undergo solubility in water, no matter how much excess of water you have taken. So this is a tricky fact which I'm testing you with. So you can count all the number of molecules except helium and neon, all will form clathrate compounds. So I guess we have discussed this also. Solubility increases down the group, but helium and neon are less soluble. But practical fact is they are insoluble in water. So for this question, what is the force? What is the force? Sir, it is a dipole. And dipole will induce a dipole to inert gases, but not all inert gases except helium and neon, and will form a soluble complex with them. So the option will be dipole, induced dipole. Moving ahead. So moving to the types of the hydrogen bonds, they are basically of 2 types. Intermolecular hydrogen bonding, which are definitely more strong, and the intramolecular hydrogen bonding. Intermolecular hydrogen bonding can be of homo intermolecular, as in when constituent molecules are similar, like HF is hydrogen bonded with another HF molecule, and it can also be hetero intermolecular hydrogen bonding when one water molecule having strong hydrogen bonding can attract all those organic compounds, because solubility law says organic compounds are non-polar. They do not dissolve in water because it's a polar solvent. But Water, because of hydrogen bonding, has the capacity to dissolve all those organic compounds who can also form hydrogen bond with water, a very useful application for all of organic chemistry. Now, coming to the intramolecular hydrogen bond, intramolecular, as the name suggests, when it takes place within the molecule. So it only takes place within a molecule when a ring formation takes place, and especially as per Bayer, 5 and 6 membered ring are free from angle strain. So whenever a ring formation takes place because of hydrogen bonding, then in those particular cases, intramolecular hydrogen bonding always creates a stabilizing effect, and that stabilizing effect is also termed as chelation. For example, the famous salicylaldehyde contains intramolecular hydrogen bonding. Orthonitrophenol contains intramolecular hydrogen bonding, but as I said, intra is always weaker than inter. So if you, let's say, if you have to compare boiling point of the para isomer of this salicylaldehyde with this salicylaldehyde, which is the ortho isomer, so obviously the I've increased the number of H bonds because intermolecular hydrogen bonding is strong. So these two molecules are quite attracted towards each other. It will be difficult to bring them apart, so its boiling point will be higher. For the species whose boiling point is higher is generally termed as less volatile because it will not form vapors easily with respect to the other species which has a lower boiling point, and hence also termed as the more volatile component among the two. Moving ahead, now some applications. Now these are some direct questions which many number of questions you will get of hydrogen. For example, orthonitrophenol is less soluble in water because orthonitrophenol is involved in intramolecular hydrogen bonding, while para isomer is involved in intermolecular. So if I want to get dissolved in water, I should attract water, but orthoisomer is attracting itself and not water. So what will be the reason? Because orthonitrophenol shows intramolecular hydrogen bonding. That's why. Moving ahead, now hydrogen bonding application, you will find very number of hydrogen bonding applications, but that we'll be discussing in organic chemistry, because organic chemistry we'll be discussing independently, and we have taken already a lot of time for chemical bonding. But as promised, for block chemistry, these block chemistry concepts are also very famous. So some application for the block chemistry, if you consider the hydrides of p block elements, down the group mass increases, so size also increases, so van der Waals forces of attraction should increase. So down the group, what you expect? Melting and boiling point should increase. But for in case of nitrogen, oxygen and fluorine, as you can clearly see, down the group it is increasing. Boiling point is both melting point and both boiling point is increasing. But for water, HF and ammonia, what you are expecting them to be? Do you expect, according to periodicity, you expect, because they are for second period elements starting the group, so they should have the minimum melting and boiling point, rather they have the highest value of melting and boiling point in their respective group. Highest as in, now or few, I mean, these questions are also not very famous. As per mains, that information was more than sufficient, but because advanced loves it, so mains have also started asking these factual things. For example, if speaking of melting and boiling point of precisely the nitrogen family, obviously hydrogen bonding is the strongest intermolecular force of attraction, so it will increase the melting and boiling point of that particular component. But factually, it has been seen that if my mass is very high, then there may be a case that I can even supersede your hydrogen bonding. For example, when talking of melting point, ammonia wins the race from even bismuth. But when talking of liquid state of ammonia, although boiling point of ammonia will be high as expected, because it is not attracted by very tuchu, a small intermolecular force of attraction. It is attracted by strong intermolecular force of attraction, that is hydrogen bonding. But when it is undergoing a boiling from its liquid state, it loses the value. It is increased, but it loses the battle of having highest boiling point from bismuth and antimony both. So it comes third. So this is a trick that I make, that for melting it is obviously first, but for boiling it comes third. Similarly, for water, thanks to Mother Nature, water wins the race in melting also and boiling also from its constituent elements, while fluorine loses the battle and comes second for melting, loses the battle from iodine. But when talk of the boiling of HF has the highest boiling point among its hydride of group 17. Again, a very important point, a very famous point loved by JEE. If you compare melting and boiling point of hydrides of second period element, water no doubt wins the race. But in melting, ammonia becomes higher than HF, and in boiling, HF wins the race with respect to ammonia. Very important point you should remember. Now, looking at some few examples of what paper has asked, these are just JEE Mains 2024 questions. You will see how small and beautifully they ask questions. You have to tell which one of the following is the correct option. Okay, hydrogen bonding exists when hydrogen is covalently bonded with an electron. This is the definition of hydrogen bonding. Definitely correct. Intermolecular H bond is present. Sir, orthonitrophenol has intra. This is saying inter, so this is wrong. Intramolecular H bond is present in HF. No sir, it has actually inter, so it is saying intra, so this is also wrong. Fourth is magnitude of H bond depends upon physical state of compound. Yes, when ammonia was in solid, its melting point was coming out to be, it was the winner, but it was not the winner, but for boiling it was higher. So obviously physical states decide, because molecules will stay close to each other. So obviously the state will decide the magnitude of H bonding. Now, hydrogen bond has powerful effect on the structure and properties. Yes, the application, the properties, the melting point, boiling point, their solubility, everything changes. So it definitely has an effect. So what are the correct option? 1, 4 and 5. This is a JEE Mains question. Piece of a cake. You do not have to pick up your pen and do the answers. Now, number of molecules which show hydrogen bonding. Again, a mains question. Obviously, methanol, O bond H. Water, yes. No. Orthonitrophenol, intra. The question is saying hydrogen bonding, not inter and intra. So it will also be considered. HF, yes. Ammonia, yes. So answer is beautifully 5. Select the compounds from the following which show intramolecular. Sir, intra chelation effect has. So option D is right. Moving ahead. Not moving ahead. We have utilized so much of time. More various application of hydrogen bonding we'll do in organic chemistry. Now, for this side of inorganic chemistry, this is me, Gaurav Singh Arora, signing off. But you have to practice a lot of questions which I have personally selected and given you in form of DPP. So go to the description section, download them and practice them hard. We will meet in the next one shot. Till then, bye-bye and take care.